Welcome, everybody. It's very nice to have you all here. The weather is very hot today in Athens. You're not so lucky about that. But I think that here it's like in Black Forest, as we said before with Kathy. So I think we're going to have a very nice workshop. It's quite a coincidence that these three universities here have, as their main logos and in their main symbols, the three philosophers. Pythagoras from the University of the Aegean, Plato in the University of West Attica, and Aristotle in the University of Aristotle in Thessaloniki. Aristotle University in Thessaloniki, sorry about that. So, I don't know if you want to talk about the three philosophers, Nikos. I have prepared something.
No, you should.
So, the three philosophers, the first one, the Pythagoras, is the oldest one. Let's say he lived in the 6th century before Christ, BCA, and this one was more focused on mathematics. But he had created a school and some fans, the Pythagoreans, and let's say a specific movement, the Pythagoreanism, and all these guys started to do not only mathematics, but also working about metaphysics and other things. So Plato was, let's say, came to Earth in 200 years after Pythagoras, but he was very much influenced by the theories of Pythagoras. He started working on the mathematical perspective of the world, but he declined from this approach and he became more a guy who believed that there are different worlds, the worlds of ideas, and what we see and what we perceive with our eyes and with our, sensors is not the reality, but something close to reality, and not so ideal. And Aristotle was a student of Plato. He studied with him for 20 years in the well-known academy of Plato. And although he was very much affected by the theories of his teacher, he became a little bit closer to Pythagoras. He went a little bit closer to Pythagoras. He believed a lot on the empirical, things. He was more, let's say, experimentalist and less theoretician compared to Plato. So the three philosophers have more or less founded and created a very strong construction, the construction of ancient Greek philosophy, not only the three of them, but they are three very much, I would say, important philosophers and mathematicians. And probably they have started thinking about artificial intelligence at that time because Plato, as I told you before, he believed that there are two worlds, the world of reality and the world of an ideal world, which we should approach step by step. So that's all from my side, just a short introduction about philosophy, since you are in Athens. And I will give the floor to Nikos from Thessaloniki.
Yeah, thanks a lot, Adoni, and thanks also for showing me as the Aristotle, which means that I'm the younger among the three of us. So welcome also from my side. And I'm really glad to see also quite a few of our students from Thessaloniki who made the way here, and several of you who made a really long trip in order to arrive here. And just a few things about the history, not of Greece or of the philosophers, but of this workshop. So all this idea came actually out after the first workshop that was organized in Trento by Lorenzo Pavesi. We're really glad that we have him here. So after that, we thought that it might be good to have a continuation to that workshop. So we organized one in Thessaloniki, which was in the middle of the COVID crisis. So it was only virtually attended. And now, thanks to the initiative also of Adonis and Harris, we decided to have it here. And what I would like to say is that it would be really brilliant if we can, by tomorrow, for example, before finishing, have someone volunteering for having the next one. We think that it's a good period of time to have it something around June, July, or whatever. And we're a rather small community that is constantly growing, however. So we think it would be really nice if we can keep this conference on an annual or a biannual workshop, actually, not conference basis, so as to get together and discuss all the things in more depth, actually, as we typically manage to do in the regular conferences. So I'm giving the floor then to Haris, and enjoy the time here in Athens.
Hello from me. Also, I would like to thank you for coming to Greece and traveling around the globe in order to get here. Adonis mentioned about the past. Nikos mentioned about the current situation. So I will try to put into focus about a little bit about the future. So I think it's really, really important that this is a growing community, and this is a thriving community that is growing every day. So it's really, really important to keep this initiative that Lorenzo Pavesi started in Trento a couple of years ago and reorganize and make it an annual event in order to exchange ideas and even include more and more aspects so as to merge new ideas and new concepts, and apart from photonics, electronics, software approaches, in order to make this community stronger and bigger. So, from my point, I would like to thank you as well for coming here.
Okay, some practical issues. I don't know if all of you have an internet connection through edu-ROM, or I don't know. If people from US do not, we can provide you a Wi-Fi access. So please tell me if it is necessary. We already have set it up. And let's start the first session. Just give me a second to find the program. Sorry about that. Okay, the first session is about programmable photonics for machine learning applications. And the first speaker is Jose Campmani from University of Polytechnic of Valencia and also iPronics. So you can come.
Okay. We start back, adjust the clock. So Okay, good morning to everybody. Thank you very much for inviting me. Haris, Adonis, and Nikos. I don't know if I said it in the correct age order, but okay, you will excuse me. So yes, today I'm going to try to provide you with an introduction to the fundamentals of analog computation in the way that we are advocating, and that is by using programmable photonics. I'm not going to stop a lot on programmable photonics because it's Wim after me, and he's going to probably provide a fantastic talk as usual. So I will just stick to this content. So my index is the following. We are proposing a new way of doing computing in photonics, so this requires a not so short introduction. And I would rather prefer to elaborate on this because I would like you to understand. And this is not a kind of huge scientific conference, but it's a workshop. So it's an opportunity to launch the ideas and afterwards maybe discuss and get some feedback. Also, it's a new concept, so it's not already been worked thoroughly. There will be an opportunity to do this in the next 5 years within an ERC grant. So don't expect me to provide you with very refined results, which I'm not going to do, just the basic ideas. Any computing theory revolves around concept of unit of information, so I'm going to try to discuss what is the unit of information that we propose, and of course the basic operations or gates that we envisage for doing this. One of the features that you will see of this way of doing computing is that in a way it resembles quantum computing, although we cannot unfortunately exploit the non-locality effects or the entanglement effects. But nevertheless, we can do we can share some of the principles and, of course, do some things that quantum cannot do. And I will try to explain which are these prohibited operations that we can do with this way of doing computing. And we'll provide you with some more considerations and maybe a roadmap, okay? And then finally we'll go to the summary and conclusions. So, first of all, just a few clarification about what we understand by signal processing versus computing. And signal processing, we are thinking always about transforming waves, like, for example, doing phase shifting or other kind of operations. But we don't work with units of information. Usually, we don't need to work with them compulsory. While in computing, what we do is we transform units of information. For example, in digital electronics, we change zeros and ones because these are the units of information. Okay, so what I want to say really is that they are really independent concepts, okay? However, this doesn't mean that we cannot use waves to convey units of information. We can do that, of course. So that means that at the end of the day, computing is something that is embedded in signal processing. We can do signal processing of waves which do not carry units of information or which carry units of information. So this is to put a little bit computing and signal processing into context. So regarding computing, just a very brief refresh, we have digital or discrete computing, where we transform units of information that are described by discrete valued functions or digits, or we have also analog computing, and we understand by that the transformation of units of information which are defined by continuous valued functions, right? So just these are the two main computing paradigms, and you probably already know, but I'm gonna show in this slide a small classification of the main computing theories that you can find available. Of course, we have the very powerful digital computing that is supported by Boolean algebra, and then we have on the analog side, analog and neuromorphic. So quantum computing is supported by strong algebra theory. It's not Boolean algebra, and this is one of the basic building blocks of the computing approach that we are going to propose here. So, yeah, if we were to make an overview about what are the, let's say, mathematical concepts or the theories behind the different computing approaches and the technology that we employ to implement them, we would find that, of course, digital computing is mainly done by electronics. In quantum computing, you have different options. You have photonics, of course, but photonics for really doing the linear part of the quantum computing. You have superconducting technologies. And in neuromorphic, you can find in the literature both approaches based on electronics, based on photonics. But there's a void space here. There's like is there any computing theory that would be suitable mainly for photonics? Okay. So this is one of the main statements that I want to do here, that the current computing paradigms that we have available were not in principle conceived to leverage the specific properties of photonics. So this is one consideration. Of course, there's been a lot of work on the so-called optical computing. And the optical computing, first of all, in the first years that people working on optical computing tried to mimic digital electronics. But there is a problem with that. We don't have nonlinear concentrated elements that can be squeezed in circuits. like the transistor. We have optical transistors, and it's very difficult, if ever, would be possible to integrate or an optical transistor, because you need these nonlinear effects that are hard to engineer in a chip. We don't have memories. I might remember that photonics, photons are bosons, so they cannot be stopped. They cannot be stored in the same way that we store electrons. Okay, we can consider other approaches to store, like, you know, delaying, storing in cavities, but it's not the same thing. So probably that indicates that it's not the right platform to do this digital electronics. Analog signal processing, on the contrary, is supporting, like I said before, quantum computing and neuromorphic or neural computing. So the idea is, well, can we do analog signal processing either with some of the available photonic platforms? And of course, you can think of many, like metamaterials, but we believe that programmable integrated photonics is the right one, because it provides on-chip capability, and it provides a relatively straightforward way of reconfiguring and programming different elements. So, about programmable integrated photonics, this is my only slide. So we arrange the programmable integrated photonics in meshes, waveguide meshes, where we connect what we call tunable basic units, or small Mach senders and phase shifters, and we activate those through a different variety of elements, maybe currents, maybe voltages if it's MEMS, or a phase shifter based on MEMS, etc. So the idea is that we are able to, by reconfiguring these small tunable basic units, we are able to provide matrix transformations, for example. But we can also do other tasks like filtering and other things which are not necessarily computing. Okay, this is an example of a non-processing function that is not carrying or is not affecting units of information. Okay, so right now in photonics we have signal processing, but we don't have so much a specific computing theory. Right, so the idea is to go a little bit beyond that and fill that void space in the table that I showed before. And this is what we call analog photonic computing. That is a theory where it is the mathematics that match to the technology and not the other ways around. So we are reversing the process. Okay, this is another statement that is important to understand. So the objectives would be to transition or evolve from optical processing only tasks to true optical computing, to match that approach to programmable integrated photonics, to have a platform where we can do this photonic computation, but at the same time is compatible with electronics. And the ideal thing would be to, a futuristic view would be to have a computing system where both an analog photonic and digital electronics can be integrated on chips, on the same chip or in different chiplets, but it can be interconnected. So this means, as far as analog as photonic computation or analog photonics is concerned, developing two new fields of research. The first one is what we call analog photonic computing. This means addressing what is the unit of information, what are the relevant gates, and what are the relevant algorithms. And the other one is analog photonic information theory. And this will take care about other issues which are more standard in other computing theories, but that you nevertheless need. And I've listed a short, there's a short list of the main relevant things. So as I said, this concept is not very well developed in its entirety. It will take some years, but the basics you can find in this archive paper. It's rather long, so all the basics of what I'm going to tell here are already included there. So let me jump into the unit of information. Okay, I'm going to talk very briefly about unit of information, and I deliberately titled this view graph as rationalization. That means this is something that we are going to propose de facto and we're not going to demonstrate, okay? So since our building block in programmable photonic, integrated photonics is a 2x2 Mach-Zehnder units or interferometers, then we will try to use a two-dimensional unit of information. Second, leverage on what optics is good for. And what is optics good for? It's good for managing interference, especially integrated circuits. That means our variables will be modulus and phase. So we're going to work with analog complex signals. So, like I said before, this leads to a two-dimensional analog complex function, which is what we call the analog bit or ambit. And it's defined as you see here. So it's basically the unit of information is represented by a two-dimensional vector where each vector is multiplied by a complex amplitude. And this complex amplitude brings the information of amplitude and phase, like I said before. This is the unit of information. And it reminds a lot of the qubit, okay? The qubit is, if you replace the former, the vectors that you see E0 and E1 by the Dirac representation of the 0 and the 1 is more or less the same representation with some restrictions. But there are some differences. So first thing is that the functions are implementable with classical waves, not with single photons. Second, we don't require that the optical power is normalized. So you don't have this restriction of being, the sum of the square modulus has to be 1. Third, it can span many dimensions. I just presented a two-dimensional definition of the unit of information, but it can range to any dimension, including dimension 1. And finally, in theory, we can consider operations and we can build multiple ambit states, either both considering tensor or Cartesian products. So it's very flexible at the end of the day. The most straightforward representation is using a dual ray with two waveguides, as you can see here, where each of the functions that represent the two vectors, the two dimensions of the vectors of space, are encoded in a different waveguide using pulses. Of course, there are other kinds of modulation formats that you could use, of course, that are common in optics. But do you think that, practically speaking, are less interesting? Might be polarization could be feasible as well to consider, but mainly these are the options, kind of mode encoding, polarization, frequency encoding, or time encoding. And for the detection as well, like in any optical system, we can consider either direct or coherent detection. If we consider the coherent detection, we will be able to access the four variables of the two dimensional complex valued functions. That means the modulus and the phase. But if we consider just direct detection, we can access to 3 degrees of freedom. And this is very much like quantum computation or the qubit. So we can represent our states in a sphere, which we call generalized block sphere. Why we call it generalized is because the amplitude is not restricted to 1. So besides the two-dimensional angular encoding systems, you can also consider the third one, which is the radius of the sphere. So bear in mind that this, what this tells you is that you have a new way of encoding the information. Because in principle, and with the restrictions that noise sources will provide you, you can use all the states in the sphere, or in the different spheres. You will be restricted, like I said, by noise. You cannot put all the points as closer as you want. But bear in mind that in quantum computation, regardless of what you do in the middle of your operations, you can play with the whole block sphere if you want. But at the end of the day, when you detect and you collapse the wave function, either you go to the north or to the south pole. So what you materialize at the end of the day is a two-state system, not more than that. Here is different. You can detect, you will not destroy your information, so in principle, you can encode and recover all around the different block spheres. That means with a two-dimensional system instead of...
Creo que no te entiendo.
Oh, sorry. He doesn't understand me, she. So, so at the end of the day, instead of having two states, you can have maybe tens or hundreds with these two. That makes a different approach. Okay, so just keeping to a single ambit gate, of course, is a two input waveguides, two output waveguides, and you can, of course, you can do linear. You could do nonlinear transformations if you wanted. I'm just going to focus on linear today, and of course, this entails a matrix relationship with a possibility that in order to have this mathematical transformation universal, you can use the Euler rotation theorem. That means that you can, in the case of unitary gates, you can provide any arbitrary transformation provided that you cascade 3 rotations around 2 non-orthogonal axes. So it turns out that programmable photonic elements that you use in programmable photonic circuits naturally give you these rotations. So for example, a directional coupler gives you a rotation around the x-axis. A phase shifter, a dual rail phase shifter, gives you a rotation around the z-axis. And a Mach-Zehnder, balanced Mach-Zehnder, 3 dB Mach-Zehnder interferometer gives you a rotation around the x. So at the end of the day, you can construct these universal ambit gates by cascading 3 of these elements, and you can end up with very compact device setups for your gates, like this, for example. This is one option. There are more, for example, and this is basically a standard element for waveguide meshes. So, like I said, you don't need to restrict yourself to unitary transformations. You can do more complex general transformations, and I'm not going to go a lot today here, but the basic idea is that you can have non-conservative gates, and in this case, you would need to make the gate a little bit more complex because you need to be able to apply the singular value decomposition theorem, and that means that you will cascade three different transformations, which 2 of them are unitary, and the third one is a diagonal, which can be by amplification or by attenuation. And waveguide meshes, you can only select the attenuation option. But if you decide to use another programmable type of circuit, which is not strictly based on regular waveguide meshes, you could still be able to try and include amplification with the precaution of not generating non-desired lacing effects. Okay, so of course there is the opportunity of doing basic operations with those gates. You can do control gates. And moreover, in this case, the controlling bits can be supplied electronically with the signals that you employ to control your circuits, your phase shifters, for example. And one of the things I wanted to, let me skip that, do is combine these 2x2 gates to do either combinational or sequential. As you see the systems, combinational systems are like feed forward, while in sequential you are going to take the outputs from previous, the output ports and feed them back to the input ports of some of your gates. So this is something that is, in order to do this, you need to have fan-in and fan-out elements. So it turns out that you can do fan-in and fan-out elements with programmable photonics, of course. You can design systems where you will have the two states and provide you with output states which are a combination of your input states. And so, for example, this is an example. There's a detailed construction in the paper. The idea is that, for example, in one of these particular constructions, if your input state in the lower port is 0, then you will have a fan out. So it's a division. And if it's not 0, you can exploit the output port, the upper output port, to provide a combination, a fan-in with positive or fan-in with negative combination sign. Okay, this would be the implementation, okay, of again, so these are very basic principles just to show that you can do. Also, reconfigurable sequential systems can be provided as long as you have fan-in and fan-out, so you can engage different gates and provide feedback signals. So this opens the path to analyze and design more compact devices, because more sequential, as you may remember from digital electronics, sequential systems usually can emulate much more complex combinational ones. So this is a path for considering the design of much more compact systems. Again, this is just pointing out ideas, but for example, this is an example that we have in the paper. It can be shown that this system, which is a combinational one, and includes 4 gates and the fan-in and fan-out, can be reduced to this one where we save one of the gates, one of the transformations. And of course, this is a very basic example, but you can go and extend, and this is one of the things that we are going to work. Not only the design of sequential, combinational, but also the synthesis from one to the other. Okay, so let me skip that. And just finally say that in principle, this can be employed to implement or emulate other computing theories, like digital. But I said that it's not interesting, but you could in principle do that. And if you do you use the 1D approach for programmable photonic for this ambit, then in principle you would be able to emulate neuromorphic computation architectures. So I'm just running out of time. This is the roadmap. So it's defining the unit of information, designing principles for combinational, sequential, from basic gates to multi-port gates, doing PIP implementation with PIP, and probably then finally develop the algorithms and the information theory. Kind of comparison, qualitative comparison table of what can you do and what you cannot do with different computing theories. This is digital, quantum, neuromorphic, and analog photonic computing. Of course, this is controversial. Probably some people here will not agree with that. We can discuss later, maybe. But what we cannot do is, like I said before, is entangling or instantaneous non-locality. So, fine. My last view graph, this is the picture. So it entails not only APC, like I said before, not only playing with the physical waves and the systems, the hardware systems that you have, but also extending to the outer parts. We don't usually deal with that in photonics, but again, we haven't developed a computing theory per se for photonics. We have imported other computing theories, so we didn't have to do that. An example of that is how to encode successfully the different states of the ambit into the different points of the generalized block sphere, and also to be able to retrieve that information safely in the presence of noise. So thank you very much. This is, I'm not going to read this, but these are the main features of that. And just remember that if you have good students, we are hiring. The project will start next September, so please, if you have some possibility of distributing, I would thank you very much for that. So thank you.
Thanks, Jose, for this radical presentation. Yeah. Is there any question from the audience? We have the microphone here if you need.
Don't throw me tomatoes. Hey, I don't have developed all the story yet.
Thanks a lot for this very nice, indeed radical talk. I have a question regarding more or less the last slide that you showed, where you go through, you want to deploy the information theory for using all this new mathematics within a channel.
Yeah.
But computing actually does not refer, is not a channel. Doing computing is not actually a channel. So it's a bit difficult for me to conceive how to use the stuff that you deploy for computing within information theory that has to deal with transmission.
Okay, thank you. Thanks, Nikos. The question is that Nikos doesn't see very much the channel issue within the computing. By channel, what we mean is the actual hardware implementation, okay? In communications, like, well, you are accustomed to deal with communication systems, and we have this view of something that is spatially very broad. So you have a transmission medium, you have your equipment, and this is not really, this is a long range in many cases, no? Some meters or whatever. By channel, to what I am referring is to the actual physical implementation. It can be a nano channel, but nevertheless introduce noise and undesired effects. This is what I wanted to say.
I had a comment or maybe a question about your table of comparison, maybe a slide before. If I take the point of view of a theoretical computer scientist, what I would say is what is important from that abstract point of view is how many resources I need in one model to reproduce the computation, what I can do in another model. And in that context, well, digital computation, you can imitate analog computation just with overhead, given that, for instance, there's 10-bit precision you're using. Neuromorphic computing also is classical. There can be an issue with parallel computing, and quantum computing, people believe that the classical resources you need are going to grow exponentially because you can't reproduce the tensor product there. So I think that that's a basic difference which you haven't highlighted here. And of course, then there can be questions of efficiency. Maybe I can go faster with this technology or that one, but that'll gain you a few orders of, say, a few orders of magnitude, but not a scaling difference. So what is your comment about that?
Okay, that's a very good question. You're absolutely right. That's why I said it would be a little bit like controversial. This, in a way, I don't like to call it a comparison table, because it's not. What we try to do here is list things that we thought that could be done and that could not be easily done without, like you said, paying attention to the resources. The fact that you can do things doesn't mean that that would be the most efficient approach. And that's the statement. You're absolutely right. So I don't, like, for example, yeah, well, we don't have the scale of our systems to probably in analog photonic computing. We could emulate digital computing, of course, but just the very basic operations, we will not be able to do memory and that. But on the other hand, I don't think that, for example, doing analog computing, broadband analog computing would be especially easy with electronics, for example, with digital. If you want to go really on a high bandwidth, then you start having problems with your electronics. You have to do a piecewise design because some of your electronics will need to be scaled up. If you want to go into the, let's say, RF region or you say microwave region, I don't think that would be fairly easy to do with a compact digital electronic circuit. But yes, you're right. What I was trying to say here is, for example, and the other thing is that you could probably do reverse computation with digital electronics, of course, but then you would need to design your gates in a slightly different way. You would have to provide a second output port, so you could retrieve the that's what I was intending to do, not more. But we can discuss that later, yeah.
I have a question. The way I see it from your presentation and also from the paper, there's still a mix between certain analog concepts and digital concepts, or continuous, and also a mix between continuous and discrete things. Your system still has a clock, right? It's still discrete time-based. Is that what differentiates it from signal processing, in your opinion, or is it, or is this something that could evolve into a continuous time-based computing system?
Okay, the key is, let me go back. It's here. And the API. That's the part where you do the mapping between the information and the units. The units are like information containers. Okay, like the 0 and the 1s. We call them information units, but they are not units like kilograms. You know, they don't have the same. So basically, when we talk about this, we are thinking about information containers. So it's a 0, and using strings of 0 and 1s, we do mappings between our originator source and the information that we want to convey through these containers. Okay. Yeah, the pulses are, the amplitude and the phase do transport. In the amplitude and the phase is where the mapping has been done. Like, for example, consider when you are filtering a signal, for example, in the waveguide mesh, okay, you implement, but you are not processing a unit of information. You're just processing a wave.
Yeah.
Probably we can shift in the next Yeah, because we're already 10 minutes delayed. I don't know. Lorenzo, please take the last.
A very short question. So you say that all your gates are linear gates, isn't it?
Yes.
So why don't you consider also nonlinearity, which is going to be a dramatic difference with respect to quantum computation, where you have linear transformation, while here, so you can have gain, losses, and nonlinear effect as well.
You can do it. I didn't have time to comment today, but you can do it because you can develop your operators and use this series expansion. Then you will not have a matrix theory, of course, but it can be done, yes. But so I didn't have time to comment. But there are some discussions in the archive paper that you can find.
Okay, I think we have many of us have many questions on this talk, but let's save time for the dinner today.
Sure,
so let's thank the speaker again, and I would like now to invite Wim with his presentation on scaling challenges for programmable photonic circuits.
Okay.
I will find for you just to save time. Here.
All right. Thank you. Good. So I'm, like Jose already introduced, I'm going to give a bit more details on programmable photonics. I'm not going to go into neuromorphic computing at all, so sorry. But all the tools that you see here do have an impact on how you can implement these neuromorphic photonic circuits and the choices you need to make on a technology basis. So we all know what photonic circuits are about. You basically have all kinds of photonic functions on a chip, typically light sources, modulators, wavelength filtering, photodetectors, interfaces to fiber, etc. And as you also already know, probably well enough, photonic circuits are becoming increasingly more complex. We see a scaling law of photonic circuits. And you can compare it with the scaling of electronic circuits, with the distinction that we are probably a few decades behind in integration density, and that the scaling mechanism that allows us to go to dense integration is completely different from the one in electronics. What basically powered Moore's law and scaling of transistors for many decades, now it's the recent 2 decades is a bit different, but basically the original scaling was very simple. You take a transistor cross-section, you scale all the dimensions with the same number and basically the threshold voltage, and you have a transistor that works exactly the same way. So as long as your fabrication technology can make it smaller, you can basically keep exactly the same function for your transistor. In photonics, that's not really the case. In photonics, your scaling of your waveguide is entirely determined by the index contrast, which means that if you want to make a waveguide much smaller, you need different materials. So every scaling operation in photonics would essentially require a new material system. So that's actually the nice thing. We came originally from like first waveguide circuits were in silica, glass, were essentially kind of a fiber on a chip. And now we are at silicon on insulator, which is roughly as far as you can push it without involving metals. But it basically allowed us to scale waveguides from a 10 micron diameter to, when we went to 3.5 materials, to like 1 or 2 micron diameter, to now sub-micrometer diameter, like a mode size that's a few hundred nanometers in diameter. And that's great. And that's entirely enabled by the use of silicon, because silicon has a very high refractive index and the surrounding oxide has a much lower refractive index. And the nice thing about silicon is that this feature, this high index contrast, is one of the key enablers that created the field of silicon photonics. The fact that you have these small waveguides gives you an enormous scale advantage. You can make many more circuit elements on the same area of a chip. The second scale advantage that you got with the field of silicon photonics which is what all the investors were really interested in, is, wow, you can do this with the same technology infrastructure as electronics. So you can use a CMOS fab to make your photonic circuits. So this is really the two key scaling enablers for, or have been the two key scaling enablers for photonics, at least for the past 2 decades. On one hand, you had large-scale manufacturing. You now do see commercial products in silicon photonics that are made in CMOS fabs. And at the same time, your large-scale integration, the fact that your waveguides can be much, much smaller. So that means that you can take essentially the same circuit, take it from silica, like a glass-based material system, all the way to silicon and insulator, and you basically reduce the footprint by a factor of 10,000, so 4 orders of magnitude. And that allowed us to also scale in another dimension. You can go from a very simple circuit where everything is predefined. You basically have all the connections predefined, all the coupling coefficients predefined, to circuits which become a bit larger, but a lot of elements are now tunable. For instance, you have a tunable filter. And then you start integrating multiple light paths, and you integrate switching components on the chip so that you can do multiple functions on the same circuit. And then over the past 10 years, we now saw these, like these feed-forward interferometric circuits, these multi-path interferometers, where you now can control the path of light from a set of inputs to a set of outputs almost arbitrarily, because everything can now become tunable. You have all these tunable elements that allow your light paths to basically be reconfigured. And then finally, I think if you go to the most generic architectures, are these, what also Jose showed earlier, these kind of recirculating programmable photonic meshes, where your light is no longer propagating from left to right or from inputs to outputs, but basically can be reconfigured to propagate between any ports in the system and also like through multiple paths in the system. And then you get these kind of hexagonal meshes which have been seen for the last 10 years now. So, but with all these elements, that means your circuits become larger. So now we basically are entering the area of what you could call very large-scale integration for photonics. And indeed, if you look at the timeline, you do see a kind of a Moore's law for silicon photonics in terms of number of building blocks, number of optical elements that you see on a single chip. So we're approaching the 1 million optical elements on a single chip. That's quite impressive. That's the 1 million number for a square centimeter is probably as far as you can push it actually with silicon photonics. You might go maybe 1 order of magnitude higher, but without going to new materials, without going to a higher index contrast, I don't know how. This is probably the integration density limit, like per square centimeter. So this is something to think about. What are we going to do with the scaling capability that we have now? And we aren't using it to the full extent because there's a lot of challenges. And that I'm going to cover in a minute. So this is just some example of one of these larger chips. This is actually not a silicon photonics chip. This is silicon nitride based, so it's a bit larger. It's a 20-mode interferometer, so kind of one of these large waveguide meshes where you propagate from left to right. And the key building block that enables this kind of programmable circuits, these large-scale circuits, this is actually the building block that also Jose introduced. You could call it a 2x2 optical gate, or a 2x2 basic tunable unit. There's a number of names being posed here. What is inside of this is essentially phase shifters and tunable couplers. And as most of you probably already know, you can actually build a tunable coupler with phase shifters if you use a Mach-Zehnder interferometer. So you need good phase shifters. And this is a key block to actually enable scaling, because this kind of tunable passive building block is what you will probably need hundreds or thousands or 10,000s of if you want to make a large-scale photonic circuit. So that means you need really good elements. And this is one primary scaling challenge. For these circuits, you need gates with a low loss, because your light has to go through tens or hundreds of these. Low electrical power consumption. For the same reason, you have too many gates on the chip. If each consumes a kilowatt, then you have a problem. Preferably driven with CMOS-compatible drive voltages. You'd like it to be fast, megahertz, gigahertz for reconfiguration. And also no crosstalk. So if two gates are sitting side by side, they don't influence one another because you're driving one, the other doesn't change. And this is not the full list of requirements because this is the list what you need if you want to make a forward propagating mesh. If you want to make one of these recirculating meshes where you can do switching, splitting, but also make filters, you want these gates to be also very short. And I'm going to explain in a second. Basically, the gates that you use for a forward propagating mesh or a recirculating mesh are the same, but if you want to use them in a recirculating mesh to make filters, then you basically have a requirement on the free spectral range. The shorter you can make these gates, the wider the bandwidth or the free spectral range of your filter. So if you want to make a Mach-Zehnder, there's a minimum delay length that you can implement in a Mach-Zehnder, and that depends on the length of such a gate. And if you want to make a ring resonator, there's a minimum size of the ring, which depends on the length of the gate. So our wish list is not just a low optical loss, but also short optical length, and therefore also a small footprint, so you can stack them very close together. And if you want to make a really general purpose photonic circuit, you also need these gates to be compatible with the technology that is already there. Fast modulators, fast detectors, preferably also light sources. So how to make these gates? What are the options on the table? Well, there's a lot of research going on. Essentially, we want a very low power phase shifter, a very compact low power phase shifter. And the standard way of doing that is heaters, but there's many other options. And if you put them a bit on a scale, like how fast these are and how strong these different effects are, then you see that actually the strongest effects tend to be the slowest, and the weakest effects tend to be the fastest. So there's already an inherent trade-off. If we want gigahertz speed effects, we're probably going to end up with basically a heater or a phase shifter that is much larger than if we want a megahertz or a kilohertz effect. So what is on the table? Heaters, yeah, very easy to make. I mean, it's the most simple device to make. You just put a resistor on top of a waveguide. You do some undercutting so to basically make sure that the heat doesn't leak out. So that's a bit of a complication if it's integrated with the rest of silicon photonics. But the main drawback of a heater is that it's just hot. I mean, so you get thermal crosstalk and you're constantly burning power. And if you want to scale this to 10,000 devices on a chip, this is maybe not the best idea. So what else? In silicon photonics, we have carriers. They're already widely used for making fast modulators. So they give you a phase shift, but they do have quite a high optical loss. So it's okay if you want to do fast modulation and so a one-time pass through a device. You have a few dB of loss. You can live with that in a transmission link. You don't want to go through hundreds of these. And typically, they're also fairly long. So they're off the table for the kind of function that we're looking at. Phase change materials, very, very promising. Can have a very strong effect, and I guess we're going to see some of that later in this workshop in the coming days. They can be very compact, very low power, essentially zero static power consumption. They only need power to reconfigure. Most of these devices tend to be lossy in one of the two states, although that is now changing with the new antimonide selenide compounds. And there's also the question of like how much aging effects do they have? How accurate can you control them in an analog way? Like how many states can you configure, hysteresis effects? But very, very promising and really thing to look out for in terms of enabling scaling density. But not yet in a point that I think we can reliably put it in silicon photonics together with everything else and have it work as a baseline material. Maybe in 5 years, I'm looking forward to that. There's piezo, like essentially just applying stress in your material. Quite popular in silicon nitride, but it's a very weak effect. So you need very, very long phase shifters. So off the table for what we want. Pockels effect, that's an interesting one, because it can be a quite good effect. It's super fast. You just need to engineer your Pockels-based materials into your photonic circuit, like lithium niobate, barium titanate, or some polymers. And you need to be able to integrate to basically apply a very strong field over it. And then you have, again, all these materials also do tend to have some nonlinear elements in their response curve, so also the control and the long-term use is still a question mark. And then what else? Liquid crystals. It's a bit like Pockels effect, but it's much slower and much, much stronger because you have these molecules that reorient themselves. They're liquid, which poses its own questions. Like I want to do large-scale integration. I want a chip with hundreds of these or thousands of these wells which have a little bit of liquid in them. How will that live over time? But okay, we all use liquid crystal displays in our portable devices. So it's a technology that, on the other hand, is already quite well known. And then the last one, and I'm going to go in a bit more detail on those, is MEMS, movable devices. This is a very interesting proposition. MEMS is also a quite stable technology. You have MEMS devices in your smartphone. But the MEMS that if you want to integrate MEMS with waveguides, it comes with its own set of problems. And okay, you want to also integrate it with the rest of the silicon photonics. But it's a very strong effect because you're moving essentially silicon around. So you're changing the environment of the waveguide as having air to silicon. That's about as strong as you can get. Now, how would it work? I'm going to give a bit more detail here. You basically have a waveguide, and then next to the waveguide, you have a thin silicon beam. And you can do that above the waveguide, you can do it next to the waveguide. There's different ways to implement that. But you do need a mechanism to move that little beam of silicon around. So in this case, this is suspended on a set of folded springs. You have a shuttle that can move horizontally, and then a comb drive that essentially can pull the shuttle away from the waveguide. And that's a very strong effect. You do need a fairly high voltage to make it work. So in this case, this is simulation. It predicts like a 30-volt actuation voltage for a pi phase shift for this particular device. Turns out that after fabrication, the device performs a bit better, so we get a pi phase shift at 20 volt. But that's over a length of only 50 microns. So it starts to come close to what we actually want from our type of devices. And the nice thing is that you can also very easily in MEMS devices do a tunable coupler by essentially just taking two waveguides close together. They form a directional coupler. And then if you pull them apart, they're basically two isolated waveguides. So very, very elegant way of implementing a tunable coupler and a phase shifter. Now, you can integrate these MEMS devices into silicon photonics. So that's actually what we did in the Formake project and the Morphic project. So you can combine them into circuits. And you see in this case, the unit cell of one of these programmable photonic circuits. So you have three tunable couplers, three phase shifters. And then they're connected together in a much larger waveguide mesh so that you can actually do this routing of light and you can implement these filters. It's not all that easy. The MEMS devices tend to collapse mechanically. So the waveguide just falls down and sticks to the substrate. And they're exposed to air, which makes them fragile. So you do need some protection mechanism, for instance. And what we're doing is we basically do a wafer bonding. We put a silicon lid on top of every individual MEMS device so that you basically have these sealed areas. So this is a better picture. These sealed areas on a chip, you see these like table-like lids sitting on top of the MEMS devices. And you still have access to your metal bond pads and your grating couplers. So that allows you to basically do further packaging and integration of these devices in a larger system. So MEMS devices is quite promising. And we're still working on that in the Formake project, which is a follow-up of the Morphic project, to basically build these large-scale circuits. Now, having a good gate, and we're not yet there, there's no technology that really ticks all these boxes already perfectly. MEMS devices tend to be relatively slow, for instance. But you don't need just good gates, you need to be able to integrate thousands of them on a chip and to control all of them. So all of these gates need electrical interfaces, need software, need control loops. So which means that for every phase shifter, every tunable coupler, you need something like a digital to analog converter or something that performs a similar function to tune them continuously, which means that you basically have to have that many electrical connections going off chip to connect to your electronics. So you need the electronics and you need the packaging. And then typically you need also a feedback loop. You basically need detectors on your chip. You need analog readout. You need control loops, which can be in analog or digital electronics or even in software. So, and all of that needs to work together. And typically, because this is an interferometric structure, the optimum operating point, or if you go to the landscape of performance, it's typically a landscape with lots, like a 1,000-dimensional optimization landscape with all local optima. So finding in that global space, finding the best control point is not easy. So that means that you do need to think about that from the start. If you make an architecture like this, like a mesh, where do you basically do your readout? Where do you monitor what is going on in the mesh? And how do you feed that back into your actuation? And monitoring is in itself just a big question. I mean, if you just look at one single node, there's lots of places where you can put a detector, but a detector obviously introduces a bit of loss and a bit of space, and you need to read it out. And then there's still the question like, okay, you can put a detector, but it only monitors amplitude. If you want to monitor phase, you need to come up with additional, maybe detectors and additional readout schemes. So you cannot afford this typically. So you need to make strategic choices in your scaling, like where do I put my detectors? Where do I put my monitors? And your whole control strategy needs to be based around those choices. So it's a bit of a chicken and egg problem. You can't just make a chip and then think about the control. You need to think about the control while you're thinking about the size of your chip. And that's just at the lowest level. On top of that, you need to, in a programmable circuit, think about your configuration algorithms and essentially your system control as well. So detecting whether a device has failed and rerouting everything around that failed device, for instance, is one of the type of control schemes that you need at a system level. The electronics integration itself is a challenge. In the future, I think one of the most common ways to implement these photonic electronic together is going to be flip chip. You're going to have a photonic chip, you're going to have a custom ASIC to drive the photonic chip. For anything that is large volume fabrication, that's the very logical approach to go. For experiments, that's way too expensive to design a custom electronics chip for every photonic chip you make. So going to packaging-based approaches is, I think, really important for the coming decade to allow us to explore these larger scale systems. And so just to give you an idea of what we're talking about, so I showed you this picture. So it's part of a larger circuit. The circuit actually contains 700 actuators, 200 photodetectors. So these need to be brought to the outside world in a packaging approach because we're not making a custom electronic IC here. They need to be brought out in a packaging approach. And we came up with this like large-scale grid with 3,000 connectors, 3,000 electrical interfaces where you can possibly place a bond pad. You don't have to use all of them, but you use the ones that you want. And together with Tyndall, we designed a standard interposer that could be used for any chip that has that same grid, that uses pads on those grid locations, can be used with that interposer. And it's a non-trivial thing. It's probably one of the largest fan-out interposers in the world. It fans out these 3,300 connectors. It also has 24 high-speed fan-outs for modulators and detectors. And it basically breaks that out from 20 by 20 millimeter footprint to about 10 by 10 centimeter. So you have the chip sitting on one side. You see the high-speed tracks at the top. And then on the back side, on the same scale, you have these groups of 200 connectors which fit to a standard package, a standard high-density connector. But you can also use them for direct flip chip, direct solder bumping on a printed circuit board. So this interposer is very expensive, but it allows you to take a chip that just uses that same grid, fan it out, and then basically at the bottom what you have is a printed circuit board, which is a cheap technology. So you have that one mass-produced expensive interposer, but because it's in large volumes, it's relatively cheap. And then it's matched with a cheap printed circuit board. That, for instance, in this case, you have those almost 1,000 connectors wired out, and then you basically connect them to a modular set of driver boards. Each driver board matching with 64 channels, driving 64 channels, and having 32 readout channels. So that's the hardware part. On the software part, there's a bit of questions. You, of course, need to also program these devices. So you need software layers. We have a software framework that matches chip layout to mesh logical connections to circuit simulations to the hardware. That's kind of nice. But in the end, if you want to make that really useful, it has to turn into something like you can download. If you buy an FPGA off the shelf, you just download the design kit or the development kit and you start programming. And so you need this kind of development environment for people to do it. And that needs to include configuration algorithms, for instance, ways to do routing, like mesh, graph representations of your mesh that allows you to do routing algorithms, distribution algorithms, for instance. So to make this work, this large scaling for programmable photonics, but actually large scaling for photonics in general, you have to think really beyond just making a photonic chip or making the phase shifter. That gate is important. That gate is super important, that we can get that smaller and lower power, but we also need to make sure that it matches in scale with the photonics, the electronics, the software, and the packaging. So you have an entire technology stack that needs to be completed before you can really scale up to these very large-scale circuits. Now, with that idea, if we can make one of these chips, do we then have one chip to make everything work? Well, in a way, yes. You have an FPGA for photonics. You can buy it, you can program it. But at the same time, it's still going to be a large chip. It's going to be expensive. These general purpose chips still will have a higher loss than a dedicated chip and a higher power consumption. Now, with that being said, how much time do I have left? A couple of minutes. Okay, I want to say a few words on the other side of the scaling then. That's the large-scale manufacturing, just to put something in perspective. What we call large-scale is maybe not exactly that. And just to give you an idea, let's take a 200 millimeter fab, an electronics fab. That's typically an old fab. That's nothing compared to what TSMC is, most advanced fabs is. But this is the typical fab that is being used to make photonics today. So let's say that we want to use such a fab to make photonics. What is the capacity of that fab? If we're looking at chips of like a half square centimeter, such a fab can churn out on the order of 30, 40 million chips per month. That is, for the fab, a very profitable business if it can do that. Now, what is the market? 2021, the only, and today still, the only volume market for photonics is transceivers. So what is the market for transceivers in 2021 was 11 million transceivers. That's 2 weeks of work for the fab, and the rest of the time it's twiddling its fingers. So that's not a very profitable thing. But okay, what happens in the future? Well, even if you do an optimistic projection for 2025, you will just barely fill that fab. That's okay. Fab is happy, except there are, at this point, 10 commercial silicon photonics fabs in the world, or 10 fabs, commercial fabs that have developed a silicon photonics platform. So it's still a mismatch. Another way to compare it, if a fab can do 60,000 wafers in a month, an electronics fab, that's roughly all the silicon photonics wafers that have been fabricated in 2021. So in 1 month, the fab could do all the silicon photonics for the entire year for the whole world. Again, most of that was actually, about half of that was R&D. People developing LiDARs and neuromorphic computing and all the fun stuff that everyone likes to do and publish was not even a product. So that's just way too low. So we need to step away from the whole idea that photonic chips should only be used for communication. It's just as stupid as saying that electronic chips should also only be used for calculators. We know what electronic chips are used for. I mean, you have Tamagotchis and Furbies and whatever, dishwashers, all kinds of things which might not actually need an electronics chip, but we put them in there anyway. So we need to come up with basically useless applications of photonics so we can create volume for those fabs. Now there's actually tons of applications. The optics market is huge. So if you just look at bulk optics, or anything, the total optics markets, it's larger than the electronics markets. So there's a lot of potential to basically put that on a chip. But that means that we need to actually think of like, what is the bottleneck? Why haven't people been selling smoke detectors with silicon photonics in it? I mean, these things are being published, they're just not being sold. And one of the key reasons, in my opinion, is that if you have an idea, I want to turn it into a chip, it's taking me too much time. The biggest problem is time. Because you have to design, fabricate, package, test a chip, and the technology is not yet good enough that you get it right the first time. And probably not even the second or third time. It takes you 4 or 5 iterations because before you have a prototype that can convince a customer. And each of those costs a lot of money. And a 5-year runway is not something that you typically have as a startup in this field. Investors are not that patient, except for quantum. So we need that same model as in electronics where we have an FPGA, you buy, you program, you test, and you demonstrate in a week, a few weeks, a few months. So basically cutting that fabrication, that costly fabrication cycle, at least out of the initial stages of your development. So turning that 1-year turnaround time for your photonic chip into a 1-day turnaround time. And this is important, and it's important for all fields of photonics. You want to be able to iterate faster, to demonstrate things faster. So you need something that is programmable. You need something that you buy, you program. And that's the kind of technology that also Ipronics is developing and actually already has a device on the market that puts a really important first step in that direction for these rapid iteration cycles. So this is necessary to scale. It's not just a technology scaling. We need to fill these fabs. We need to come up with new applications that fill these fabs, because otherwise, 5 years from now, a lot of these foundries are going to think like, it's not worth it, and shut down their platforms. And then we're all lost, because our research is also running on those platforms. So we need these lower development costs, these shorter time to market. And the nice thing about programmable photonics is that it scales also well in time, because you can provide software upgrades. We now already are familiar with our cars that get over-the-air updates and stuff like that. So your phone gets constantly updated. So it gives you a longer lifetime. But most important, it puts photonics, and this is very important, it puts photonics in the hands of people who don't know what light is. Basically, electronics engineers, software engineers. And that community is 100 and 10,000 times larger, respectively, as the community of photonic nerds. So we want those people to use photonics as well. We want them to innovate, because there's a lot of ideas there. And with that, I would like to conclude. I mean, this is a kind of a, I probably used the word neuromorphic a few times, but I was not talking about neuromorphic photonic, but it impacts this field a lot, because it's building on a technology that allows the scaling. So with that, I want to conclude. So scaling photonics is not just about the technology. Of course, you do need that really perfect phase shifter. We're really waiting for that. I think a lot of people in the room would love to have that, and probably a lot of people in the room also have ideas and technologies that are going a long way towards that phase shifter. But it's also the scale of the circuits and the scale of the market that is important. And if we don't address all of those at the same time, at some point we're going to hit the wall. And with that, if there's any questions, feel free to ask.
Thanks a lot, Wim. We have time for 2 questions, no more, because the time is already... Yes, give it to Volker first. Yeah.
Yeah, so like awesome, like very good stuff. So now, just I think what's great, maybe like one comment and question. So it was great that you showed actually what is really possible with state of the art right now in silicon photonics, and then also certainly packaging and integration. So I think so like big thumbs up, like great lead. Question on the chip that you did show. I think I noticed like 3,000 DC connectors and just a handful, like 2 times 12 or something like this RF connectors, right? So I guess what you're saying is you're having your high, you have a basically like 24, like one-dimensional input vector of, let's say 24 lines or so at high speed, and then the updatability, that one is really, really slow, right? Now, I'm talking these days a lot with like electronics folks, and they basically, if you run some, I don't know, like I'm sure you ran some numbers, what's the really use case for this? Because are we actually better with this? Because I really doubt that we were anywhere getting close to what you can do in FPGA. Performance-wise, from the actual system. So amazing technology, but is it anywhere competitive?
It's a good question. So the use case, I think, falls much under what Jose called signal processing. So your fast lines are your input and output signals, and then you configure your processor to do filtering or whatever, or to basically perform its function. But that configuration is, on the time scale of the signals, is static. That's, in a way, that's a constraint imposed by the fact that we don't have infinite money. Because if I could do whatever I wanted, I would probably have an ASIC sitting on top of my photonics with short electrical connections between the driver ASIC and the photonics, and then I could drive it faster, but then I also still need a fast phase shifter. So I need one of those phase shifters that ticks all the boxes, including gigahertz configuration speed, which is not trivial. You can have that, but then it doesn't tick some other boxes.
So basically, if we had that, you could make the refrigeration layer also at gigahertz, and then it would be indeed the whole system, also not just data processing. Of course, I can program it, and I can filter some whatever signal, hyperspectral filter, whatever at the edge, right, and forget it. I can always. So I think that's what you have right now. And if you had that amazing phase shifter, you can even do the reconfiguration at that fast number, right?
Yeah. So if you have that phase shifter, and if you have the money to do the ASIC driving, and you solve all the packaging problems of having like thousands of high-speed connections, and the thermal problem because everything is now sitting together. So it's a package. I mean, the problem, it's all integrated. So also your problems are integrated. It's not just your functionality. You have to solve all the problems at the same time.
They're entangled there.
And yeah, quantum packaging.
Okay, Jose. Yeah.
Okay, thank you. My question is a little bit more qualitative, maybe a forecast. There are really two questions in one. First is what is your impression about how many gates would we be able to integrate in a standard chip in, let's say, in 2 years' time? And with that, if that number would be enough, or because you know what happened with the FPGAs. People went mad by scaling up with a lot of units, and it turned out that at the end of the day, you don't need so many. So if you have a guess about that.
Okay, so there's both the technology push and the application pull here. How many gates do you need for typical functions? I guess actually for at least what people can come up with in terms of ideas at the moment, you're probably okay with like 100 or 200, between 100 and 200 gates. We'll probably be able to do most of the small scale ideas that people can come up with. The problem is that once you give people a tool like that, and the smart people a tool like that, they come up with lots of things that you haven't thought of. And that typically is going to involve like, okay, instead of 2 input channels with high-speed signals, I want 50. And then you want the commensurate number of gates to increase as well. From the technology side, bottom up, there the question is like how low loss can you make your gate? Because if your gate has a certain loss, that means you can only cascade so many of those in series, and that limits the size of your chip, your mesh. So technologically, yes, we can put 3,000 gates on a chip. That's possible. But I mean, then basically you have the perfect attenuator, which is maybe not what you want. I do think that we'll probably see, and it's an interesting case to think about, if you can get your fiber interfaces sufficiently low loss, then you will be able to cascade these systems or these chips in a larger mesh And so the loss on each individual block is manageable, but then if you want more complex functionality, you might be able to go off chip to the next one and basically have a kind of multi-chip solution. As long as you don't require exact path length control between two of these cores, then you can have fiber links between them. So that might be an intermediate solution where you have the benefit of relatively small cores, so the transit from, let's say, one side to the other is manageable. But if you really want large-scale functions, you can still cascade them. That's my thought.
Thank you. Thank you.
Okay. Although you have the acoustic noise, you have multiple devices with fibers, but let's not discuss that now. We can discuss it.
You could embed everything like glued, fixed, etc. in the package.
It's not so easy, I think.
It's not so easy, but it might be an intermediate solution.
Yeah, of course. Okay, thanks again, Wim. And the last speaker is Francesco Daros from DTU. He's going to talk about data-driven gray box modeling of MZI meshes.
I think you had it already open. Yes. Thanks. All right. Good morning, everybody. So, first of all, thanks to Adonis, Karis, and Nikos for putting all of this together and getting us in this nice and not so hot room. And also, thanks a lot for putting me as, right after these two excellent talks. So, setting the bar very high. All right. So, what I want to talk about here is something that goes a bit more into the neuromorphic side, but it still plays a little bit in the programmable photonics sort of field. So, maybe trying to branch into the next sessions. So, I mean, as we all know, when we try to do neuromorphic photonics or some sort of optical machine learning type of hardware, well, what we really want to benefit from is the fact that, we need massive interconnections, and that is where photonics can help us. Because, we don't need to deal with metal wiring, we can rely on lower loss, parallelization, WDM, and so on and so forth. So we can sort of trying to, at least in a, sort of shorter term span, use photonics in terms of accelerators and so on, and that has been a lot of work on that, as we all know, in terms of optical neural networks, reservoir computing. I mean, basically what everybody in this room is working on and has demonstrated. So what I'll focus a little bit on here is maybe more the side of photonic accelerators, so where we basically try to implement all these interconnections with an optical circuit and do the matrix multiplication on a photonic layer. Now, if we want to do that, as we also heard from Jose and Wim, I mean, we can use elements with phase shifters. So those can be Mach-Zehnder type of interferometers. They can be micro-ring resonators. Depending on the group, there's slightly different preferences. They all have advantages and disadvantages. But what it comes down to at the end is that, yes, we can build a network, but as I'm very happy that Wim brought this point up, then we need to train and control the network. And I'll not go into the level of detail or the upper layer as Wim started discussing, but just in the very close to the hardware side, when we want to optimize the weights or optimize these interconnections, well, there we can take mainly two approaches. We can rely on offline training, but then we need very accurate models of our PECs, but gain the advantage of potentially a faster configurability, because then we can get it almost instantaneously from our model. And we can do online training. But then we might need more monitoring ports in the PEC. It needs to be a bit more PEC specifics, and it's an iterative process where then reconfigurability takes a little bit more time. So for this talk, I'll focus more on the offline training part. And if we start talking about the offline training and the modeling part, then we need to start dealing with some of the sort of more neglected effects in a way which are the more complex to deal with. So effects such as optical crosstalk, thermal crosstalk, electrical crosstalk, and depending on the technology in which you implement the phase shifters, of course, you might have different relevance of the various ones. But if we stick with heater-based type of phase shifters, well, there has been some earlier works from Jose's group where they started looking at the thermal crosstalk on microring resonators, and the reason why I really like this graph is that is as a function of the distance between the elements, and the distance between the elements obviously plays a key role when we try to increase the number of devices in a certain footprint. So that automatically shows that, yes, we do have some problems to address. And then the question that we wanted to try to answer is, well, can we still use simple model when we have to address these type of questions? So this brings me to the outline. So what I'll discuss here is a number of strategies that we have tried to compare with modeling these type of PECs. So starting with Mach-Zehnder meshes, so just 2x2 interferometers, and also trying to not only compare methods, but also trying to relate then modeling performance to accuracy on certain tasks, and then addressing some of the challenges such as data scarcity if we want a model based on experimental measurements. And then I'll give you another example where we move closer to programmable photonics, so some work that we did in collaboration with Ipronics on looking at the thermal crosstalk in these programmable meshes and how we can compensate it. I mean, the nice thing, or the thing I mostly like about thermal crosstalk is that it's a deterministic effect, so we can actually do things about it. So I'll go very quickly on this. We all know how Mach-Zehnder interferometer meshes work. So we apply some voltages. If we have thermal optic phase shifters, we all know how that applied voltage is related to the change of phase and so on. So in principle, if we have just an interferometer, it's very simple to learn the mapping from my applied voltage to the weight that I am applying with this interferometer. However, then we start packaging more and more interferometers one next to the other, and then all of a sudden, well, it might not be that simple because a voltage not applied to an interferometer in my path all of a sudden start mattering. So what can we do about that? Well, we can start by doing the somewhat lazy approach and see if we can get away with it. So I'll just ignore it. So I'll just do my modeling in the somewhat usual way, so very much based on physics, where I just include some fitting of the loss and the extinction ratio, this Mach-Zehnder, and I just include the Mach-Zehnders that are on the path. So in the specific case shown there, from input 1 to output 2, and I start playing with the voltage, so I just sweep the voltage applied to the first interferometer. I can get pretty decent fit. So the blue dot are measurements, can fit my model, there's nothing too complicated about that. But then I do something slightly different, and I start playing with voltage 2. Voltage 2 doesn't matter because it's not applied on my path. However, well, the measurements don't agree with that statement. So voltage 2, that interferometer is quite close to the previous one, so it starts creating an effect on what I'm seeing. So, okay, can we do something about that? Well, still sticking very much to the physics. Well, we can do what also a lot of groups are doing, such as MIT and so on, which is to add some phenomenological terms, so some corrective terms, using the voltages applied to well, pretty much all the Mach-Zehnders in my mesh. And then I can get a pretty decent fit. Now, here I'm still sweeping just one voltage at a time, so that's relatively simple. But what I really want to do is when I have complete random voltages applied throughout my circuit. And well, if I do that, then I might want to try also a bit more of a, let's say, black box or gray box in the specific. I'll get to that approach where I pretty much just train a neural network type of model to learn the mapping between my applied voltages and the weights I'm applying from the circuit. And well, I'm going to try to be at least a little bit smart and use some of the physics. So, I mean, I know that there's a dependence on the voltage squares. So maybe that's better not forget about that. So try to keep a little bit of the physics knowledge into the throwing a machine learning approach to it. So I call it that sort of gray boxing type of thing. And the reason for also liking to use a neural network type of model is that, well, in general, what we want to use those models for is when we want to model things efficiently, or we want to model things that are not very easy to represent with the physics. And, well, thermal crosstalk, we know the physics of it, but it's not an extremely simple model, especially if we have a complicated circuit. And on top of that, we can train these neural network models very easily from experimental data. And finally, if I want to optimize this model, well, everything is differentiable. I just apply, you know, simple gradient descent through it. Everybody knows how to do that, so it's very straightforward. So we wanted to compare these models, and we did that basically on measurements based on a 3x3 Mach-Zehnder mesh structure. It's a 3x3 just because of the chip we had available. Very much looking forward to scale this up. But then we build up some data sets by either sweeping one voltage individually or just having random voltages and then measuring the transmission through the chip. And now, without getting into too much details for the sake of time, I mean, here I'm comparing the error distribution between what we predict of weights on a testing set and the weights that we actually measured. And as you can see, I'm comparing these three models, and there is a clear improvement by adding the crosstalk in the simple model. That's not surprising. But when we try to go further and have this gray box neural network type of model, what we really improve on, and well, you can see the mouse, but is the outlier part. So, I mean, the variance does not improve too much. The RMSE does go quite down. I want to point out something maybe slightly not obvious at first glance. The x-axis is non-linear in this plot, just for the sake of visual clarity. So of course, things stretch out a lot more if you go on a linear scale. So the take-home message here is that obviously the more you manage to capture the effect of thermal crosstalk, the better your model is. The nice thing about neural network models is that then you can start going beyond the signal frequency model, which becomes a bit more challenging with more physically rooted type of modeling. So we can, for example, model the behavior of the chip at 10 different frequencies in a sort of not so smart way, which is just cascading 10 neural networks trained at each frequency. Or we can, again, consider that, well, we expect that there is some correlation in frequencies, so neighboring frequencies are maybe going to have a slightly closer behavior and so on. So then having a bit of a more evolved type network where we start using a convolutional layer can help us with capturing these correlations. And overall, what we see is that they all perform quite well. So the dash baseline is the single frequency, and then the models, they sort of have an error that increases a little bit with the number of frequencies I'm trying to model. This is not a modeling problem, this is a measurement problem, because of course, if I consider a sort of single frequency or a single band type of approach, I'm also averaging off a little bit of the measurement noise because I'm integrating over a slightly broader bandwidth, so the more finer resolution I want is just, so this is nothing really fundamental with the modeling, is we could improve our measurement setup to address that. But overall, we can get pretty good models, mainly limited by the measurement accuracy. We can also relate this type of modeling error to then the bit precision that we expect to obtain by using a network trained with this model. And we can see that with the neural network type models, we can get around 5 or so bits of bit precision. Now, just for the sake of clarity, that there's sort of slightly different flavors of how bit precision is normally defined. We are using the 3 sigma. If one uses 1 sigma, it's just a slight rescaling, right? You can go a little bit beyond just considering the achievable bit precision and test it on actual tasks. So, of course, we have a 3x3 network, which means we are a little bit limited on which task we can choose. So we chose a couple of toy tasks to just get a feeling for how things relate. So the first one is a 3-bit XOR task, where we emulate the input matrix as the optical matrix accelerator, where we add the noise on the weights according to the PDFs that I've just shown. And the activation function and so on is on a digital level, so without actually adding noise. And what we can see is that we can get pretty decent accuracy. We have a little bit of outliers for the neural networks, which go below 100% accuracy, but the average is pretty close to 100%. So this seems to work quite well, which also hints that maybe a 5-bit precision for this simple task is not that bad. We can go more into a regression type of task, where now we are doing Gaussian regression. Well, now it's the testing RMSE, so it's the opposite type of picture, but the results are pretty much the same. So also for this task, we get pretty good testing RMSE for the size of the network that we have. So as long as we do take thermal crosstalk into account, then we can get off with implementing a task quite reasonably. If we don't, we do get quite significant penalty. That's what you get from the more or less simpler models, where you either ignore the crosstalk, or even if you add it just as a fitting element, it doesn't work as well. Now, that's all nice and good, but neural network models are something that does require training data, a lot more than if you are fitting just the more analytical type of model with a lot lower parameters. So how do we deal with that? I mean, having a lot of measurements is not very scalable to bigger meshes and so on. So what we looked at is how the training and testing error evolves with the training set size for the simple model with the crosstalk, or the simpler neural network model, so the single wavelength one. And as you can see, there's just for this simple circuit 3x3, that there's a factor 3 roughly scaling in size of the data set that we need. So that's not too positive. However, what you can do is you can apply techniques such as transfer learning. So what we proposed is to basically use the simpler but less accurate model. We fit that on a smaller set of measurements, and then we use that to generate a huge synthetic data set. So just numerically, that's a lot easier to generate, right? I mean, it's not a complicated model. The computing power required for this is very little. And then we pre-train our network based on this synthetic data set. And only after we do some retraining of not the whole model, just a few layers, so the standard transfer learning type of thing, with the experimental data, and which means the same experimental data that we have used for fitting the simpler model. So we don't need extra measurements. And the thing that we see is that the testing RMSE, well, it's still not that bad by using this approach. So what you see here is on the leftmost side, the neural network trained on the full measurement data set that we had available, so making sure that it had converged and so on. And then you can see when we start doing the training of that on a 10% of that data set, roughly, and we get hit by a huge, I'd say, modeling error. But that's not the same for the simpler model. So we can use the simpler model to generate this data, and that's what is shown as the 2TL box plots, where we then use 400 measurement points to train the simple model to generate the synthetic data set for our neural network pre-training. And with 400 or 1,000, I mean, we are only maybe a factor less than 2 or a small percentage off compared to using the full data set. And that saves a lot of measurement time, also because when we have this peaks, I mean, measurement is not only really measurement time. I mean, we need to ensure stability and so on. So depending on how the peaks are packaged, there might be some challenges in that. Okay, now I'll go very briefly, because I see Adonis looking at the clock, into another example. So now we are going to switch from a standard 2x2 interferometer to the hexagonal meshes, which I will not introduce because both Jose and Wim did a great job at that. So this is based on a collaboration with Ipronics, so it's based on their programmable photonics technology. So in this case, of course, things have been optimized very carefully to address thermal crosstalk already. But if we start looking at somewhat very demanding type of applications, so now we have built a ring resonator, so that's the colored pucks that you see up there. And so that's a small ring resonator, and then we look at how the resonance frequency of that ring resonation shifts as we increase the voltage that we are applying to all the neighboring pucks. So in the perspective of maybe we want to use the rest of the area of the chip to implement other type of functions. And of course, if we apply heat to the other pucks, then there's heat transfer to our ring, and what we see is that the resonance frequency shifts. So, and that is again also for a chip where things were very carefully designed. So can we do something about this? And given that the shift is not that big, what we are trying here is simpler approaches to address that. So what we tried is, first of all, just doing a simple linear regression where we are trying to map the shift as a linear fit with the amount of phase that we are applying or the amount of power that we are applying to the chip. We can do a little bit more evolved modeling where we also take into account that not all the power that we apply affects the shift the same way. Of course, there is a direct relation with the distance between where we apply the power and where we measure it, basically. Or we can try to basically fit completely where we just have a scaling coefficient for all the phases. So if we start with the linear regression, that works quite nicely. Actually, we get pretty decent RMSE. I mean, you clearly see a very, very linear trend. If you use this model where we start taking into account the distance of where we apply things and then have a few more fitting parameters, so this is basically a 4 fitting parameters type of model, so it's extremely easy to train with just a few hundred measurements or so. And it also works quite well, and it gives us the extra advantage that since it's a little bit more physics-based, where we can also start extrapolating some trends beyond what we measured, and I'll show you that that is actually something very helpful. And then we can use the more evolved model with a bit more degrees of freedom, so now we're talking 67 degrees of freedom, where we do a full fitting. And now the error gets a little bit lower, of course, because we have more degrees of freedom. Now, okay, we can model this, but then the goal is really, well, to use this model. So that's what we did. We went back to the chip, same ring, all the phase shifters tuned to all the other phase shifters tuned to the maximum phase, and we see that the spectrum is indeed shifted, as I've shown you in the earlier plot. But then we try to apply a compensation based on the 3 different models. And, well, given that the modeling error of all 3 of them is really low, well, we see that basically the conclusion is that all 3 of them work. That's no surprise there. Then we went a little bit further and tried to see, okay, if instead of using the model that I've trained on that specific ring, well, what if I have a model trained on the ring next to it or on another place in the chip? And now I'm just going to use the one next to it just for time constraints. We have tried with different rings throughout the mesh. Well, the nice thing about it is that if we use the model where you take into account the distance, then it's very easy to remap it and use symmetry considerations to then effectively compensate the crosstalk. And this, to me, is another good way to try to address the challenge of, need for data for these models. Because the moment I can use all these symmetry arguments, then I don't really need to model the full chip. I can just model a small part of it and then extend it. And that seems to work really well, at least for the testing that we have been doing so far. So that's another way to sort of provide some arguments for how we scale these compensation models and so on. So that's more or less what I wanted to discuss here. I can also leave the conclusions up. I'd like to thank Ali and Isidora, the 2 students who did a lot of the modeling work in this, and I'll be happy to discuss things.
Thanks, Francesco. We are out of time, but at least 2 questions can be okay.
One question from my side. It's interesting that you can use a different ring in the same chip in order to extrapolate this behavior. Can you do the same with a different chip? So if you have done the same measurement for a single chip, if you have another chip from the same iteration, then wouldn't the model fit? Have you done some experiment like this?
Well, the main limitation there is to get access to the chips. So I think I'll have to talk to Jose about that. But I mean, to be honest, we have done some. So we haven't tried to map the model exactly, but at least we have had access to some measurements from another chip. And at least in terms of the relation here, in terms of linear regression, I mean, the slopes are pretty similar. Of course, depending on where the ring is, this model does not work as well as the other one, because if you have a very edged ring, then you also have a lot further elements, which then skew a little bit the slope of your simple linear regression. But again, that's exactly fixable the moment you take the distance into account.
So a question about the stationary approach that you are using, because here you are essentially assuming that everything has thermalized, right? While the transient is in thermal crosstalk is really important if we want to exploit also the temporal response of the device. So how do you implement this transient?
Yeah, yes, that's a very good point. So we have not looked at transients here. I mean, the whole goal here was to be very much in a steady state point, because the goal was to have something, some more deterministic and slower type of compensation. Of course, if you wanted to do faster tuning, which I guess in the specific chips that we have been using was not really that possible with the speed of the thermal elements and wiring that we had access to. I mean, in principle, it's still a deterministic effect, right? I mean, if you have control over the timescales of what gets applied, I mean, I don't see why you shouldn't be able to compensate for that. The model becomes more evolved because you need to take the time dimension into it, but I mean, even from a neural network perspective, that is doable. I mean, we know how to predict time series, and this would not be very different from a time series prediction, I would suspect.
Okay, I think we can now go for a coffee break. Thanks again, Francesco, and to all speakers of this session. So, even if the coffee break was originally scheduled for 30 minutes, let's make it 20 minutes in order to compensate a little bit for the delay. Thanks.
Okay, I think probably we can start the second session of this workshop. It is a pleasure to have today Kathy Lüdke. She's a professor at Limmenau in Germany. So, Kathy.
Yeah, thank you very much.
No.
Okay, now it's working. Okay, then I will start again and thank the organizers for inviting me and be part of this workshop. And what I'm going to talk about today is related to the timescales that we can add to the readout or to the input in time multiplexed reservoir computing. And the research has been done at TU Ilmenau, where I'm now together with my postdoc, Lina Haurige. And my outline, what I'm going to talk about, is structured like that. So first I want to talk about a bit more in general about this delay-based reservoir computing and Tarkin's embedding and the timescales and how those things are related. And then I want to present some methods how to augmentally add memory to a reservoir that hasn't got this memory yet. So how to easily change hardware implementation of a reservoir to make it suitable for a certain task, and then I will present the results, how this adding of the memory improves the results. And we already heard in the morning session, I was actually very impressed how you can do that in photonics already, how to do these deep neural networks, but my motivation is always, well, it's very hard to do these deep neural networks because you have to train all of those connections in order to get this mapping between input and output. So what I'm concentrating on is this reservoir computing approach, where you actually don't tune the inner connections of your network, but you use a physical system that has a certain degree of nonlinearity, a certain degree of memory, and you just exploit what is there to do your neuromorphic computing, your training. And since I'm from this nonlinear laser dynamics business, my goal is to use an optical system like a laser for these reservoir computing applications. Today, it's not even really a laser, it's just one semiconductor optical amplifier that is used with a feedback loop, but we come to that later. So if we first introduce this time multiplexed reservoir computing, it's the one highlighted in white here. And on the right, we have the normal implementation, this spatially multiplexing. It's basically working the same way, you just exchange time with space. So instead of just sampling different nodes in space and then adjusting the output connections, you sample at different points in time and sample those intensities if you talk about an optical system, and you write all your responses into a state matrix, you do this training. And for the reservoir computing, the good thing is that the training, what you actually have to do to determine the weights, this W out matrix, is just a linear regression matrix inversion basically. So here in this state matrix, you have all your intensities that you detected in your time multiplex system, and this O with the head is supposed to be the target. So of course we need some kind of task that we want to solve, and in my talk I will concentrate on these time series prediction tasks. So what we want to use this system for is to predict some time evolution. Can be, of course, some artificially created data, like what makes it easier in computation. We use this Lorentz 63 task. It's the Lorentz equation, it has chaotic dynamics, and we want to predict always the next step. But it is meant to be used also in applications, for some edge applications where really the evolution of a dynamical system is supposed to be learned. So it's not limited to this task. And one important thing here for the task is that in order to predict, for instance, this Lorentz task, you already see it has some characteristic time scales. You shift between these butterfly arms on a certain time scale. And if you want to teach this reservoir to predict this dynamics, it would be good to have the time scales that you need here in included in your system. And different tasks will also have different memory. So for instance, you have the Lorentz equations. These are 3 differential equations in x, y, and z. And if you give it the x component, so you put in the x component into your system, and you want to predict the future of this evolution, it's a different task as putting in the x variable and predicting the z coordinates. So for the last one, much more memory is needed, because in order to get the z evolution, you need much more memory. And this comes down also to the point of whether you feed in the full information or the partial information into your system. So there has been already just some recent research on that if you have a differential equation that describes your system and you feed all the points into your reservoir, either in time or in space, and then all the system needs to learn is the next integration step, which is, of course, much easier and much less memory requirement is there than if you just feed one variable and all the others have to be included indirectly via the memory. And that also changes these memory requirements with the discretization, and that's something I also want to talk about. So if you have your Lorentz time series, for instance, and the way you feed in the data, you first have to sample, so which points you feed in. And there are also some recent research that I want to just, no, the first one is not recent, but the last one is recent, which I want to mention, that these time steps is not always the smaller the better, but there are also some rules that can make it easier. And for that, I just to show that I have this Mackie Glass task here to show what I mean with discretization. So this is the time series of the Mackie Glass. It's given by the time delay equation. It's a chaotic dynamics, but by inspecting it, we already see there are some characteristic oscillations which are not regular, but still there's some memory on this time scale. And if we now look at this time series and we sample with a time step of 1, then of course with 100 time steps we just get a short part of the time series, but we get all the details. But if we sample with 12, for instance, we sample a lot of points in the past. We don't get all the details, but still it's much easier to reconstruct the chaotic attractor, which is related to Tarkin's embedding theory. And for that, I have this picture here of this paper by Marquez and al. In 2019. It's plotted the autocorrelation function of this Mackie Glass task. So this is this line here. And this autocorrelation function has a zero crossing at a time lag of 12, which means if we sample with these orange dots with this 12 time distance, then all the different points that we sample, they are not correlated. So the correlation function is 0 there. So we get the most of the information out of it. While when we sample very close to each other, then every points are correlated. And by sampling them all, we have redundant information into our system. So we have to keep that in mind. If we have a task, we need to know, is this information that I feed in redundant or uncorrelated? Okay, so now I can start with the setup I want to investigate. So we know we want to do a reservoir computing. We have to keep an eye on the task we want to solve. And what I show here is now a possible way of adding additional memory to our system. So here I just put a nonlinearity. It can be everything, can be a laser. In my case, it's an amplifier, or could also be a different system. The important part is we have a feedback delay section here, which is called N. So whatever comes out, if it's light, it's fed back into our system. And then the information, the time series we want to predict, that comes here from the left. And we need to multiply a mask when we have this time multiplexed reservoir computing, so we get another index J, and we have an input scaling factor that we multiply the thing with. And then we have these 2 additional delay lines in the input and the output that I want to focus on later on. But first, we stick to this internal feedback delay, and to the system I'm actually modeling here. So The state of my dynamical system is given here. It's an x variable with a discretization time I. It's an iterative map, so there is no internal dynamics in our system. So usually we look at these lasers and we care about the internal timescales. In this case, it's very simplified. It's just a map. So there's just an amplifier that is given by this nonlinearity G. So we have this like a tangent nonlinearity. And then we have this feedback loop. The only thing we have to care about here, it's a map, but we have these two indices. We have the indice of the map, so every input of my Lorentz or my Mackey-Glass time series is now also sampled in between, which is the index j, and then the total input is indexed by k, so this I is the number of virtual nodes times k plus j. So just to keep that in mind, that we have a certain number of virtual nodes, which refers to the number of spatial nodes in a spatially multiplexed network, and that is fed into our system. So if we look if this time delay makes any difference for the performance, I plot here the normalized root mean square error. So I did the training to predict the next time step, and then I determined the normalized deviation from the target. This is plotted here on the left, and on the right is the feedback delay. And what you see is when the feedback delay has the same size as the sampling inside the mask, the performance is actually not very good. But then if I get longer and longer, there seems to be an optimum, and then there are all these little resonances in the middle. And if we zoom in here, because that's very squished together, so we zoom in, we see all these resonances again, which always appear when this delay time, the external delay time, is an integer multiple of the sampling number of the mask steps. And if I zoom in even further, I see at these integer multiples, I always have a peak, and if I go one next to it, then I get quite good performance, which is by a factor of 10 better if I use this relation here. So my delay is 8 times larger than the rate at which I feed in the data for this Lorentz cross prediction task. So that's the first thing, how I can change the memory and the nonlinearity of my setup by just tuning this delay that I use for my reservoir computer. And I will talk about optimal delay when we use this adjusted delay value. And the default delay is what people usually use for these maps, that you just take one step longer, so that you have like a ring coupling, you intermix your virtual nodes within your cavity. That is called the default delay, which is not working quite optimal. We see it here, it would be here, and we can get much better. Okay, so that was the first, this feedback delay, just to explain the system. And now the central point of the talk is how to change the performance by adding this additional delay line. So experimentally, a very simple step, much easier than what was talked about in the morning session. So it's just another delay line. So we take the same input and feed it in twice, but one is delayed by this number ny input delay. And the other one is also very simple. I put a delay line at the output, so whatever comes out, I store for some time. I take both into my state matrix. This is the state matrix. One row is always sampled within one mask step, and then I take one from the past and put it next to it, and then I go to the next input. So very simple to realize. And as we will see, all these methods lead to a strong improvement of the performance. So as an example here for the Mackey-Glass system, 12-step ahead prediction, if we tune this output delay, we also see here an optimal value that would be good to use for this task. This is the feedback delay, again tuned, but this time we always went just next to these resonances. So all these resonances now disappeared because the delay time is always n-1 divided by s. And for the internal delay, sorry, the delay now goes up and down here, but we also see dark values are very good performance, and we also reach them here at about a level of 10 delayed steps, and we can choose our optimal values for these output, input, or for the feedback delay, and always end up with more or less the same performance. And what is also already indicated here with this input delay is the second parameter, because when we have this delay loop in the beginning, in the entrance of our input, we have to scale that, and this is the input scaling here. And we see usually it depends a lot on this input scaling, but when we hit the right delay, then the dependence is not that strong anymore. And if we characterize that a bit further, which is basically the parameter sensitivity. So the problem with reservoir computing is always the hyperparameter tuning. So you have your reservoir, somehow you have to choose all the parameters. And what I want to focus on today is if we add these external or internal delay, this hyperparameter dependence is more or less lost, because all what is important for your reservoir is that it has the right timescales, and if you get it to the reservoir externally, you don't have to care so much how to tune the reservoir to the right parameters, and this is shown here. So these are two parameters of our reservoir, the input scaling of the non-delayed version and the feedback strength, how we feed it back. And it's for the default delay, so more or less the same delay time and clock cycle for 10 nodes or 250 nodes. So of course, from top to bottom, the performance increases a lot, but what you see, it also depends a lot on these hyperparameters. And now these three columns that are supposed to appear in a second are these three ways to optimize the performance: the input delay, the output delay, or the best feedback delay. And what we see is that this parameter dependence disappears. So now we get a good performance over the whole parameter range, both for the input delay. Also for the output delay, we reach a more or less similar best performance value, and also for the optimal internal delay, which told us, well, I just need to include the right memory for the task that I'm investigating, and then the parameter dependence gets much less worse. And all these pictures we can just plot in one graph. So this is the best performance that I found in this two-dimensional grid search. And again, for the default setup, which didn't work that well, for the optimal internal delay and the output delay, and what is expected with the virtual node number, this decreases. This is the zoom for very large number of nodes, and then we see here, in this case, the optimal internal delay even wins. So for this task, the best was to optimize the internal delay. And also the parameter dependence is shown here with this quantity P01, which basically tells us how much green there was in this picture. So how many areas with good performance below 0.1, how many points did we find? And there we see that this output delay was performing the best in view of this hyperparameter dependence. And now one last thing I want to focus on. So first was adding this delay is very beneficial wherever we put it. Now I started in the beginning with this discretization. So now let's look at this Mackie Glass time series again and change this discretization step. We just have to keep in mind that the number of steps I predict into the future, it's time series prediction. So if I do a one step ahead prediction for a discretization of 12, I would predict this red dot here, which is my target. If I do a much smaller discretization, that would be a 12-step ahead prediction with a discretization of 1. So we have to keep that in mind, that our task, so what we want to predict, is given in units of this discretization. So just as an example here, oh yeah, I already said that. So this is a 12-step ahead prediction for the discretization of delta t equals 1. And I can do the same with the same delay in physical units and the same prediction in the units of the time series, but then it's a 1-step ahead prediction with another discretization. So what I want to say, changing this discretization changes my task, and also changing this number of step ahead predictions. So I could also predict a different step here and would have a different task. And this is done in this plot. So for now, we let the discretization step constant, and we change the predicted step. So we want to predict more and more into the future on the x. And on the y-axis, we chose a different, we tuned the delay at the output. And what we see is this good performance, the sweet spot we found before. Is that the timer? No. The sweet spot we found before that shifts with the task. So you can't say for this reservoir a certain output delay is beneficial, but you always have to know what you want to do with the reservoir. So for each task, you would need a different optimal delay. And something I wrote here is, for this simulations, we even put the feedback, the internal feedback delay to 0. So this is an extreme learning machine. So there's no dynamics because it's just the amplifier. There's no coupling because the feedback is off. So no memory in the system whatsoever unless we put the output delay. So we see with this, only with this output delay, we can already improve the performance. And this works, of course, much better when we have the delay in the system. So now the delay is back on. We have a reservoir computer, not an extreme learning machine. The performance is, of course, much better, but still we see that the output delay makes the story better. But if we already have the best internal delay, so if we did our job in optimizing the internal delay, we don't need the external delay additionally. So you just need to implement that once. So I think my time is up, so I will speed a bit to this last graph where we try to take the same target. So we always compare here targets where the product between discretization and step ahead prediction is the same. So we always predict the same step, but with different discretizations. And then you see, for this case, the optimal value of the external delay shifts to smaller delays, but this is given in units of the discretization step. So basically always the same delay here is needed. But also for these other two cases, for the default feedback and for the feedback delay, we see, let's focus on the right part here. We had optimized that for the 12-step ahead prediction. If we now change the discretization, it's not the optimal feedback delay anymore. So if we optimized our feedback for one discretization, this will change if we go to another task. Okay, so with that, I want to conclude. I hope I convinced you that if we focus on this reservoir computing and we want to optimize that, we always have to keep in mind that every task has different memory requirements. And for a reservoir that is universally working, we would need some reservoir where we can tune the memory externally. And there we presented these three methods with input, output delay, or internal delay. And of course, I need to acknowledge the group. I'm also looking for a PhD student, but I think everyone here is. Yeah, and I want to thank you for your attention.
Thank you for the nice presentation. I think we have a lot of time for questions. So, any questions?
Thanks, Kathy, for this nice talk. Just a question that always is in my mind when we discuss about this reservoir computing. Does your reservoir node
nodes in general, let's say for a specific task, can define the memory you need? Or the memory is independent from the node you use?
What do you mean, can it find? I mean, it has to be...
We have different types of, let's say, reservoir computing architectures, or with a laser, or with a,
yeah.
Let's say, in space, etc. There are different schemes we have seen in the literature. For a specific task, is memory bound on the reservoir node you use, or it is independent from that?
The memory that your reservoir has is bound to the reservoir, but as that was what I tried to say, that if your memory is not enough what your reservoir has, like if you use some frequency space, multiplexed reservoir, also water bucket or whatever, if there is not the memory you need, you just need to add this input or output delay.
Yeah, I understand that, yeah.
And that you can have it. So you're not requiring to have the best reservoir for all the applications. You can choose a reservoir that is best suited for the application. So if you think of edge computing, so you have some optical problem you want to solve, you just take what's easiest to implement there, and you just have to make sure that you input the time scales that you need.
So you believe that the memory is what you, I mean, it's independent from what you are going to use as a nonlinear node there?
The nonlinear node is not that important, but of course this time scale somewhere it has to be either in the node or in the input or at the output. You have to put it somewhere.
Okay, thanks.
I have one question as well. You demonstrated that you have, for the Mackay glass, for example, that you have to find an optimum feedback for your cavity in order to get the proper memory that you need. And you said that this is 5 times the sampling rate minus 1. So these oscillations do not provide the same performance. So the typical one is the sampling rate plus 1. Mm-hmm. But you demonstrated that you need 5 times this or 8 times this. Is there a physical explanation why we need 5 times the sampling rate and not 7 times, for example? Why this dependency?
This is related to the specific task. So for the Mackay glass, that's because of these oscillations that have a certain internal dynamics. So depending on the discretization you use, you need you need to hit some points in the past. So if you make the feedback delay longer, then if it's 5 times as long as the input, then the input of 5 times in the past will meet its friend after 5 round trips. And that is beneficial for the Mackay glass task. For the Lorentz task, it's a different delay that you need. So it's very specific to the properties of the task.
So is there any practical technique that you can have, let's say, an application or a general task that you can first identify this time scale and then adjust the feedback?
Not that, I mean, we tried it with the autocorrelation function, so you get this zero crossing, but then again, that depends on the discretization so much that it's not helping you. And in another project, we also looked at the series expansion of the task. So you can use that and then look at the nonlinear transformations that the task needs. But still, there's no easy way. We just saw here it depends a lot on the task, but how to really do the mapping. I have this task, I now use this delay, we couldn't solve so far.
Let's thank our speaker for an excellent talk. And now I think it's the time for Serge Massar from, my French pronunciation is terrible, it's from the Université Libre de Bruxelles. Good, okay.
Oh no, I just wanted to open, oh this one is broken. Okay. You can choose yours.
I uploaded it just a few minutes ago on your website.
Maybe you refresh it. I don't know.
Let us check.
Copy it, or?
Otherwise, I can put my computer if you... No.
I don't have it as well.
You've got a stick, USB stick there?
Fortunate for us, Kathy provided a 5 minutes buffer from her talk, so we'll be okay.
But I need to take out the... Okay.
Connection from the other side.
There's the key here.
So it's one free USB port here.
Here, there's please. Remove that.
Okay, no, I put this. Probably it's working.
This one.
This one?
Yeah.
Okay.
Okay.
So you're good to go.
Yes. How do I go from one slide to the next?
You just press
Okay.
key, probably.
Okay. Sorry for that little glitch. So, well, thanks again for inviting me and for organizing this nice workshop on this exciting topic. And so I'll be talking about neuromorphic computing and trying to see how we can exploit the frequency domain to do neuromorphic computing. So I'll very quickly sketch the kind of algorithms I want to look at, and then some ideas about doing neuromorphic computing in photonics, just to introduce the tools I'll need. And then two realizations we did. One, basically an extreme learning machine, a very shallow network, and the second, reservoir computing. In the first case, I also show how we can use the Kerr nonlinearity, and also in the second case, how we can build deep reservoirs. So as Cathy sketched, I mean, the workhorse of neural networks are these deep neural networks where you train all the parameters in the network. To have a reasonable training scheme, you need to use feed-forward networks. And so these are very powerful. It can be scaled to huge sizes, but they're certainly difficult to implement in physical systems. And so we're going to look at very simple architectures, but where we can explore what we can do with physical implementations. And the first is just a single layer feed-forward network where we're going to use also randomized connections given by the physics of the system we're using and only train the output weights. And so in this case, well, we've got these fixed internal weights which are random, so we can hope that our physical implementation will behave more or less like a typical random system and give performance, a reasonable performance. And because we only train the output weights, we can do this with linear regression, as Cathy pointed out, and get easy training of the system. The other algorithm I'll use is the one Cathy talked about, of this reservoir computing, where we've got our input going into this dynamical system with recurrent connections, and then we train the output weights. And again, because the system, we can implement this in software with randomized systems, we can hope that our experimental system, many experimental systems will work well. These systems have memory about past input, so they're good for processing time series. And again, the trained output weights, we only train the output weights, so training is easy. Just to sketch, well, we're working with photonics, which at least has the potential for very high speed, a potential for parallelism. This is actually what a main reason for exploiting this frequency degree of freedom. But certainly compared to electronics, photonics has a very high footprint because you're limited by the wavelength of light, and the technology is much less mature. Many of these things were said in the first talks today. But these constraints also force you to try to think out of the box and to try to develop new schemes, which I think is quite interesting. So to go first to parallelism, the most natural way to try to exploit parallelism in optics is with spatial parallelism, where you use multiple spatial modes which basically can cross each other without speaking to each other. And this is a scheme of a reservoir computer done by the group of Sylvain Guigan and Lighton which exploits about 50,000 spatial modes. You've got this spatial light modulator at the bottom, you've got this camera, information is diffused on this kind of diffuser, so it's a kind of linear optic scheme, and you see that you can use huge number of modes in spatial mode. We'll see that in frequency we're much more limited, but okay, we have to think a bit differently. The other idea I want to introduce before going to the systems I'll talk about is the idea of using passive coherent systems as information processing devices. So this idea was introduced independently many times. One nice theoretical paper is by Grigorieva and Ortega, who discussed basically a reservoir computer which is linear. As you can see in this equation here, you've got the input u and then the internal variables x, and this is a linear system, but then you build a polynomial in your variables xi and train the coefficients of this polynomial as your output. And this, they show, provides a powerful way. This was a theory paper of doing computation, and an experimental implementation was first done by the group of Peter Binsman using this recurrent optical network, and then you measure the power of the individual nodes. So the variables inside of the amplitudes of the electric field, they interfere, but you measure their norm squared. So this is you get a polynomial of second degree as output. Some time ago, we did an experiment, a reservoir computing experiment, was basically implementing this, which gave quite good performance on a number of tasks. I won't go into it in more detail, but basically at the top right, you've got the output photodiode, which converts the electric field amplitudes, which have been interfering in the system, into intensities. So now I'll switch to information, well, using frequency multiplexing to process information. And so basically the idea is that we're going to use a frequency comb. So as sketched at the top there, do you have a pointer or no? Anyway, at the top here, you've got the frequency comb where you've got a central frequency, small omega, and a comb spacing given by big omega, and the amplitudes of this comb, AK, are the variables you're going to manipulate. And then how do we create and manipulate these frequency combs? Well, the tool we use, but you can imagine others, and that would be quite interesting, is using phase modulation. So we drive a phase modulator with frequency big omega, which typically will be, for instance, 20 gigahertz, as sketched on the right here. And so this gives a phase e to the im cosine big omega t. You can do the Fourier transform of this, and it gives some coefficients in terms of Bessel functions. The exact values are not important. And with our devices, we can make combs with about 25 usable spectral lines. So we're going to be using networks with about 25 nodes, which is not a lot, but still enough to do some demonstrations. So let's go to the extreme learning machine scheme. And how does it look like? Well, at the left, we've got our laser, monochromatic laser, and we've got a phase modulator, which we drive with our RF source, big omega. And so this creates a frequency comb. And then we want to encode the information we want to process in this frequency comb, and we do this with a programmable spectral filter, which will change the amplitudes of each comb line depending on the data we want to process. And then we mix this data with a second phase modulator. And finally, we're going to do a readout. The simplest readout would be to read out each spectral line separately, but we can also, as I'll explain, implement the readout in an analog way. So if we want to look at the spectra, this is a sketch of what's happening. At the left, we've got our monochromatic laser. After the first phase modulator, we've created our comb. And then we've got in green down there the input, which is some series of attenuations, which we apply, and this modifies the comb into the comb E in. And then this COOM, which contains the the information we want to process, gets mixed by the phase modulator. And now we've got our COOM we want to read out, and we're going to read out the intensities of each COOM line. So we could do this, and we do this sometimes, by measuring each COOM line separately with a filter which we scan, and we measure the powers in each COOM line. But we can also apply weights with another spectral filter on each of the COOM lines. And here what we do is we separate the weights which, the COOM lines which we want positive weights go to photodiode 1, and the COOM lines we want negative weights go to photodiode 2. The photodiodes are going to register because they integrate over a long time, the total power in that part of the COOM lines that they receive. So they're going to give, photodiode 1 is going to give the sum of all the COOM lines with positive weights and their powers, photodiode 2, all the COOM lines with what we want to be negative weights and their powers, and then we take the difference. So we can implement quite simply a readout scheme like this. Some results for this system. These are, again, simple classification tasks because we don't have many nodes. The famous iris classification introduced by Fisher something like 100 years ago, and some other databases. And in blue, you've got the results with this optical weighting scheme, which I described before. In red, what happens if we measure each COOM line separately and then do the linear combination afterwards. And in yellow, results of simulations of the device. And we see that the optical scheme generally performs similar to the other scheme, so this works quite well. And the horizontal axis is that often these databases are small dimensional. For instance, the iris classification is three-dimensional database. Well, 3 dimensions, 3 values, which you want to, three-dimensional database. And so we can multiply this several times to affect multiple COOM lines with the same input value, and these are these values of D, which sometimes improve performance a bit. So another experiment we recently did on this same basis is instead of using a phase modulator to mix the information, we tried to use the Kerr nonlinearity. So what we did is we amplified our input power to basically half a watt, and then passed this through 500 meters of optical fiber, and then did the readout. So, then we ended up having quite a bit of difficulty interpreting these results, because it turns out, as I'll show you, that basically the EDFA does enough. It also has some nonlinearity, and it does enough nonlinear mixing for the tasks we want to do, and the fiber afterwards, even though it adds more nonlinearity, but it doesn't help for the information processing. And it took us quite some time to figure this out, and we're still writing up the paper. So these are some results on different classification tasks within blue and red, again, digital weighting, optical weighting, different ways of doing just measuring the outputs. But the different columns are, on the left, the amplifier plus the single mode fiber, in the middle, the amplifier alone, and on the right, comparison with a software extreme learning machine with the same number of parameters. And basically, you see that the left column and the middle column have more or less the same performance, showing that adding this single mode fiber doesn't change much. And we can confirm this in simulation. Here on the right, what we've done is the blue curve is the accumulated nonlinear phase. So the integral from 0 to propagation distance L of gamma times the power. And while you're in the amplifier, the power is increasing basically exponentially. So the integrated phase is increasing very fast. And then we get into the single mode fiber, and there the integrated phase just increases linearly. So these are, and then what we have done in orange is to measure the performance on 2 different tasks as a function of propagation distance. Well, these are simulation results, obviously, but you see that you need a certain amount of nonlinearity, but not very much, because the vertical axis is in milliradian, so we get something like 20 milliradian of nonlinear phase, and then suddenly we have enough nonlinearity to improve the performance on the tasks, and then this kind of saturates. So this maybe requires, is interesting. It shows that at least for some tasks and some applications, you actually need quite little nonlinearity
to do interesting things in photonics. One idea we're developing for the moment is here you see one of the key elements we are using are these spectral filters, and we're developing an integrated version of such a spectral filter. This is a sketch of this device with a cascade of Mach-Zehnder modulators with well-computed delays, so that they, in the end, were able to apply weights on different spectral lines, on 16 spectral lines separated by 20 gigahertz. And, well, it's a thermal control. I mean, I think for the experts in integrated optics, this is rather standard stuff. But, okay, we hope to have a chip which we can use. For the moment, we've tested the chip, published the test results, but we haven't yet implemented it in our system. And so replace these commercial spectral filters by our custom chip. So let me pass to the second algorithm, which is reservoir computing, and how we can implement this in, with frequency multiplexing. And I'll first describe how we can do some computation with this. Many of the tools we have are already clear. So we've got a CW source, and we're going to encode our input with intensity modulator, and this will now, our input is time dependent at a rate which is defined by a cavity, as we'll see later. So we've got our time dependent input, which is modulating our monochromatic input. So we've got our monochromatic input, and its amplitude is going to change over time. This is the signal we want to process. Now, from this monochromatic input, we create a frequency comb by driving a phase modulator with this RF source. This gives us now a frequency comb whose overall amplitude is changing in time depending on the input. And then this goes into this cavity. There's the connection to the cavity is in the wrong sign. I mean, the PowerPoint always deforms this curve. Anyway, not very important. So the light is going around, and the light coming in and going along as the arrows are indicated. And inside the cavity, we mix the information again with a second phase modulator. And so we've got a new frequency comb in the cavity, which is changing over time. So, and the input time scale, the time scale over which the input is the same as the round trip time of the cavity. So each round trip time, we get a change in spectrum inside the cavity. And then what we do, well, we need an amplifier inside the cavity to compensate for losses. And we will measure the intensity of the comb lines of this spectrum. So each spectral line will be changing in time. We measure these intensities for different spectral lines, and we do a linear combination to create the output. And we can do this linear combination directly in the optical domain using the same trick I described before. We published this on applications on some tasks last year. What I'd like to discuss now is how we can extend this to doing, to couple several reservoirs together. So our aim is to do something like what has been called a deep reservoir computer, where you've got one reservoir whose output is fed into a second one, etc. And this can, at least on some tasks, improve performance. So we've got multiple reservoirs connected in series, and this enriches the dynamics, possibly gives you more information, so it can improve performance. And we'll implement this now in our optical system. So this is a sketch of the, so the first thing we'll do is we're going to use the same device here on the right, the same reservoir, to process two data series at the same time. So we're going to do parallel information. What we do is we use two sources at different wavelengths, 1550, 1555. We encode two different inputs using two intensity modulators, and then, well, everything is processed in parallel in the frequency domain in this device, and we can do two computations in parallel. So we've got two frequency combs, and we can do two information processing in parallel, or we can use it just to increase the dimensionality of the system by processing the same time series and reading out the output. So, well, we've got, just to re-sketch this, there were two inputs. They go through these two reservoirs, which are actually different because the reservoir performance is sensitive to the dispersion in the cavity, and so changing the central wavelength will change what is the interferences going on in this cavity. And then we take the intensities, we take linear combinations for one output, linear combinations for the second output, or else we could, if we're doing the same task, take the linear combination of all intensities to create one output. Now, what we'll do in our deep configuration is we're going to read out the data from one reservoir and from the other, and we're also going to couple the two reservoirs together. So the output, the data, the Coombe lines from one reservoir are used to drive the second reservoir, and we're going to collect all the information, information in the Coombe lines from the two Coombes in the reservoir and use this to compute the output. So a sketch, again, yeah, I'm just repeating what I just said. We're going to use one reservoir, use it to drive the second one, and to do this, we're going to apply our programmable spectral filter and attenuate the Coombe lines, use this to drive a photodiode, which drives the input of the second reservoir. And we're also going to train this attenuation mask. We're going to try to optimize it. We've tried different techniques, but optimizing it, of course, can improve performance. So how does this look in practice? This is the system you just saw. And what we're going to do is we're going to use our programmable spectral filter, use it to drive the output of that to drive a photodiode. So we've got positive weights driving, we're only using positive weights to drive this photodiode, and this drives this Mach-Zehnder modulator. We can also switch from one configuration to the other very simply by adapting the system. And so we tested this on some tasks. The one I'll just discuss here is this sort of artificial nonlinear channel equalization task, which Jaeger used more than 10 years ago, where you've got a channel with four symbols, and it goes through, is affected by nonlinearity, memory, noise, and you want to try to recover the original signal from the distorted signal. And if you use one reservoir or the other, you get, as a function of the vertical axis is the symbol error rate, so how much errors you want, lower is better. And the horizontal axis is the signal noise-to-noise ratio of the channel, so it's a parameter you can vary. High means that there's very little noise in the channel, and so you expect low symbol error rates. You see that the two reservoirs operating independently give approximately the same results, and but they're doing different computations. They don't talk to each other. And now if we use the deep reservoir configuration, well, and some regime of parameters here where we've got very little noise, we see a very significant improvement in performance. And if we use the two reservoirs independently and use their outputs together, we get something intermediate. So there's this deep reservoir computing scheme, well, can improve performance, and with this frequency multiplexing where we can implement this output layer in the analog domain quite easily, well, it leads to be able to implement this in a nice way. So, well, just to conclude, I've been talking about how we can try to use frequency multiplexing for neuromorphic computing. It's maybe a different way of thinking about things. I discussed this extreme learning machine. A weak kernel nonlinearity is sufficient. You can easily apply weights in the optical domain, and we're trying to move at least parts of the system into integrated versions. And the reservoir computer, where we could implement easily independent reservoirs, so we can do parallel computation on the system without the systems talking to each other, or we can use one to drive the other, and we get into a deep configuration. Well, deep is 2 layers here, but okay, it's a first step. The limitations of our system are that the processing speed is given by the round-trip time of our cavity, which is fiber optics based, so this gives about 20 megahertz, and the whole system has to be stabilized quite carefully. This was one of the big limitate problems which we had initially developing this. And of course, for the moment, we've got an electronic output. We're trying to see if we can devise a system where our output is in fact optical. And some perspectives, I would like to try to do more of these kind of more advanced information processing schemes. I think this is one of the fun things to explore. And then on the technical side, we could try to have better frequency comb sources and have more frequency comb lines. For instance, if we just covered the C-band at 20 gigahertz, we could have about 100 channels. We could increase the speed if our reservoir was integrated on a chip to maybe up to 10 gigahertz is probably possible. And then we can, try to optimize other parameters. And so just to finish, I'd like to thank all my collaborators on this, and especially Alessandro, who's the PhD student who's been really behind this, and he's the co-author on all the papers I've presented here.
Thank you very much for a very interesting talk. Any questions for Serge? Yeah?
Thanks for the very nice talk. I mean, this might be a little bit detailed question. We can also discuss it a bit more offline. But I was very interested on the EML scheme you showed and this fact that you get a lot more nonlinearities from the EDFA, and that's sufficient and so on. And I was just trying to understand a bit more experimentally what is happening in terms of maybe the pulses that you're sending in, and whether decreasing the power would sort of like the gain of the amplifier would then change the picture. I was a little bit surprised that you were getting this much nonlinearity from the EDFA, and it was interesting to see that was actually sufficient.
Yeah. So actually, we're working in CW. So the peak powers are the power, or half a watt. I mean, this is the CW power, and when we so one could go, of course, to much higher nonlinearities by sending pulses. There are a series of papers on this using, if you sent femtosecond pulses through a kind of system like this, you'd have completely different dynamics. Here, because the nonlinearities, as I showed in one of the next slides, actually are very small, you can do linear kind of perturbative analysis or perturbative integration of the nonlinear Schrödinger equation. And so you see that what's happening is that because there's a Kerr nonlinearity, each Coombe line amplitude gets a small contribution where it gets sums of, it gets contributions from products of 4 other Coombe line amplitudes. So it's like creating a kind of small 4th order polynomial in your system. And I think what happens is that once the amount of nonlinearity, the amount of this nonlinear mixing becomes sufficient to overcome your measurement noise, then you can exploit this in your linear combination. That is, if there's one like 4th order term, suppose there's one 4th order term or combination of 4th order terms which is really interesting for your task, you can, in your output linear combination, select this by putting adequate weights, but for that you need that the nonlinearity which is appearing is strong enough to be measured compared to your background measurement noise. And yeah, maybe if you, and then whether or not huge nonlinearities, there's some papers where they have these basically femtosecond pulses which undergo soliton fission and try to do the same kind of thing. Sure. And then, I don't know how it compare. I mean, I think it's an interesting area to explore how these nonlinearities affect performance and what you can do with them.
Yeah, just one tiny thing. I mean, when you say it's CW, I mean, I guess you're still modulating the data on it, right?
So in this extreme learning machine, we just, the spectral filter has a very slow update rate. So basically we fix this to some input. And then we measure And update rate is like a millisecond or something like that. So it's really very slow, and time scale, there's no time dependence here. Yeah. Contrary to the reservoir computing, where there everything changes in time.
Thanks.
Yeah, okay. Thank you for the nice talk. I had a question to the end, so I'm sorry. We should have switched the question. Where you have this deep reservoir computing, in the limit where you don't use the second reservoir, but just the feedback, it's more or less this output delay. So I was wondering, how much does the result depend on the delay? You feed it back, the first reservoir into the second, and does the coupling strength change the results a lot? I mean, you showed this large improvement. So did you need to tune a lot the parameters, or?
So just if we go back to the scheme of one reservoir here, okay, I can go back to the figures, but even if we just have one reservoir, we have some parameters, global parameters we adjust here, and one of them is the two we play with are the frequency of the Coombe source, but the most important one, which we can very easily change, is the RF frequency of our RF driving, because basically, because we've got this long cavity, dispersion plays a role, and so by changing the RF frequency, you can change whether, if you looked at each Coombe line separately, what is its accumulated phase is going to change in some complicated way across the Coombe. And so this is a parameter we can scan very carefully and check good operations. I think you were asking about timescales. I think that in the way we're using it, we do not, I think everything is, we adjust so that the readout is actually corresponds, we take combinations corresponding to the same time.
But when I was referring to the steep, you feed the first output of the first reservoir into the second reservoir.
Yeah.
So is there a delay? This arrow, this gray arrow.
So I think that the way when we take these outputs, I think we compensate, I believe that we've got, there's some delay between the output of reservoir 1 and reservoir 2, but I think that in the way we did it, we put the same delay before computing the output, so that we haven't tried to exploit delay times, which could be done and could possibly improve performance. So you could certainly play with this, but we haven't done that.
Thank you very much for the talk, very interesting. I have a question regarding your filtering stage, the one that you showed with this tree configuration.
I'll try to find this slide,
Okay. So from this, I guess that you want to separate, then you want to change the amplitude of each band, and then combine.
Yes.
Okay, is that correct?
Yes, so we've got a demultiplexer, which is what is blown out at the bottom. So it's a sequence of Mach-Zehnder unbalanced Mach-Zehnder interferometers. Okay. I didn't do the design, so I can't really talk about how it works. Then we attenuate selectively each channel, which is now a separate Coombe line, and then we go to remux everything. And what is drawn here at the top is basically, say you take one Coombe line, when we attenuate it, we attenuate that Coombe line, and what we've analyzed but is not on this graph is that there's very little crosstalk to other Coombe lines.
Okay, so my question is there any special reason why you choose a 20 gigahertz spacing?
No, so there's, at least in the way there's a kind of trade-off, which is that it would be easier to do this with 50 gigahertz spacing, because then everything just becomes smaller in scale. But then, if we want to create a Coombe with our phase modulators, which is the way we do it, we're limited by the frequency response of the phase modulators and our amplifiers, which is about 20, 25 gigahertz. So that's the fastest with our current system. We can we can create these Coombes and mix them with the phase modulators, The maximum spacing is around 20 gigahertz, and that's enough to make selective filters and look at specific lines. So there's a kind of sweet spot for us now, but you could imagine using a comb with 100 gigahertz spacing if you had another mechanism to mix, to create the comb and to mix the information in the comb, and then you could make all this more compact. On the other hand, there's an interesting trade-off is that if you think, suppose I'm covering all the C-band and the telecom wavelength, well then if I have increased the spacing of my comb lines, well I'm going to have less lines over my usable bandwidth. So there's, I think, a whole series of interesting trade-offs which, we've just started to explore.
Okay, thank you. Thanks. Okay, let's thank our speaker once again. And the final talk for this session will be provided by Antonio Hurtado from the University of Strathclyde.
I cannot find it, but we copied it before.
We are looking at the memory stick, so go there, go here, it's okay. It's here, this one.
All right, there you go.
Okay.
Okay, good morning everyone. Well, good afternoon already. Thank you very much, Haris, for the introduction, for the kind invitation to come here to Greece. So I'm coming all the way from Strathclyde, that's in Glasgow, in Scotland. And believe you me, it was a different temperature over there when I left. We had a maximum temperature of 17 degrees and a small drizzle. And I came here, it was almost 40, I don't even know. I all thought I was gonna melt in my way here. And although I'm originally from Spain, I think I'm already posterized or something, I don't know. I kind of lost my Spanish inner core. I'm struggling here. But anyway, it's wonderful to be here, so thank you very much indeed. Looking forward to seeing the city and enjoying talking to all of you. So I'm gonna change gear a bit. So it's brain-inspired computing as part of this session, but I'll be talking about spiking systems and how we can build spiking systems in photonics, and how we can even use them to build neurons and spiking neural networks, hopefully. So this is the idea, if you want, behind all this. Nowadays, computing systems are incredible, so I don't know. I don't really think I need much to introduce the topic here, but anyway, just this idea that computing systems are amazing at doing all these things that they do, and artificial intelligence, and you name it. But they come with a huge cost in terms of the power and energy that they require to operate. So that doesn't come for free, very, very fast, very incredible stuff, but very, very powerful, very power-hungry systems. But on the other side of this very simple graph, we've got the human brain, which, as we know, it's very powerful, allows us to do all these incredible things that we do without even noticing. But it operates at very small timescales compared to our computing systems, but remarkably, it does so at very, very small energies. So that is obviously fantastic. And the brain, it uses different mechanisms for computing, and one of them is spiking. So this signaling between neurons, these beautiful spiking signals that are a bit weird if you think well about it. It's not the first idea that would come to mind. But evolution has developed this wonderful thing, this kind of system, which is half analog and half digital, which is very resilient to noise and allows these very, very powerful operations. So the idea is, can we use photonics to try to get the best of our worlds? So can we have systems that can operate very, very fast and reduce the energy consumption in the systems? And hopefully, can we draw inspiration from the brain, and can we use spiking platforms to try to do things differently? And also using light. So I think it's pretty cool. And the UK government actually very kindly bought this, and they are funding me, so that's great. And why photonics? Well, I don't need to convince you that we are doing photonics because, you know, we are all here photonic scientists, so we're interested in this. So, but I think there are key things here. So in particular in our lab, we're using different technologies, but mostly lasers, so VCSELs, vertical cavity surface emitting lasers, and also resonant tunneling diodes more recently. But there are systems obviously in photonics, and the ones that I mentioned there that allow fast speed, low energy, reduced footprint. They are technology mature, especially VCSELs, and they're used in data centers, optical interconnect. So they readily allow themselves to use in computing. They allow 2D arrays, and they are compatible with optical networks and so on. But and also importantly, they permit this optical and electronic control, especially RTDs, with these multimodal data inputs that we can play with. So we were interested, as it has been introduced before by the other speakers, on this concept of reservoir computing a few years ago. So this idea, I'm not going to introduce it anymore, that we can get this very complex performance with very simplified networks in which we only need to train the output layer weights, reducing complexity. And that's beautiful because we can integrate that very simply. And in photonics, that's been provided before, by using the space-time analogy. So just using one nonlinear node, in our case it's going to be a VCSEL, we can produce these large networks with very simple training, with low power, high speed, and we can do pretty cool things with them. So we started working on that quite some time ago. And we tested our system, so we built a simple experimental system in our lab, an optical injection and feedback system in which we are injecting light generated from a match sender modulator and a CW laser into our VCSEL and an external cavity to produce the feedback, a very well-known system to the community here. And in our case, our nonlinear node was a VCSEL, and we were producing these beautiful tasks, time series prediction, channel equalization. So it's very good at time series prediction, classification tasks, and so on. In our particular case, we are using fiber optic components, so our delay time was around 65 nanoseconds. We were sampling at 50 gigasamples per second, so that allowed us to have a network with 325 nodes. We could do pretty cool things with them. And the fact that we were using VCSELs allowed us to have systems with very low power, so typically less than 100 microwatts or so of optical input power to get the performance that we wanted, but also our lasers required just 1 or 2 milliamps for operation, so very, very low power and gigahertz speed processing. So that was very interesting, but as I said, we wanted to look into, can we build systems that are more drawing direct inspiration from the brain, and can we have some spiking platforms indeed with these systems? And if we look into a neuron, actually a neuron is, in a very simplified way, it has these input terminals called the dendrites, where the information comes in, and they are weighted. And all this information coming from different neurons in a network is integrated in the neuron cell, in the so-called soma. And if all the energy combined from these inputs goes over a certain threshold, we get a spike activation. A spike is fired by the neuron, and that is propagated through the axon through other neurons in the network. So if we wanted to build this with a laser or with another optoelectronic system or photonic system, we have to have something like this. So some optical signal coming from a master laser or a master signal with some perturbations encoded into it, and that going into our neuron or a slate platform that will react by firing spikes when stimulated. So basically like a neuron in our brain. So we can do that with the same setup that I was introducing before in the reservoir computing platform. We're injecting light from a master laser, CW laser, into our VCSEL. And lasers, they have a high degree of nonlinear dynamics, from periodic oscillations, chaotic dynamics, but also, crucially to this research, they're also excitable systems. They can be driven to be excitable, much like neurons in our brain. So we have a situation in which we have an optical input, and we have a perturbation that goes over the threshold for a spike firing, as you can see here on this diagram here. Okay, so my Greek, there you go. In response to that perturbation that goes over the threshold for a spike firing, the VCSEL fires a sub-nanosecond long spike, so it's 150 picosecond long spike. But if we put a perturbation which is below that threshold for activation, the system does not fire a spike whatsoever. So because there is not enough energy, it's an all or nothing response. But if we put multiple inputs, in this case they are separated in time, their energy adds up together. And at some point, even though the individual perturbations are small enough on their own, when they add up together, they are able to cross the threshold for excitation and we get a spike firing event. So we get this all or nothing spike activation and this integration regime as well. And the plot here on the right-hand side just shows that if I repeat this input perturbation scheme 750 times, I get the same response, these spike activations, which are shown in this line here. Every dot here is a spike. So we get these very fast spiking responses, much like in neurons in our brain. And also we can look into the other neural-like dynamics in our system. So it does behave like a neuron. It has this so-called refractory period. So basically this idea that when a perturbation arises into the system, it reacts by firing a spike. But if a second perturbation arises too close after the first one, within this so-called refractory period, the system cannot react to that one and does not produce a second spike in response. And that's what's going on here. When the separation between this doublet of perturbations is below 1 nanosecond, we only get one spike activation. But once we increase their separation, we get the spike firing for the two input perturbations. Again, we're talking at systems which are much faster than actual biological neurons, which operate at millisecond timescales, and here we are at nanosecond, sub-nanosecond timescales. So we have these systems which can trigger these neural spiking activations directly in photonics. So the idea was, okay, it's pretty cool. We're having kind of photonic neurons. Can we try to build something useful out of them? And the very first thing that we started looking at was, okay, let's try to do some basic pattern recognition. So we kind of computed these 4-bit input data patterns represented here in these kind of 4-bit squares. And the idea here is that we can apply a weight mask to each of them, and only the target patterns, in this case, are computed in such a way that the system reacts by firing a spike. So in this case, we're particularly interested in detecting that pattern here, and you see that the VCSEL is only firing this sub-nanosecond long spike for this particular input. And it's actually remaining quiescent for all the other possible inputs there. So that demonstration, so it operates very fast, so we can encode these bits at 80 picoseconds per bit, and these pulses are well below 1 nanosecond, at least in our VCSEL. Other thing that we were doing going forward is try to see whether we could do some image processing, so kind of typical tasks that you can try to focus on. So one of them was this idea of the MNIST data set. So the idea here is by applying different kernels, we could extract directly using these spiking outputs, the edge information from these images. So you get here a digit 4, and basically by combining all the spiking regimes, each dot here is a spike fired by the VCSEL. We can retrieve the information, and we did so for many different images. And we passed that information to some colleagues at Strathclyde that work in spiking neural networks in software, and they were able to classify the digits and so on. Okay, so these were, as I said, our initial kind of try to looking into these things, no? What can we do, and what are the ideas coming forward? But obviously, as I mentioned at the beginning, we're also looking at reservoir computing and string linear machines and this concept with VCSEL. So the idea came natural. Can we combine the two worlds together? Can we try to have these spiking systems that we are building with our lasers, and can we somehow draw inspiration from the reservoir computing and string linear machine paradigms to try to build full networks that will use spiking signals to operate rather than analog continuous signals? So using the same scheme, and now without even a feedback loop, so in a way it's more based on the stream learning machine paradigm. We have our system, so we're injecting in time multiplexing way, as it's done in the time delay reservoirs that Kathy was introducing in the first talk. We can introduce this information weighted with a weight masks. And obviously the VCSEL will react if we drive it into the excitable mode, in firing the spike patterns, and they are connected in time. They are coupled through the dynamics of the laser and the leaky integrate and fire responses that we can obtain in the system, and also the refractory period that I mentioned before, triggering also inhibitory effects. So they are indeed yielding this coupling between the different nodes in time. And in fact, what we're building is basically a neural network in which we can include the data. We don't need to train the input layer weights as we do in the reservoir computing paradigm. We have this connectivity provided by the spiking dynamics in the VCSEL, and we can retrieve the output layer information, and we only need to train those weights, okay, to produce a classification or some task that we may be interested in. So as Serge introduced before, we look also at the iris flower classification task, very classical task, 100 years old. It's a 4-feature, 3-class problem. So basically here we've got 4 features, which are the petals and sepals dimensions of the flower and we need to basically tell which type of flower there was. So there are 3 different types of them. So you see that the points are very intertwined, so it's a nonlinear classification task, so you need to do some complex machine learning there to try to separate those. So this is how it works. We can inject the information into our spiking neural network with just one laser, and that's how the input information looks like for all the different points for one particular type of flower. This is how it looks like for one of the flowers here. We can tweak at will the number of nodes that we want to use just by making our time series longer or shorter. And as a response, the VCSEL, or laser in this case, fires these spike patterns, which change depending on the input. And the idea here is, can we use these spike patterns to do this nonlinear classification task? So that's what happens in this map here when we plot all the responses, all the spike patterns from all the for all the different data points. And you see that each of these green dots is a spike fired by the system. So you're already seeing this kind of Matrix movie-like plot. I mean, it's pretty, I don't know if you can see it, but you see that already things start to appear to the naked eye. You see patterns start to appear. So you can already think that you can drive a very simple algorithm to try to see whether you can classify those with using this sparsity in the signals of the spiking patterns and try to develop some easy ways in doing those classifications. So at first we use the very same algorithm that it's used in reservoir computing, this kind of inverse matrix multiplication, and the result was pretty good. We got able to classify the regimes very nicely, so we can get very high performance. And this is basically, this plot here plots the accuracy, so the error, sorry, so we want to have low error, and we want to have high accuracy. So the accuracy is pretty high, as you can see, it drops very, very nicely. But what surprised us, if you want, was not that the accuracy could be high, because obviously that's what you are aiming for, but what really surprised us, in a way, was that we were obtaining very high accuracy for very small training data sets. So we're talking about a task that has 150 points, 50 points per each class, and just using 2, 3, 5 points to classify was already enough for the system to give very high accuracy. So this kind of makes us hopeful that the systems, the fact of using spikes has some inherent benefits for computing. So that was our first task. So it's a 4-feature, 3-class task, but we wanted to push things forward. So now we looked into, can we do things with a more complex task? Can we use our system to do something even more fundamentally complex? And we selected this task, which is, again, a classification task, but it's just a much more complex one. So it's called the Madelon dataset classification task. And the idea here is that it has 500 features, so we're going from 4 to 500, so pretty scaling things up. And it's a 2-class problem, okay? So we need to classify this into different classes. We chose this one because this was a task, academic task, that was chosen as some competition for the NeurIPS conference back in the day in 2000 and something. So we had some metrics to compare our performance with, basically. But the idea here on this task is that we have a point, okay, and we have 5 informative features about this point, and then 15 linear combinations of those 5 features. So in a sense, we've got 20 informative features telling us about the class of that point. And then there are an extra 480 that are just there to mess things around, that do not carry any information about the point itself. Okay, so there are only 20 features which carry information and 480 that are there to make things more difficult. But as I said, in our simple strategy, we're using just one VCSEL, optical injection. We can tweak the number of nodes that we can have our network configured with. So we can just, if we have a more complex task, we can just increase the length of our time series. And now what we did, okay, the task is much more complex. So before we were solving this task with 500 nodes or 1,000 nodes, but now we're at a 250 picosecond per node, so pretty fast. Now we want to have a more complex performance, so let's just basically increase the length of our reservoir or our spiking neural network. So we tried with networks with 4,096 nodes, which basically allows us to have a readout every 1 microsecond, more or less. But that's the idea. Here is same as before. We have the input information there. That's how it looks for a specific point in this data set. And you can see that we get a spiking pattern from the system reacting to that. Again, we tried this with 300 different points from this data set, 150 points per each of these two classes. And you get to see, okay, it's a bit more difficult now because obviously there are many more points and the dots are a bit everything is a bit more tricky. But patterns start to arise as well. And again, just using the same algorithms as in the reservoir computing paradigm, we can get this very high performance in this accuracy in this very complex task. And that goes up to 95% accuracy, which is higher indeed than the baseline that was achieved back in the day in the software implementation of this task, which they arrived to 93%. And we're talking about systems implemented in software with very deep neural networks, lots of parameters, very complex training. So it makes us believe that with very simple hardware and these concepts, and using spiking signals, we can do very powerful things indeed. So, but obviously we wanted to push things forward a bit, and then we looked at, okay, we have now these systems that operate using spikes, but we're using still the same algorithms that are used, well, we were using back in the day for this reservoir approach. Can we, now we have an output which looks completely different. Can we do something completely different as well? Can we drive and create our own algorithm? And this is what we did. We started looking at, this is an excerpt of this kind of map here. But just to show for these two different classes that we get these sparse signals, these spiking activations. And we can already see by looking at it that there are points or nodes, virtual nodes here, that are not very important, like this one here. We don't get very many spike activations for either of the two classes. So that node is not really telling us anything. We have also intermediate nodes in which we get a few spikes here for one class and a few spikes also for the other class, a few more. So it's a bit more telling me about that specific class. But I have, you know, the super fantastic ones, if you want, highlighted here in green. So specific nodes for which we get basically almost no spike activations for one class and a lot of spike activations for the other class. So basically because we've got this binary system, which is either spiking or non-spiking, this particular node is telling me already that if I have a spike here, it's going to be that class, okay? So that allows me to make this algorithm, which we call the significance algorithm, which allows us to rank the significance or the importance in each node to do this classification. And I'll tell you why we found that interesting. We can drive more efficient training. So, okay, these plots are a bit dry, but basically the idea here that we can get very high accuracy, over 95% performance in these complex tasks. That's what is done in this particular, in y-axis here, that's accuracy. Again, very important, even for this complex task, and we're only training the output layer weights. We can achieve very high performance with very low size training data sets, rather than using 80% of the data set to train and 20 to test, as we've been doing in the reservoir computing when we were doing these things. Just using a few points, less than 10% of the data set, we are already achieving over 90% performance in this very complex task. So we require low size training data sets, and we believe this is precisely because of the spiking nature of the system. And I also mentioned that we're developing these algorithms where we are only looking at the importance of these spiking nodes. Some of them are very, very telling me something about the class, and some others are basically telling me nothing. And that allows me to even reduce the number of nodes that I need to use in these concepts from the output layer to train my system. Typically in a reservoir, you need to train all the nodes in your output layer, which is pretty good because you don't need to train the internal nodes or the input nodes. But here, we're achieving very high performance, just selecting less than 1% of the output layer's weights only, okay? Just selecting those that are more significant, and still we are able to achieve very high performance. That's what's shown here, that only using 20 nodes of the basically 4,000 nodes network that I'm building, I can get very high performance indeed. So that's where we are at the moment, and we're trying to increase, obviously, the complexity and looking also at server computing paradigms and doing new classes and new tasks and collaborating with some of you in this. Also, some other activity that we're driving in our lab, it's in collaboration with some European partners. This was part of a European project called Chip AI. We're also looking at resonant tunneling diode systems. And also, it's a different way to try to build these optical networks or these optoelectronic networks. And it's also a device that I showed you that it's excitable, okay? So we're looking always interested into these things. So a resonant tunneling diode, in a nutshell, it's a very simple device, and it's the device that allows you to see quantum tunneling at room temperature, okay? But at the core of it, it's basically a double barrier quantum well, and you're basically creating this potential well, okay? And you have these quantum energy levels. So when you start to apply voltage into the system, this is an electronic device, as if it was a diode, you start to get an output that grows with your input. But at some point, as you increase your voltage or your bias, you are basically changing your energy levels, and basically at some point, the electrons cannot tunnel through the resonant tunneling condition, and you get a drop in the performance, in the IV curve. So you get this so-called negative differential conductive region. And when you go and get back again, and you go over this threshold, you align to another different resonant level, and electrons can tunnel through, and you get this recovery. So you get this very N-shape or Z-shape IV curve, okay, which starts like being like a normal diode curve, but then it kind of drops very nicely, and it kind of recovers. So you have this region of so-called negative differential conductance or negative differential resistance. And the beautiful thing here is that when you bias your device at these points, either at the peak or at the so-called valley, and you push the system into one side or the other, you get an excitable excursion, and you can trigger a spike in signals. So that's what's happened here. The idea of this project was to combine these resonant tunneling diodes with either photodetecting and light-emitting sources, so we could build these optoelectronic neurons, and that's what we call the so-called PRL node, okay, with a photodiode, a resonant tunneling diode, and a laser, or an LED, to have this kind of optical input and optical output and spiking activation. So in simulation, because quantum tunneling is really, really fast indeed, you can get a very short pulse producing this perturbation that will trigger a spike fire by the resonant tunneling diode, and that will drive a light source, and you will get an optical spike at the output. And the time scales, you can see them there. It's well below 1 nanosecond, and that's basically limited by the circuit that you build around it. So we were looking at these things, and we were starting to build these things modularly because we work with VCSELs. So we say, okay, we can put a photodiode at one end, we can put a VCSEL at one end, we have RTDs in the middle, and then we can start looking at these things. So that's what we did. This is what we call the PRL node. And basically, we've got an RTD, which is going to be our spiking system, a photodiode, just to have lighting, and that basically the output from the RTD drives the laser that produces the optical spike at the output. So these are the IV curves from the RTD. So we're going to base it here at the peak, for example, and that's the LI curve from our laser, and we're going to drive the laser just below threshold. So basically, this is how things work in experiments. So we can come with very small optical pulses into our photodetector. Very, very small electrical signals can bring the system over the equilibrium point and trigger a spike excursion. And it's here seen in red. That's the electrical spike driven by the RTD. And that's basically the output, optical output from the node coming from the VCSEL, which is basically directly modulated by this. Okay, so we have this modular, flexible system in which we have optical input and output terminals, and we can have spiking systems. And we started looking again, as we did before, can we do some tasks with them? So one of the things that we did is that we did this coincidence detection. So we had two optical inputs at two different wavelengths entering our photodiode. And basically, when they are both aligned in time, their energies, combined energies add up, and we get a spike activation. And so does happen when they are slightly separated in time. We get still spike activations. But when they are farther apart, their combined energies, basically things go down, and they are not enough to trigger a spike from the system. So with this very simple approach, we can have this very simple task, coincidence detection, which is something used in our brain for the auditory tract and many other different things. So that was our first approach, and then we said, okay, can we go as part of the project try to drive things forward and trying to build systems which have more integrated functionality, and that's we developed here in collaboration with colleagues at Glasgow University and others. We developed these systems, which is basically an RTD with an optical window, so now has a photo-detecting capability inbuilt in it. And it has even a nanostructure here, a nanopillar, to try to reduce even further the energy that we need to drive the system. That's the LI curve, the IV curve from the device, and obviously has this NDR function here. And in blue, we have the dark IV curve, so basically only the electrical response when we drive with voltage bias. And when we shine light on it from a tunable laser at 1310 nanometers, 1 milliwatt of power, we get a shift in this IV curve. So basically this tells me that we got a shift both upwards and lateral. The lateral one might not be that clear. But basically I can put myself at the boundaries between either the peak or the valley where this transition happens, launch some optical perturbations, they will modify the electrical response on the system, and I will get this activation of electrical spikes directly from it. So that's what we did. So we biased our device at the peak. Again, it's rather low power, 0.5, 0.6 volts. And we check these perturbations, in this case, these negative pulse perturbations with increasing intensity. And you can already see that when they are below the threshold activation for spike firing, we don't get any spike activations. But when we start going ahead and beyond this threshold for spike firing in the system, we get these reliable spike activations coming up from the device. This was in the peak, so again, these are very, very low optical power signals. We were using 1 milliwatt, but in principle, they should be much faster than that, much lower power than that, but it's just due to the coupling. We were having some coupling efficiency problems there. And now we can also drive the system in the valley, put now positive perturbations, and again, only when they go over the threshold, we get these reliable spike activations. So not only have we got ourselves an optoelectronic neuron that can work with both optical and electrical signals delivering spikes, but it has two modes of operation, both in the peak and the valley. And we can do some tasks with them, and now, as of late, we are starting to look into interconnecting these things to try to build networks. And the idea here is that we have a first element with some periodic perturbation input that triggers a periodic spike train from the first one. We have a VCSEL, basically, to convert these electrical spikes from the system into the optical domain. We have a weighting element in between, the output from this first element here. We weight it down, and then we connect the input. The output from the first one, we connect to a second one, and only the second one only fires spikes when we get these high-power optical spikes from the first one here. So we get this interconnectivity, we get this multi-wavelength operation, we get this task performance. So the idea here now going forward is, can we build networks with this? So we've done some work in theory, and just as a demonstrator, we show that we can do 5-to-1 neural networks and different layers, and to try to do some spatial temporal pattern recognition, and it seems to work. We developed some algorithms for the training as well. That's reported in that paper. The idea going forward is try to do this experimentally. And just to finish, acknowledging everybody in the group that has been working on this through the last years. If you have any doubts, please by all means contact me, acknowledging also support from our partners in the European project that provided devices and help with the fabrication, and the sources of funding. And also, just to mention that we have a book project together with my colleague Bruno Romeira. That comes from when we had a symposium in Clio Europe and Photonics for AI. And we have been approached to try to edit this book here, this book project. So please, by all means, if you're interested, consider it. And I'm sure I will be contacting you individually in the next few days and weeks to try to seek your contribution. Thank you very much indeed.
Thank you, Antonio. A really interesting talk. Any questions? Yeah.
I had a question, just trying to understand for instance, this classification task, the more complicated one you did. My understanding, but I may be wrong, the Madelon task is that, so you've got your 480 features, and you have, you said your data gets masked. So what you do is you take linear combinations of all these features, and these random or say linear combinations are used to drive the VCSEL, and you see which linear combination gives rise to a spike and which don't, or is it, how does the...
We use a random mask.
A random mask, and then this random linear combination of input features is used to drive...
We expand these 500 features to the number of nodes that we've got.
And then you see which gives rise to spikes and which don't, which is like a threshold. Is the linear combination above a certain threshold?
So the input looks, obviously because it's a linear combination. So it looks different in each particular time step. So every time step is 250 picoseconds. That would be our virtual node duration. And some of them, because there is this leak, integrate, and fire behavior, so things are integrated in time, and then it kind of goes down, and then if you get a spike, you have a period in which you don't get spike firing. So there are all these different dynamics.
Okay, so there's even talk between successive inputs to your pixel because of the leaky integrated fire.
Yes, yes, and yeah. Those that do not activate, but also those that activate inhibit some responses going forward.
Hi, sorry. So very interesting talk, thanks a lot. In terms of advantages, I understand clearly that the ultra-fast timescale is very impressive, but then you mentioned also that you get advantages in terms of accuracy or performance compared to more traditional algorithms, even in software. And that I find it really impressive or surprising. So I wonder, what is the specific mechanism that you think brings this advantage in performance? So is it the fact that you use a reservoir? Is it the fact that you use a spiking neurons, which would then presumably be also observable in software? Or is it something about the hardware that you use?
I guess the honest answer is I don't know. I think the fact of using spiking signals might help. Also, I should mention that this Madelon data set, we selected it because it had been part of a competition, but the competition had been quite a few years ago, to be honest, and they implemented this in software. So we had something to compare with, if you want, something complex, something to compare with. I am sure nowadays with incredible things that AI can do, I'm sure they can build software networks that can do this, also to this high level of performance. I guess the beauty here is that we're using just one laser and something very, very simple in hardware, and basically benefiting from the fact that, and very simple training. We're just training an output layer, so I honestly don't know, but I would be happy to discuss, yeah.
Yes. Hola, Antonio. Thank you very much for your insightful talk. My question was related to the laser source. You have mentioned all over the presentation that you have been using pixel sources. I assume there are some underlying implications related to size, efficiency, power consumption. But I was wondering if you have thought about using other laser sources, such as the DVR or DFB laser sources, and if you think that this may have an important effect in the outcome and the results of these works.
What type of other sources were you talking
DFB lasers or DVRs, distributed back reflectors?
Yeah, I'm assuming that you should be getting similar performance with a DVR or DFB laser. You could drive them also in an excitable regime. I guess the only drawback there would be that you would need certainly a higher bias current to drive them, so one order of magnitude higher, and potentially you would need more power to get the system to produce the outcome that you desire. But yeah, we are also looking into using bespoke laser sources that will have an improved advantage here. I guess I forgot to mention that all the lasers that we are using here are commercially sourced, so there is nothing particularly special about them.
Okay, thank you very much.
Okay, let's thank again Antonio. Also, I would like to thank all the speakers of the session, and I think we will be back at around 2:30, right? In 1 hour from now. Keep synchronized at 2:30, okay? Thank you.
Adoni, I think we're missing quite a few people. No problem, okay. Okay. Yeah, now it's actually the time where the workshop turns into a symposium, because symposium means, in Greek, drinking together. So actually, after drinking together, it's 2 minutes, okay. So, okay, I think we can start. So this is the third session now, and we're going to start with a talk from Adria Grabulosa from Université de France, Comte Besançon, in Besançon, France. Sorry. Yeah, and the title will be 3D Integration Towards Scalability for Photonic Neural Network Integration. So the floor is yours. Thanks a lot.
Yep. Okay, so again, thanks for the invitation. Actually, I was not invited, but it was my boss, Danny, but he couldn't come, so here I am. So I will try to, give my best. So basically, today I will present you our work, what we do at FemtoST in University of Franche-Comté. And the title is 3D Integrations Towards Scalability for Photonic Neural Network Integration. So first, a bit of publicity of our institute. So we work at FemtoST, and it's located at Besançon. I'm sure you don't know where is this. So it's in France. It's near the border with Switzerland. So, well, and as the French, they tell, they have the best cheese over there, which is the Comté. And this is a picture of our group. In the top, a more recent one, and in the bottom, like an old one. So I'm in both, so I'm not scamming you. I really work for Danny. So, well, to start, the scientific motivation of our work is basically, well, you all know this graphic already. So, but basically here in the left side, we can see the performance versus the peak power of the power consumption of all the range of microprocessors we can have, beginning from the small ones we have in our laptops or phones towards these data centers. So basically, all these microprocessors, they are stuck in this linear trend where to achieve a high peak performance, we really need a high power consumption. So until now, there has not been any technology capable of shifting this tendency towards this goal over here. It's high performance and low power consumption. So basically, to have more by paying less. So one way to do this, it's, well, this is why we are here. It's by means of photonics, because we can take advantage of its parallelism, the high speed, and the intrinsically lower losses. So another way to do this as well, it's by means of the optical neural networks, and you are much more experts than me on this. So basically, this is I will just say that this is a typical scheme of neural network with the artificial neurons that are arranged in layers, and they are connected between them with this kind of connections, of interconnections. So all this has a neurobiological inspiration, and you can see here from this handwritten draw of Ramon y Cajal, where he drew what's happening in our human brain. So basically, all this bunch of neurons are highly dense interconnected between them, but they have one thing in common, that all the connections are done in parallel. So from starting from a point, they go through different layers in a parallel way. So to do this, or to be able to do this in a hardware, so it's very challenging. So for instance, here we have the typical 2D photonic substrate, where we have this mesh of Mach-Zehnder interferometers. So just by a 4x4 connection of array, so the area of the chip scales to 1.2 millimeters square. So basically in 2D, the input and output channels doesn't scale linearly with the area and the height of the chip. So in order to mimic what happened in the brain, where we have around 100,000 neurons per millimeter square, so it's impossible. So our solution, or what we propose here, is to use the 3 dimensions of the space. So basically in our scheme, so the artificial neurons will be arranged in a 2-dimensional layer, whereas the connections itself, they will be done in the 3rd dimension. So this results that the input and output channels or interconnections scales linearly, as you can see here, with the area and the height of the microchip. So how to do this? So our fabrication technique is based in the 2-photon polymerization process. So I'm sure you all know about nanoscribe nowadays. So basically this machine is able to fabricate sub-micron structures. For instance, here I just put an example of the Eiffel Tower or the Taj Mahal with very high precision. And this machine is used nowadays in a lot of applications, from crystal lattices, from mechanics, and so on. But for us, the most important is it enables to print or fabricate optical components. So a bit more in depth of this, basically, like this machine works as a femtosecond laser. It's first rapidly moved with a galvo mirror, and then it's tightly focused with a microscope objective inside liquid photoresist. So what happens is from this liquid photoresist, which is like a polymer solution, the 2-photon absorption of the photoresist launch or trigger the polymerization of this liquid polymer into a solid monomer. And normally this volume is so-called voxel, which typically has a feature size of 200 nanometers. But one key aspect of this is that this technique is CMOS compatible. So basically means that we can now 3D print different objects on top of different silicon or like CMOS substrates. For instance, in silicon photonics, or in more complex substrates, as in gallium arsenide micropillar arrays. But with this, I will talk later about this. So this concept was first demonstrated by Lindemann here in this article by the so-called photonic wire bonding, in which by this method, they linked 2 photonic substrate from point A to point B, that in each case, the different points are 2 different CMOS substrates, different distance by a gap. So our first demonstrations by using this technique were the air-cladded 3D waveguides. So here you can see the refractive index of the polymer when it's fully polymerized. It's around 1.5. So when they are air-cladded, so basically the cladding is air. So this means that the NA is really big. So for a waveguide of diameter of 1.2 microns, there are already 22 higher modes present in these waveguides. But this allows for high integration. So for instance here, we fabricated 1 to 9 couplers that they have this shape here, like an octopus, let's say. But the cool thing about this as well is that we can escalate, or we can increase exponentially the number of outputs. So from 1 to 9, so if we cascade the same structure, we can achieve 1 to 81 outputs. So if we check here at the optical characterization, so it's obviously the higher order modes are present, and the losses for the different couplers, 1 to 9 and 1 to 81, are quite high. But here we went farther. So basically, we printed these highly connected couplers where there are like 225 inputs, and they go out to 529. Okay. Now, I don't know what happened this. Okay. So another application of this is that we can fabricate spatial or the so-called hard filters for convolutional neural networks, that they are like the final layers on deep neural networks. So basically, for instance, in F3, if we take an example, if we inject from this right corner, so we spatially filter all the signal towards the middle, for instance. So this concept works really well, but there is a drawback that there is a high cross-talking between the waveguides because intrinsically they have higher order modes. So the next investigation we did is to print waveguides as well, but instead of air-cladded, they will be polymer-cladded. So basically, with the same material and with a single step, we can fabricate this kind of waveguides. So the basic concept is, as you know, for the core of the waveguides, they have to have a refractive index that it's higher than the cladding to allow total internal reflection. So with the same photoresist, the advantage is that we can tune the refractive index or the degree of polymerization over a range. So basically, for the core, we use this range for higher refractive index, and for the cladding, we use this lower range. But basically, how we can tune this? So with the machine, by the two-photon polymerization, we can directly tune the refractive index while printing. So basically, here is an illustration that shows this concept. So the refractive index of the core here is higher of the refractive index of the cladding. And here there is a structure of a 3D cuboid or block that it's integrating different waveguides of different diameters. But as you can see here, the fabrication is quite slow because all the volume, it's like printed in the same fabrication step, but this volume is quite huge. And also with this technique, we can print volumes that are like graded in refractive index by changing or modulating this laser power. So here there are some results using this technique. So basically here we can see the confinement factor versus different waveguide diameter. So by injecting different modes inside the waveguides, so we can have the different optical modes that they can allow inside the waveguides. For instance, the LP01, that is the fundamental, and going further to LP11 and LP02, sorry. So basically, we can, with this technique, we can really tune the optical confinement and then the optical modes present in this kind of waveguides. So we compare as well the numerical aperture for STIN and graded in the waveguides, and as expected, the numerical aperture for the graded case is higher than the step-in case. Here as well, we evaluated the evanescent coupling or the coupling ratio between different pairs of waveguides that they were printed with different gaps between them. So as expected, the coupling decreased exponentially with the distance. So here you can have a taste of the idea of how apart they have to be, these waveguides, in order to reduce the crosstalk between them. So how densely packed they can be, these waveguides, in a space. So here we can see that for a distance of 4 or 5 microns, the evanescent coupling also is diminished completely. So in order to solve this problem of the printing time, so we develop a new technique that we call flash TPP. And basically, so it involves 2 steps. The first step is, as usual, we print the waveguide score with this 2-photon polymerization, where we have to optimize different parameters, for instance, the laser power, or the hatching and slicing distances that define the resolution of the final waveguide. And so we want to really optimize this to have smooth transition throughout the waveguides to reduce propagation losses. So once all the photoresist is like the photoresist that not has been polymerized is developed from this photonic circuit, we introduce the chip inside a UV chamber where it will be 1 photon polymerized. So basically we play as well with this concept of using the low refractive index region for the cladding and the higher refractive index region for the core. But in this method, we mix different polymerization techniques. So here we can see an example of different waveguide diameters printed in this cuboid, where the red areas represents the volume printed with TPP, and the blue with the OPP. So here so we evaluated the propagation losses by printing different waveguides of different length, up to 6 millimeters. So here you can see that we can really have structures of high aspect ratio. From this linear fit, we extract propagation losses of 1.36 dB per millimeter, which for polymeric waveguides is still okay, but we are far from the silicon photonic propagation losses by 1 or 2 factors. But the cool thing about this is that we have low injection losses of 0.2 dB. And basically, so I would like to mention that here all the different data, so they were like the different waveguides were printed in different substrates, meaning that there is a higher reproducibility of the measures. And as well with this technique, which I recall it's single step plus single material, so we can achieve refractive index difference of 10 to the minus 3, which allows for single mode propagation. And compared to the previous technique that I show you, so it's 90% faster, because basically all this volume that it's represents the cladding, it just polymerized by 1 flash. So we also check the temporal stability of this kind of waveguides. So they show, they have been shown to be stable for more than 1 year. This was at the time for the paper, so basically 1 year ago, and now I'm writing the thesis, so I check it again to be sure. And also we check the temporal stability under continuous aspiration, basically injecting a laser for more than 600 hours, and basically the optical performance, or DNA in this case, is the same. But however, once we put these structures directly under sun exposure, so basically they polymerize absolutely. So basically this is linked because the low degree of polymerization in these cladding regions, that they may have some photoinitiators still there in the solution. So basically the direct sun exposure finalizes or activates these photoinitiators and triggers the final polymerization. But this is not a big issue because normally we don't put our chips directly under sun. So we went further in our demonstrations. So we fabricate what we call 1-to-M Brobland couplers that they show adiabatic coupling between one input and several outputs. So basically the geometry of this, so it's one input, from one input we inject like here, and we inversely taper the different outputs where the light will be evanescently coupled between the different output ports. So with this technique, we compare to geometries that we call conical and truncated rod. So basically for the conical is as usual in this taper length, the two waveguides are squeezed in the X and Y direction at the same rate. But for this truncated rod, so one direction, let's say X, is fixed, while the Y is squeezed at the same rate as before. So basically this gives more transfer area or more space for this efficient adiabatic coupling between the waveguides. And this has been shown experimentally because, well, as you can see here, the truncated rod couplers show less losses than the conical ones. We also checked the adiabatic criterion of our couplers. So we printed different waveguides for different taper length, from 200 till 500 microns, and separated by a distant gap. So we can see here that for a taper length more than 200 microns, so all the output intensity represent single mode and are mostly decoupled. As well, we characterize the coupling losses of these kind of structures. So we print, again, different couplers with different taper length and different gaps. So we obtain that for the best conditions, the optical or coupling losses are reduced to 0.06 dBs. And the difference in the output intensity between the two output ports, it's only 3.4%. So basically, it's highly homogeneous. And finally, we also check the broadband functionality of this kind of couplers by injecting light with different wavelengths, almost spanning an octave from 520 to 980 nanometers, and where the global losses in all this range are lower than 2 dBs. And finally, we also printed some fractal splitters, basically by cascading two 1 to 4 adiabatic couplers in 2 different layers. So here we can see the resulting 16 output ports. So basically this shows the capability of this kind of technique respect to the number of output ports that we can achieve, going from 1 to 2, 1 to 3, 1 to 4, and up to 16 output ports by cascading 2 in a sequential layer. And also, the global losses of this 1 to 16 coupler are only of 1 dB. But still, there is a bit of inhomogeneity in the difference of intensities, as you can see. So we will work on that. And just here, like a recap of all the aspects of global losses that I mentioned here. So basically, this is where we want to go. So we just demonstrate the proof of concept of our technique to print different waveguides, air-cladded, polymer-cladded, whatever you want, but this has to be used in some practical context. So we start by printing on top of semiconductor gallium arsenide substrates. So to show the compatibility of this technique with CMOS technology, even this is not CMOS yet. So the first challenge of this process basically is to optimize the laser power, calibrate it, because basically before, all the waveguides I showed before, they were printed on substrates that they are transparent in the wavelength of the femtosecond laser. But here, there are multiple reflections going towards and coming back from the substrate. So basically, we have to optimize precisely the laser power in order to have proper polymerization plus not burning. So this is what we did here. So you can see, like, sweeping the laser power give or fully burned regions or not even polymerized. So then we fine-tune in a different range of laser powers, so we know in which area we are safe. And then while printing on top of these gallium arsenide micropillars, so we observe that when we print cubes, for instance, there are some sort of holes that they are directly on top of these micropillar structures, basically because there are some issues finding the interface in these areas. So basically the solution we found is to print, as before introduced, to print these cubes with a graded laser powers of different laser intensities as we go through Z, so with different refractive index. So basically we see from this left side to the right side the difference in these both techniques. So here we achieve like this smooth surface along all the cube. And here it's like different structures that we print as before, the same cube with different waveguides inside in front of gallium arsenide. So it's just to show that it really works. And then the second challenge of this technique or printing on top of different substrates is basically the alignment. So here we just, this is all done by the two-photon polymerization. So first we print these cylinders, then we develop all the sample, and then we again print it on top, but shifting or tilting the substrate. So basically we arrange the scanning direction of the femtosecond laser with the pattern structure. So here we can see that the alignment of the new structure is fully in the middle of the fabricated before. And here is an example of the same, but on top of gallium arsenide micropillars. So you can see that these waveguides here are completely aligned with the pattern on the bottom. And here some preliminary results of this kind of technique, or where we print different waveguides on top of the micropillars, and we just inject light in order to see the reflection on top of the micropillars. So basically we can see here when the laser is on the wall, so there are multiplying scattering along all the area, but then when we put on the waveguides, so the reflection gives this higher intensity here, and these are the losses for these wavelengths. The better results are for 1 dB, which is like promising for the future. And this is like, I want to show here just like our idea of arranging these artificial neurons, or like the image of a neural network, arranging the artificial neurons in 2D, which here are the microlasers. And then the connections will be done in 3D via these three-dimensional waveguides. And these are, well, where we want to go. It's like doing some connections between them, as well as higher scalability or higher connections between these. And well, this is the conclusions. I will not read it, you know already. And thank you, and I will be happy to answer some questions.
Thanks a lot, Adria, for this interesting talk. So now the talk is open for questions. Please, Wim.
So, now that you can make single-mode waveguides in this technology. Yeah, okay. All right, very nice work. So now that you can make single-mode waveguides in this technology, how good is your phase control? Because once you're single mode, then you can start thinking about making interferometers and phase-dependent devices. And like in the last picture you showed with the lasers combining, you can imagine also that phase relations between those different waveguides start to become important. So how accurate can you control the optical path length or the phase of these waveguides?
So basically you are talking about adding tunability, you know, to the waveguides?
Well, first of all, just by definition, passive, how accurately can you control it? Like if you make two identical paths, will they be constructively interfering, or how much phase error will accumulate between these two paths, like over a certain length?
So, well, basically all these proof of concepts that I show you now, all the waveguides are passive. So basically we didn't start to control any phase. So we didn't introduce any active.
No, but I'm not asking for active. I'm asking for pure based on fabrication. So after fabrication, how well is the phase controlled? So, I mean, if you take silicon technology for chips, typically they have very good phase control. You can make very long waveguides, and you know exactly what the phase delay is along those waveguides. So how accurate, or what is the uncertainty on the phase after, let's say, fabricating 100 micron of waveguide?
Or let's say on the waveguide length, for example, how accurately you can control the waveguide length?
In terms of fabrication, so we can, so basically in the length, we can really like control the dimensions of the waveguides. The main problem we are facing now, it's about the smooth in the interface. So basically we want, well, the next step is to try different resins in order to have these smooth interfaces. So then I suppose it is more related to your question. So if there are no scatterings in the interfaces, so then we can control, or we can tune more, or we can control, yes, the phase of this, of the light going through.
Okay, but you don't have any numbers or no
Of course,
measurements?
no,
Okay, no, okay.
Not yet.
Okay, thanks.
Yeah, exactly. I mean, maybe basically, like, maybe we really want to do some reliability studies on this, right? Maybe just make hundreds of the same connections and see what you get. On that same note, so the losses from, let's say two waveguides, one waveguide to another waveguide. Mm-hmm. You showed them. Yeah, like what are the losses again, and what are the contributions of this? In other words, what may be, let's say in terms of roadmap, let's say you want to say, okay, right now we're here, and we can go eventually to that level. So what would be a roadmap, maybe an ultimate roadmap in terms of impedance mismatch, what the tool can do, I don't know, like what might be a number, you know, imagine in 5 and 10 years that someone could give someone, say, hey, with this technology, that's the coupling loss we could maybe get.
So basically you are asking for an outlook of how low loss we can get?
Correct, like an analysis basically, let's say you're currently, I don't know, so many dBl losses, and if you break that loss down, there's so much coupling, material, interface, polarization, blah, blah, blah. You break that down, and then you can start forecasting how much each could be reduced. Mm-hmm. What might be an outlook in 10 years, what this technology could give in an ultimate best system?
Okay. Well, basically here, for instance, in these adiabatic couplers, so the losses are mainly defined by the difference of refractive index you have between the core and the cladding. So basically, if you have uniformity along all the volume, so then you can reduce the losses by this adiabatic transfer if you make it long enough. Then, for instance, to go through a volume, so then we need to go layer by layer. So this is the example we show here for these fractal topologies. So we show it in the air-cladded, but now with the polymer cladded, so the losses are lower, plus it's single mode now. So basically, the advantage that gives this kind of fractal topology is that here the number of outputs, it scales exponentially, but the losses scales linearly.
Yeah, let's say for a single connection. So I think if you don't have the number, that's fine too. It might be good to get a very good forecast number. Mm-hmm. So let's say if there's an investor coming, right, or a big company wants to put a lot of money into this technology, maybe they can, you know, make multiple beams at the same time, like, you know, multi-EBL these days and things like this. What might be an ultimate lower limit? I mean, say global loss is less than 2 for the entire range. It might be good to really drill down on this and have a very good number ready with development, you know? Mm-hmm. And if you have it, let me know.
Okay. I mean, the only number I can give it to you is this one that we have it here. So basically, if you make it long enough, so you make it easier for adiabatic transfer, we can achieve 0.06 dBs. So it's like almost at the limit of what we can measure, basically. But of course, for integration, so there is the need of making it shorter, because 500 microns now it's quite large. So we are working now in making this kind of couplers as well in air-cladded with lower losses. So we are working on that now.
Okay. Let's thank the speaker then again. And move on to the next talk, which will be given by Bin Shi from the Technical University of Eindhoven. And Bin will talk to us about WDM-based photonic integrated convolutional processor with additional parallelism.
Okay. First of all, thank you very much for the organizers and Adonis and Caris and also Nikos for inviting my supervisor to come here because she's busy in another conference. Then I will present in her place. But nonetheless, all the work is done by myself, so it's I know every details of every experiment. Okay, so today the main topic is about our new result on the WDM-based photonic integrated convolutional processor and with additional parism. And then during the talk, I will first of all to have a brief introduction of the photonic neural network, and then to the previous work that we have done in the indium phosphide platform on the all-optical deep neural networks. And after that, I will talk about the convolutional processor and the parism that we propose. Then after that will be the conclusion. So for the introduction of the background, that nowadays the data volume is increasing exponentially, and it will go up to 175 zettabyte per year in almost 2025, and which inside this data that we have our voices created and also the video and image created. Then, so this calls for more and more computing power for the processing of the data. So, and for the second, for the image, for the figures of the right side, you can see that the demand of the computing is increasing, but the computing efficiency and also the computing power is saturating, which creating a computing gap. So we need to think how we can have more sufficient data processing approach to deal with this exponentially increasing data volume. So we think in some other ways that we can have some inspiration from our brain. So for the supercomputer nowadays, it can carry out petaflops operations. Now it's hundreds of petaflop operations, and it will consume 10 or more than 10 million watts on the calculation. But in our human brain, it can carry out the same or more or less the same magnitude of the operation in computing, but it will consume only 20 watts. So it's meaningful to think whether we can create some create some computing connectivity like the human brain to make the computing and also the data processing more efficient. So this goes to the non-von Neumann structure. So for the non-von Neumann structure, it will mimic the brain connectivity, and it will mainly carry out the parallel computing. So it would be very suitable for showing like the voices recognition and image classification. And now it can also use for automatic control of the balance of the bicycles, for example, and also the controlling of the driving. Then during our work that we are more focused on the deep neural network because it's the most simple structure that we can implement in our photonic hardware. So I would like to have a brief introduction on what is the deep neural network. Maybe all of you have been very familiar with. Then mainly that we have many layers of the neuron. Then it will connect to in a forward connection frame. And also this network is very big, but the basic unit is the neuron. So the neuron will include the linear part and the nonlinear part. The output of the neuron will be the nonlinear transfer function of the weighted addition and plus the BIOS. So now then for the electronics, there's already many chips that fabricated for the artificial neural network or the spiking neural network, which have very high synapses integration density and also very comparably easy fabricated, and the power efficiencies go down to 1 gigajoule per operation. But they also based on the low bandwidth in between the memory and the processors, and therefore the computational speed is eventually limited in with this bottleneck. So we need to think an alternative approach to overcome this limitation. So this goes to the photonic neural network that we are using now. So we will have a more cooler calculation because the light propagation do not really generate heat. And also, it will be more faster, relying on the faster modulation and also the speed of the light. And if we make good use of the parallelism enabled from the nature of light, that we can increase the parallel computing in a more advanced fashion. So now there's already a coherent approach from the MIT group and also a microring resonator fashion from the Princeton University. Then, so they have performed very good in the classification problems, but the chief of the coherent approach would be more sensitive for the phase noise. And then for the micro rings bands, that it make good use of the WDM sources, but because of the thermal crosstalk, that the control would be more complicated. Then now in our university we have the indium phosphide platform, so we developed this concept on the indium phosphide platform using the SOAs, which may the circuit not phase sensitive, and we may not really have the thermal crosstalk problem, and we can have gains and also high dynamic range of tuning of the weighting. And we can also use the nonlinearity from the SOA itself directly co-integrated on chip. So that's why we develop an approach, which is the optical deep neural network approach. As you see that on the top would be the general deep neural network structure. Then what we propose is use a WDM inputs and also to split into different neurons. And inside the neuron, we process the data with also the WDM inputs. So basically, you have parallel wavelengths in, and you can tune the weights after the deep multiplexing with the SOAs or other elements. Then after that, it would be combined to fit to a nonlinear unit. Then after the linear unit, you will get to another single wavelength. And it will be combined again to fit to the next layer, or it can be communicated with another core, another layer which is maybe not in that chip, maybe on the other chip. Okay, then we have previously proved that we use the cross connect as a linear function to have the iris flower classification, which is already 3 or 4 years ago. Then we design and also fabricate monolithically integrated neuron, which we use the SO as the weighting linear weighting element as well as the nonlinear function at the output. So we have tested this optical neuron, and we do some simulation on the, because we have only one chip as a neuron, so we do some simulation with the map of a neural network containing 64 wavelengths, and it turns out that the neural network would work using the linear function that we have from the wavelength converter. But nonetheless, because we use the SOA as the output, so we will have introduced some noises at the output. So the performance of the classification will be degraded by 5 to 10%. Then we also do some investigation of the scalability of the neural network using the optical integration. So we have developed this noise modeling basically to analyze the relation of the signal clarity related, relating to the output noise that we have from the output. So we need to consider the original signal noise and also the conversion noise from the nonlinear SOA. So if you have the input here, then you will originally get some noise from if it is the previous layer, or like the chip, if you are imagining it is on the second layer. Then if you go to the amplifier and also the weighting elements, and then the nonlinear SOA. At the output, you will get directly the error. Because we use the wavelength conversion, we cannot detect the in-band noise from the OSA. So we need to detect the time trace and calculate the error to trace back the noise that we have on the in-band in the signal. Then if we have the model that creating the relation from the input noise to the output noise, so we can emulate that if we tune the certain level of the input noise and detect the certain level of the output noise, that we connect this from one layer to another layer, that we can emulate the scaling of the neural network. In this sense, that we do some measurement to the noise at the input and measure the error at the output. So as you see that on the left side here, that if you have a lower OSNR at the input, that you will get higher errors. Then, so we tune this OSNR from from very high OSNR to low SNR, and we measure the direct connection from the modulation output to the detector as a back-to-back measurement, and compare it to the multiple wavelengths in and single wavelengths out neuron. So we can see what is interesting here is the crossing between the back-to-back measurement to the chip that we have, the chip output error that we have. So at the crossing point means that for this certain OSNR input, that you will expect to get the same OSNR at the output. What can be more well explained is that you can see if we have an input OSNR, what we can expect what we get from the output. For example, if we have, first of all, 38 dB of the OSNR at the input, then you will get output for 7-channel in weighted addition and nonlinear transfer function, which we localize more or less 20 dB at the output. Then after that, if you have 20 dB as input, you will get a little bit lower and lower. And when you reach to the crossing point here, then the OSNR will not change. So roughly at 90 dB as the OSNR, that this neuron then can be scaled like as you like, arbitrary depth. So this means so we can use these kinds of optical neural network to make like very, very deep neural network. So so this noise complexion is coming from the multiple wavelengths to single wavelengths conversion. Because if you have single wavelengths conversion, that you will lose your extinction ratio at your output. But if you get multiple wavelengths conversion, then your extinction ratio can be kept as in the input. But the drawback is that still you get like 90 dB OSNR as input and output. Your error is still a little bit high. Then we also do some simulation on using this concept, so we can see that after 4 layers, that the output noise will be stable. Okay, so this is all about the optical neural network that we investigated previously, and we also deep into the convolutional neural network. So the convolutional operation is also inspired and also based on the structure that we had previously. Then we have this extension research. So for the convolution neural network, first of all, this is the very general operation of the convolution. If you have your input image and also the kernels, the kernel will need to scan this image step by step. For every step, you need the kernel will have element-wise multiplication and have a submission to produce one output. So in general, in the computer, if you are not using the parallel operation, then you will need to carry out this scan step by step. So this is part of the convolutional neural network, which is given the boxes here. Then after the convolution, which is the feature extraction of the classification, then you can connect it to the fully connected neural network to do the classification. So in the optical domain, then you have the different choices for the convolutional processing. First of all would be the Fourier transform, which you can use the start coupler and also the phase shifter and star coupler as proposed in this paper from O. And then we can also make good use the parallelism on our chip or from the light. So the parallelism can include the space, the wavelengths, and also the free space region. So using the wavelengths as present here, then for the input image, these image pixels can encode into different wavelengths representing into different color here. Then the kernel can be the same kernel, but the kernel can process different regions of the input simultaneously using one step. So you can basically get the complete output including all the parallelisms that you have from the wavelengths. So if you reduce the wavelengths, then you can create another dimension of the acceleration of this operation. Then, so most recently, actually, we can also, the community can already show that we can also use the free spacing range, free space range, which is you use different wavelengths, but they are in different free space range. And in this way, you can also use the same kernel to process different data simultaneously. So I will introduce this in the second slide. Then, so here, first of all, this is the work with the microring weighting bands from Princeton University. Then it will, they use the microrings as the kernel, and at the input, the wavelength is split because you reduce the wavelengths. And then the weighted addition at output is electrically submitted, but they do not really implement other parallelisms. And for the second one is they use the mode multiplexing and together with the wavelength multiplexing. And the principle, like the dimension of the parallelism is the same, and the operation are more or less the same. And the last one would be the one from Münster University and also Oxford University. They use the phase change material, and together with the space and also the wavelengths, and then with different color here, meaning the different free space range. So, but in this case, that the wavelength itself is not reduced. If you see in the input here, every wavelength is encoded into one pixels of the input. So there's no, for one wavelength, there's no other pixels encoded. So what if we can, what if we can reduce these wavelengths So this would be possible to open up another parallelism that we can use to accelerate the convolution processing. Then, so this goes to my research. So at the beginning, that this is the cross connect, as I showed you previously doing the iris power classification in the linear operation. Then actually this one can be also used for the convolutional processing. So by having the multiple wavelengths input in different FSR, then it can like demultiply into different SOAs. For different one SOAs can process many free wavelengths in different FSR. At the end, after demultiplying the FSR as the way, which is the same way as did here, then we can get the convolution weighted addition or summation at the detector here. So in this chip, there's already 8 units of kernels that we can use for parallel computing for the convolution processing. Then for further, so in this way, we are still use, for one element, it can only process 4 inputs. So the wavelength is not reused. And for the second one, we use the routing effect of the AWG. If we have the routing effect, cyclic routing effect, for the first input, that your output will be separated or demultiplied from the first wavelength to the last wavelength. For your second input, your wavelengths will be shifted in one number, and the last wavelengths will go to the first output. And for so forth and so on, then you will have one wavelength shift from the first input to the last input. So at the end, if you have the same AWG or multiplexer at the output, then you can route back all these wavelengths one to another to form together the FS, like the same wavelengths in one output. So here for the input 1, all this signal will process by the SOA and then gathering by the output 1. So in this way, you have create n times routing of the wavelengths. So for every SOA that you can process n times more input signals. Okay, so this is also the I-coding schemes which we need to correspond, like create a connection from input to the output to the input laser wavelengths. And if we have four ports of this input routing for the routing AWG, then you will get 4 times higher acceleration, which for the I-coding you create from one FSR another FR to reuse of those FSRs. So you can create more times of operation for one element. So then we made a system simulation on system, which is creating the image from the means the digit classification, and we do the edge detection, and also we get the output. So we compare it with the electronics. So more or less the output is the representing the operation that we want, but we have some background on the picture because we have some noise from the SOA. So the SOA can be further optimized, or we use some other elements like the EAMs, or like absorption modulators to make these kernels. Then we do some digit classification which shows 83% of classification accuracy, which is can be further optimized by possibly by noise-wise training, and also by replacing better weighting elements. So we compare the acceleration factors from the previous state-of-the-art convolutional processor, then we can see that after reducing the wavelengths of 4 times, that we get 4 times of more operation. And if you increase the weighting elements number, then you can make far more acceleration of the operation. So in summarize that we, first of all, we propose the optical neural network that based on the indium phosphide platform to use the nonlinear function and also linear function together and co-integrate it on the same chip. And then we propose the additional parallelism for the convolutional neural network, convolutional processor, then which can be, this method can be used for accelerate up to like 16 times comparing to the state-of-the-art integrated circuits for the convolutional networks. Okay, please, thank you very much for your attention.
Thanks a lot, Ben. Any questions? Here, Ben, please.
Thank you for the nice presentation. Were those edge detection and classification, were those experimental results or theoretical results?
The second one is the simulation, which we used VPI photonics to do the simulation, including the SOA performance, either noise or anything.
Yeah. The SOAs are running in a linear regime?
Still in linear regime, because that would be the convolutional processing, so you need in the linear regime. For the first one, that would be the experimental results, that for the optical neural network using the SOA in linear regime and also in a linear regime.
So in that case, won't you run into a situation where you might cause the lasing in your chip because you're in the linear regime before the saturation?
So the saturation of the SOA that is roughly 5 to 8 dBm for the input power. Then we have an on-chip laser, which it can go up to that. And together with the input, you have multiple wavelengths input, so this also contribute the input power, which triggered.
And then your table showed 3 picojoule per Mach number.
Sorry, I do not hear.
Your table, power efficiency.
So for this one?
Yeah.
For this one, it's only the convolutional operation.
I think the number is very optimistic. I'm not sure how you got that.
So this is like based on every SOA, it consumes 35 milliwatt. So if we calculate respecting to the modulation speed right now is for every input, it is 10 gigasample per second. Then if we calculate from that number, that we can go down to 3.7 picojoule per minute. Sorry, if you include all the electronics for that? No, for this one, no. For this one, no.
Yeah, that probably gets.
No, if you are mentioning here the system engine, yeah, for the system and energy efficiency, it is already includes all the components, which we use the analyze inside the paper is using the state-of-the-art elements, the electronic elements. Yeah, this is the system, this is system energy. So it includes already all the parts that contribute here, like the DAC, the modulator, and also the laser, and also the SOAs, and also the photodetector. Then for, we use a number with the state-of-the-art electronics.
Sort of related question, just for my clarification. So these are for the processing a full image at the input, for example, in your convolutional network?
It is actually the capacity is still limited by how many wavelengths you have and how many elements you have. So if you see here that for the full picture, that you need to process the data would be like this volume. Then here would be in time domain. For every time slot, you can only process, for example, if you have 4 wavelengths and in 4 FSR and these 4 ports, then there would be 64 pixels. So this means if you have an image greater than 64 pixels, then you need to slide them into time domain. If you have the same as the inputs, then you can proceed in one shot.
Right, so that's what I'm trying to understand, if the measurements you give there in terms of efficiency, time, and also the ending conclusion that it's...
for the efficiency here is taking into account for every operation. So it's not related to how big the picture is.
But you would have to multiply by the number of, sliding windows through the image to compute the whole thing, right?
The sliding itself is only the connection from the input image to the lasers. Once you have this connection, then you don't need to change anymore. This is the defining the connection from one pixels of image to the laser. Mm-hmm. So this part you can just recognize, like neglect the time of the processing once you have the map. So after that, the time is only the modulation speed, and which you can take into account like 10 gigasample per second. Then for 10 gigasample per second, we have every element process 64 operations.
Okay. So first you map the image to that input layer somehow through this sliding operation, but then everything is happening in parallel?
Sorry, thank you. It's not that clear though.
I understand that there is a process that is not done in parallel, but it's done in sequence through the image, right? And is that only limited at the part where you're encoding the input, or?
Yeah, for the output you also need. This is the output. So if you want to reconstruct your output, you need this. But if you are thinking to the fully connected neural network, you don't need this because it's already flattened.
Mm-hmm. Right. Okay. Thank you. I might ask you some more later.
All right.
Okay. So since we are quite a bit off time, let's thank the speaker again. And let me welcome our next speaker, Professor Ben Wu from University of California, Davis, who has made a really long trip, actually around the globe, in order to be here. So he will talk to us about his work on brain-derived neuromorphic computing by 3D electronic photonic integrated circuits.
Okay, I hope my brain is working because my flight had a problem yesterday. I cannot find a mouse. Is there no mouse? Okay. I guess I can use this one.
Let me turn it to the laser.
I think this is working.
Because it's in Greek.
Aha. Okay, great. All right, thank you very much. Thanks for the opportunity. It's great to be in Greece, Athens, beautiful town. My name is Ben Yu, and we'll talk about the brain-derived neuromorphic computing by 3D electronic photonic integrated circuits. We recently started a center or a project called Explorer, and I have 10 collaborators, including, where did it go? Volker, where are you? Oh, just went out. Okay, they're very good-looking Volker. He is our co-PI. Program. We have Stanford, Berkeley, George Washington University, now University of Florida, MIT collaborators. So let me see here. Let's go to the next slide. Okay, well, when we take a look at this slide, we know that the amount of energy that we've been consuming on the training the system, AI system, have been doubling almost at the Moore's rate, doubling every 2 years. But then more recently, it has been going up, doubling every 3.4 months, And then for the larger system, doubling about the 7.1 month. And usually people get really excited about it and say, gosh, this is really that time to really get into AI. But it's actually a bad news, because what people are doing is to train a dumb system in a very dumb way with a big deep neural network, with a dense deep neural network. So if at this pace, right now, we are already consuming 10 to the 26 flop, 100 iota flop of energy. So on an exaflop system, it will take 100 million seconds to train a system. Deep neural network works very well, especially when it's fully connected, but it's dumb. That's why you're using the reinforcement learning or the supervised learning to train it. And typical system costs about $3 million of energy just for the energy itself, not the hardware. And GPT-3 has 175 billion parameters, costing $12 million to train. And GPT-4 has trillion parameters, and it's known to have much more than $100 million worth of energy, according to Sam Altman, just for single training. So we need to have much more scalable and much more energy efficient hardware with self-learning algorithms and less data movements. So this is kind of the background behind why we should do more than bio-inspired, we should do bio-derived, brain-derived, because not only can you think about energy efficient system for inference, you can actually think about energy efficient training and much more adaptive and flexible system beyond the special purpose computing and so on. So if you look at human brain, as previous speakers had talked quite a bit about 20,000 ATP, that's about 1 femtojoule per bit for energy transmission. Depending on the distance, about 50 femtojoule to 500 femtojoule per bit. What's amazing is that each neuron is on the average talking to another 8,000 other neurons, and 100 billion neurons talking to 1,000 trillion synaptic connections. You should be really excited about this number, because if you are having a fully connected 100 billion neurons, then you'll have to have 100 billion square synapses. But 1,000 trillion means instead of 100 billion square, 10 to the 22, you have 10 to the 15, you have 7 orders of sparsity. So your human brain is very sparse, and with the connectivity and so on, and it does work amazingly well. If your human brain is fully connected, you should be consuming like 20 megawatts, but it's consuming 20 watts, and it does very amazingly good cognitive, adaptive, flexible learning capabilities. Beyond that, human brain is, there's a consciousness, right? There's a lot of this flexible learning and so on. People think it's coming from the structured intelligence, highly interconnected hierarchical learning system with modularity and, as I said, flexible and adaptive learning. And because of all these mechanisms and so on, it has energy efficiency and scalability. So just kind of quickly summarize why we are looking at brain-derived rather than brain-inspired. Just kind of, if we were to design a neuromorphic system, what we like to do is kind of consider self-supervised learning. So instead of having to be trained and be reinforced by falling off a cliff and then say, ouch, I should never do it again, you can imagine falling off of a cliff and predict, even before you experience it, learn how not to do it. So that's predictive error-driven learning. And then once you learn something, if you know how to play ping pong, maybe you can play tennis much better. And your system has amazing abstraction capability. In a human eye, you have billions of sensing opportunities, but then by the time it gets to your cortex, say V1, V2, V3, V4, and so on, you have 10 to the 5 to 1 abstraction. So you actually do not have to respond to every one of those 100 million bit per second type of information coming in and all that. Again, the ChatGPT 4 and 5 are already approaching at the level of human brain, but the interconnectivity is never there. Your CMOS is connecting northeast, west, south. You don't have neuron connecting to 8,000 others. The interconnectivity is amazingly exciting, and the sparse connectivity. The sparse connectivity in time, space, and perhaps wavelength if you have wavelength system. The system has to be zero energy when you're not doing anything. If you're sleeping, you should be consuming almost zero energy. Event-driven system with a spike in time-dependent plasticity. Again, you want to use the sparsity in time, space, and wavelength domain. Hierarchical learning, your human brain is hierarchical in terms of learning. Maybe electronics learning and photonic learning can work together and pursue adaptive and flexible system. So we already have very good special purpose computing, for instance, matrix multiplier and so on with photonics. We want to go beyond that. We want to have a general purpose computing that can adapt and flexibly learn and then solve new problems creatively. So then modularity and structured reconfigurable system with plasticity, very important. If you look at the human brain, the neurons are very heterogeneous. You have thousands of different kinds of neurons interconnect together with a very different kind of synapses. And that actually helps creating some really amazing kind of geniuses can be born and so on. And what fires together can wire together, that contrastive Hebbian learning at kind of more local level, working above hierarchical and self-supervised learning, it's exciting. And the system, whether it's a biological system or maybe a photonic electronic system, we want to go toward 3D integration of nanoscale components. So we kind of look back, we have many decades of neuromorphic computing activities. We can group into three different categories, right? CMOS, typically digital CMOS. And then you have analog electronics that has wiring, crossbar. You have a fully connected crossbar, and you have a wiring problem, right? And then you have more recently a lot of these photonic components that are photonic systems that are more on the convolutional or matrix multiplier, more specific, special purpose, not general purpose. So what we observe here is that there are really 4 gaps in neural computing that has been going on in the past 5 decades. We're relying typically on CMOS, but even without CMOS, we're not using the new devices, new materials, new systems in a way that it exploits the dynamicism. The material has to be dynamic, just like in neurons and so on. So lack of methods to utilize biorealistic computing elements and learning algorithms, lack of next generation bioinspired materials with neuromorphic dynamics, dynamicity again, lack of innovative circuits to serve as required computing systems. And once we have those things, how would you scale it to a large scaling architecture that can exploit the mechanism of all this learning and so on? So we started this new center called Explorer, and then we have another one coming up, which is quite exciting. And expedition in brain-derived neuromorphic computing with intelligent photonic and electronic materials. It's about a 30-page of proposal. I will be able to only talk part of it, but very quickly, there are 4 observations that come from those 4 gaps. One is the fact that the noise, the previous speaker talked about noise. What's amazing in human brain is that you look at this noise and somehow the human brain looks at this noise and figure out a big picture, and this noise actually helps you come with a more global solution instead of being trapped at the local optimum. So somehow you can figure out good noise versus bad noise and so on. And that is entropy and so on is becoming kind of solving the problems that are ubiquitous. Secondly, the dynamics of the intelligent synaptic photonic electron materials, and perhaps we can build this new model, a new algorithm, a new dynamic behavior-based system. Third is based on the dynamic materials and so on, we can come up with a new photonic electronic ionic device and circuits in 3D. And lastly, we need to co-design, co-integrate this integrated intelligent synaptic materials, device, and circuits, an architecture algorithm to realize innovative 3D hierarchical photonic integrated circuits. So that's kind of our center direction. And we just started maybe about 9 months ago, and we have quite a bit of new things that are coming out step by step. Again, just to summarize, human brains are amazingly great, exciting. But CMOS has been has a limited dynamicity, but also, even if your transistor may be about femtojoule per bit type of transistor, as soon as you start to communicate across the silicon chip or between chip to chip, you start to consume 2 picojoule or repeated 3 picojoule per bit, or if you go to external chip, can be 10, 20 picojoule per bit. So those wires are a problem. And each transistor is connected east, west, northwest, but not really 8,000. And the offline training in this case, and so on. The electronics also come with a lot of thermal noise. And then when you look at the photonic electronic together, you can actually think about best of both worlds system. And you can exploit the photonic parallelism. And waveguides can be basically 1 dB per centimeter or 1 dB per meter, depending on what you use. It's considered to be independent of distance compared to the electronics. And we're going to talk about this 10 femtojoule per bit system. They can have 8,000 and so on. Now, optical devices are bidirectional, even though your neurons and axons are unidirectional. So on the bidirectional waveguide, you can actually exploit forward and backward propagation learning. Self-propagation can be possible. There's no thermal noise, so to speak, in waveguides, so you can have short noise limited system. Typically, what you see in the CMOS system is that you may have a very good CMOS chips, but to come to a global solution, you have to have a barrier synchronization, which is something difficult, and people at Intel talk about this difficulty all the time, whereas in optical, the barrier synchronization can be done much faster. Sparse processing, overcoming the locality in data, and 3D photonic electronic integrated circuits that can build a system that can exploit the density of electronics as well as the parallelism of photonics. So our kind of starting point is the neuron. And if you have a transistor, as I said, the transistor can be 100 attojoule transistor, but as soon as you go electrical wire in and out, there's a problem. But how about if you have photonic input, photonic output, but photonic transistor, where the engine itself is an electronic transistor, whereas the input can be optical and output can be optical. Basically, you put nano detector with the transistor and nano laser with the output of the transistor. So, the David Miller, who's part of our center, said that if you have a 1 femtofarad transistor gate, and if you have a 1 femtojoule of photon coming in, then you can actually create the 1 volt across that capacitor, which can be driving the gate of the transistor itself. Therefore, you can actually have a repeater based on 1 femtojoule per bit. In fact, you can actually get it down to 0.1 femtojoule per bit. Then you can actually put the laser, and typically lasers have 30% efficiency, and people may say, gosh, that's terrible, 30% is a very bad efficiency. But that is losing 70% of 1 femtojoule or 0.1 femtojoule is much better than having to consume many picojoule of bits for communication. So you can think of 1 femtojoule per bit system, or say 10 femtojoule per system for 19 dB, which is about 80x fan-out. You can think about 8,000 fan-out for some tens or maybe 100 femtojoule type of transistor that can actually be done all based on optical, and 8,000 can be consumed in, say, 100 wavelength and 80 wires and so on. So let's say you have those type of photonic transistor. You have inputs coming in from, say, 8,000 other neurons on the average. You can have leaky integrated fire. In fact, we use Ishikawa's model and then trigger the laser to be turned on. And because we're using spiking electronics instead of some known physical mechanism, you have all kinds of tailoring mechanisms. You can actually tailor your neurons in many different ways. In fact, this actually can give you heterogeneity in your transistor. So you have spiking pulses coming in from different neurons, and the spiking electronics will handle the output of the spiking with the detector and the laser at the output, the laser or the LED. Now, the idea behind the neuromorphic computing with the neurons and so on is not new. About 20-some years ago, Ishikawa has come up with the model that emulates 128 different kinds of mammal neuron behavior. And by using just 2 equations and 2 variables and several parameters, he was able to explain basically or replicate every one of these neuron behaviors. So then my student actually looked at this and said, how about if we do the same thing with the transistors and detectors and lasers and create the Verilog A model and use 2 equations, in this case voltage and current, and R and C, the basically transistor circuits and so on, and was able to come up with a circuit that would actually bring in optical input and optical output with, say, excitatory and inhibitory input and output on the VCSELs and so on. So this was kind of exciting. My students actually went ahead and put together transistors and detectors and so on from off-the-shelf elements, was able to do spike simulations and said, hey, blue spikes coming in, and then the yellow membrane potentials go up. At certain threshold, you will start to fire. The green spikes come out, and then the refractive potential will go up and down and get less tired, and they start to respond again and so on. So those are kind of the simulations that they came up with. My students came up with a SPICE model. And the experimental results were incredibly similar once they have put together circuits. And then they were also able to demonstrate that when you have inhibitory signal coming in, you could also suppress the output spikes, both in the SPICE model and the experimental demonstration. So our next step was to actually go from here to go ahead and build the foundry system. We actually make devices on our own, but also send out to foundry and put the photodetector with transistors and lasers or modulators. And then eventually, we want to go down to 3-5 nanometer system that can indeed have sub-femtojoule or sub-femtofarad capacitance on the FET with nanodetectors and nanolasers and so on. We're currently putting the lasers based on transfer printing. We're not quite there yet, but we have done quite a bit of experiments so far with the external lasers, in this case, VCSELs and so on. Now, once you have those neurons, you can put neurons in one layer and put, as spoken by a number of people, Mach-Zehnder-based photonic mesh that has the SVD type of capabilities here. This would be a kind of fully connected order of n square. If you have n by n, then you need at least n square number of Mach-Zehnders. And there's a lot of good theory, and Professor Miller has come up with a number of very good algorithms for us as well. And we put these things into, say, AIM photonics, active silicon photonics with the detectors and so on. We have bidirectional photodetectors to help us getting trained in forward inference and backward propagation. And then for using 45 CLO, we were able to use the on-chip CMOS that does the spiking electronics together with the TIA and detector and all of those components together. So this kind of our neurons. And here are our designs for quantum dot disk lasers, but in this experiment that we're going to show you later, we use the external VCSEL. So this is our circuit. So this is on 45 nanometer silicon CMOS with the photodetector and presumably laser, but then our laser is not working yet, so we have a VCSEL at the output. The detectors have the balance detector for excitatory and inhibitory input. I'm going to walk you through several parameters here. This V-leak membrane, so this neuron is programmable so that we can purposely make them heterogeneous if you have thousands of them or billions of them. So we can actually adjust these voltages to have each one of the neurons to behave differently. So this one has a leak voltage for membrane, meaning that if you increase the V-leak, the membrane potential will go down more quickly. Therefore, you will need more pulses to excite them and so on. And then V-bias, and the higher bias will allow you to have more output. And then threshold higher threshold means that you have to have more spikes absorbed so that you can start spiking. In fact, in this case, high voltage means lower threshold though. And then there's a V leakage for the refractory. If you have high leakage of refractory potential, that means that your transistor, your neurons will get tired very easily and so on. And then that functional, all of these things function together, we excite the VCSELs and get the output and so on. All right, so we have a version 1 and version 2. Version 1 just came out. We did some measurements, so we just kind of quickly looked at the membrane potentials and all that. And here in this circle, you see that pulses will disappear if we have the inhibitory pulses coming in. In our version 2, not in version 1, we put 3 different kinds of ion channels, potassium, sodium, and calcium. And this is the potassium ion channel model, but it's in V1. We don't have that yet. So V2 will come out around November, so hopefully we can report that sometime soon. I'm going to show you 3 different kinds of experiments. The first one would be to tune the threshold to show that our excitation input and output will change the behavior. So this is a standard setting to say high threshold setting. High threshold means that it will have fewer pulses coming out for the same input. The actual voltage is actually low. And then in the other case, low threshold means with threshold high, you actually have more pulses coming out because it's more sensitive, so to speak. So that's first experiment. The second experiment would be to change the bias. If you change the bias, if you put the bias higher, then you actually see the neurons to be more prone to give out pulses. So if you have V bias low, then you have fewer pulses coming out. And if you have V bias high, then you have more pulses coming out. Lastly, if you change the leakage membrane potential, as I said, if you set the leakage to be low, the membrane potential will be staying high. Therefore, once the pulses come in, you continue to set the pulses going out. Oh, there's actually one more experiment. Refractive period, if you set the refractive potential to be low, that means that the refractive potential will actually stay at a higher level, which means it gets tired very easily. So for the given pulses, it gets tired and gives them one pulse and get tired, one pulse get tired. So even if you have excitation here, there's no response here and so on. And then you can actually have excitatory input and inhibitory input. If you have excitatory input only, as you have shown earlier, you see these pulses coming out. But if you put excitatory and inhibitory together, you see that what used to be 3 pulses become 2 pulses because the coincidental input at inhibitory input with the excitatory will suppress the pulse coming out. So this neuron is completely programmable, and we were able to kind of play with these things. You can see my students playing with those inputs here. The first experiment will be to go from standard threshold to low, and if you set the V threshold higher, you will see more spikes are coming out. And then even higher threshold setting will have even more pulses coming out because the threshold itself is getting lower and so on. Okay, so that's kind of the experiment. Now we're going to show the next experiment. We're going to set the leakage membrane to be lowered. So then once the leakage is lower, then you have membrane potential that's so easy to go out, so you have so many pulses coming out. The third experiment would be to change the refractive period. So then because you made the refractive be lower, so then you get tired. Your neuron gets tired easily. It does not recover easily. So even if you have pulse coming in, neuron is so tired it does not really respond. So you can actually show that we were able to show the programmability of the neuron. The other thing that we looked at was to actually have the cascadability of the neuron or the neural network with the MZI mesh. Here you have pulses coming in from, say, 2 different neurons. You can actually send the pulses to excitatory only or excitatory inhibitory together and so on. So let's show the experiment here. My student has set the MZI. In this case, the pulses are going in only to excitatory, input 1 to excitatory. Now, input 1 and 2 both going to x-trajectory is interesting because MCI by itself is a unitary, so actually you have pulses that are normalized. But even if it's normalized, you have more pulses coming in, so you have more pulses going out there at the output. Last experiment is to have x-trajectory and in-between together. You will see that when the spikes coming in and in-between coincidentally, then you actually shut off the output. So you actually see that fewer pulses going out. Okay, now I did promise to you that I'm going to talk about the scalability. So you need to have sparsity here, and we're going to talk about the 3D integration and so on. So as I mentioned, if you have an n by n neural network, you will have to have n square synapses and so on. That will be a ballooning. It's a huge problem. But if you use the tensor train decomposition, like in a human brain, you can actually decompose the big tensor into many small tensor components that are multiplied together. And if you have additional dimension, that really helps. And in my student simulation for 1,000 by 1,000, as I pointed out earlier, 1,000 by 1,000, well, n, it will scale up at n square, but in this case, we're able to actually reduce the number of synapses by 582. So instead of n square, we have, for the 1,000 by 1,000, we have 582 fewer number of MGIs. It actually corresponds to about 171 dB lower insertion loss if the MGI were to be losing 0.2 dB per stage. So it's a huge, huge advantage. And human brain works like that anyways, the sparsity and so on. I mentioned that additional degree of freedom helps you. And in this case, we use the wavelength to be the additional degree of freedom to do decomposition. So with many small 8 by 8 MZI with multiple wavelength allows us to reduce the number of synapses by a factor of 582. So instead of 1 million for the 1,000 by 1,000, we're able to do 1 million divided by 582 MZI just to achieve the same type of sparse tensor decomposition. So we actually fabricated 16 by 16. We're about to put this together to create the 1,000 by 1,000 neural network. And to do this, we're doing a lot of things in 3D integration as well. So I myself went into clean them with a 300-meter wafer with my students. And what we're doing is the previous speaker talked about the polymer-based stuff. We're doing this 3D integration with silicon. So let's say imagine that you have a silicon CMOS photonics with the CMOS and silicon together with photonics. You're going to stack them layer by layer, I mean plane by plane, each plane having multiple layers. But you need a photonic component that will bring the light up and down. And that is the silicon waveguide, the amorphous silicon waveguide. And what we did was to create the silicon etching with the 110 crystal domain with the anisotropic etching and with the wafer bonding, and created this U-shape or S-shape or the northeast-west based layer-to-layer interconnection. So typically we expect to have 100 wavelengths and maybe 8 of them to achieve 8,000 interconnection per neuron. And then here, if you have such a neural network in each plane with the CMOS and silicon photonics, and you stack them, and then you may actually have a non-volatile memory on top to help the process. But the point here is, though, you can have scalable system that can be module by module. And just like in human brain, you can have a structure, intelligence, and so on. I'm just about to be kicked out, so I'm just going to show 2 more slides and get kicked out, I guess. Benchmarking, very important. Typical benchmarking talks about throughput and the throughput per area. So those are 2 of them. We have about 1 million times better throughput than the GPU. And also, if you normalize per square millimeter, it's about the same. So then the figure of merit is about the same. These are actually currently not the best. We're trying to come up with a better benchmarking because it's just for inference. More important is the trainability and so on. I don't have time to talk about learning algorithm, but self-learning and hierarchical learning, continuous learning, transfer learning, very important. Just to summarize, our silicon photonic-based CMOS and brain-derived instead of brain-inspired computing allows us to look into best of both worlds mechanisms and so on. We're looking at hierarchical, optical, electrical parallelism, utilizing all the good things from both optical and electrical. And I acknowledge my group members and our new center, the 10 members of our team. And just like the previous speaker this morning, we're hiring as well. We're always hiring. So hopefully many of you can start to work with us and work on this really exciting adventure. Thanks so much for your attention.
Thank you very much, Ben. So let's pick up 2 questions, I would say, since we're quite over time. Lorenzo?
Thank you for the nice talk. So in your brain model, you are considering only neurons. However, nowadays there is a huge consensus in the neuroscience community that in the brain, we have also glial cells that are play a significant role in the learning process, in long-term memories and things like that. So how do you plan to integrate in your model a glial cell?
Okay.
Like astrocyte and so on and so forth.
I think the question is the learning and neuron and perhaps synapses, the model.
Neurons is too simplified. Considering that in the brain we only have neurons.
Right.
Is a too simplified model of our brain? Because nowadays there is a huge consensus in the neuroscience community that the brain has also glial cells like astrocyte or other sort of cells that are playing
Exactly.
a significant role in.
So what's their function actually, if I may ask? Like what is the function of those cells?
That's a good question. So
Yeah.
studying. No. There are a huge experiment on that. People are studying and they're considering that those cells serve for stabilized memories. So they are really active in long-term potentiation because they do provide proteins to the synapses in order to strengthen the synapses itself. So without those cells, so these memories are no longer stored for a long time. So, but this is something that is actually in the biology consideration and treatment of the brain is really an emerging topic.
Right. Okay, so I think there's, at the beginning, I mentioned that this Explorer Center has so much things going on. I can only talk limited amount here, but everything you talked about is being studied in our center. So I did not talk about dendrite computing. I did not talk about how the synapses are formed and how the ion channels are. So we're putting everything in it. In fact, Professor Sorgar is putting some photonic synapses and so on. To answer your question, though, as I pointed out, our neuron has very brain-derived, really biorealistic, bioplausible neurons. We haven't got to talk much about our synapses. Our colleagues at MIT and also Volker are looking at brain-realistic, bioplausible synapses with actual dynamicity and so on. So how the spikes will behave, interact with synapses, almost like the way the ion channel is working between the synapses and so on. That's one of the reasons why our collaborator here, the Professor Alberto Saleo, is working on the polymer-based ionics as well. So we're trying to copy everything. So because the human brain has gone through billions of years of evolution, and it has optimized itself through the evolution, and we're trying to kind of have a brain-derived system instead of trying to do something just inspired. So I hope that answers your question. I'm happy to talk more about these things in addition. Yeah.
Any more? Yeah, please, Adria.
So thanks for the impressive presentation. So my question is about 3D integration. So how 3D you can go? Because I suppose this requires like the silicon chip you show, in 3D requires a lot of 2D lithography, mask, alignment, and everything. So how large you can go, and how long it takes in terms of fabrication?
I think microphone is doing more distortion than good things, but so I think there are people who are offline, so I think it helps you. But can you speak without a microphone?
Yeah, sure. It's a question about the 3D photonic integration.
Right.
About silicon photonic. So how 3D you can go, how high you can go.
Oh, okay, good point. So the 3D, the question was about the 3D interconnect with the polysilicon. How far up can you go? We're working on several different kinds of optical TSV. This type, we're trying to make it single mode waveguide all the way up. And what we're doing is that we are using silicon on insulator base that typically about 10 to 20 micron is good enough. So we have demonstrated 10 micron polysilicon based waveguide. What you have to be careful about is how to make a via. Typically, you can get 20:1 type of aspect ratio, and you have to make sure that it's kind of staying single-moded. We are also looking at not just silicon, but silicon nitride and other devices that will be more tolerant to the size of the waveguide. This one is about 300 nanometer by 500 nanometer at the 1.5 micron to go up, and we're able to make the 45-degree mirror. We can demonstrate 1 dB loss from layer to layer. But 10 micron, 20 micron, there's actually not much difference in terms of optical loss. But if we have to go, say, millimeter, then maybe we have to use your 3D polymer waveguide.
Okay, since we have now the coffee break and they're quite well over time, I would suggest to take any further questions offline. And let's thank the speaker again.
Okay.
And let's have a 20-minute break instead of 30, so as to not delay too much after 6.
this one.
Yeah, exactly.
Shall we start? Yeah. So welcome to the last session of this exciting workshop. With title, the section title is Applications of Photonic Accelerators, while the first talk will be given by Junsang Lee from University of Oxford, from Haris Baskaran's group. And the title is Integrated Photonic Processor for Neuromorphic Computing and Beyond. Please.
Okay. Good afternoon, everyone. My name is Junsang Lee, Jason Lee. I'm from Haris Baskaran's group at the University of Oxford. Yeah, first of all, apologies that this talk was supposed to be made by my supervisor, Harish, but he could not make it today, so I will try to speak on behalf of him. So today I'm going to talk about some of our recent work on integrated photonic components and processors in neuromorphic computing applications. As we have seen a lot of many interesting introduction why we need some new forms of photonic computing, I think we already seen this slide too. The current estimates are that we are requiring around 845 exabytes per year by 2025. And this has driven the huge surge in interest towards new forms of computing, not just photonic computing, but in-memory electronic computing or any other different kinds of computational nodes towards artificial intelligence. With rapid growth in this area, there have been a lot of different terminologies, and there was one paper summarized by Abu Sebastian, one of our collaborators from IBM. According to the paper, this AI is a catch-all term that reflects some sort of mammalian brain intelligence. And then within the subset, there's a machine learning, which is effectively learning without explicitly programming. And there's a further subset, which is a deep learning that is effectively many layers of neural network, many layers of filtering that does image recognition and so on. However, most of these are relying on the CPUs, GPUs, or some specialized FPGAs, which mostly are von Neumann architecture. This von Neumann architecture has a memory and processing unit separately. That's why you always need the shuttling of data between this memory and processing units each time when you want to retrieve the data in and out. So this decreases the efficiency. Talking about the efficiency, we might know this picture, the match between AlphaGo against Lee et al. A few years ago, and then we see how efficient this AlphaGo was because it could beat human many times in this intellectual sports game. However, what people usually underestimate is the AlphaGo requires millions of power from the clouds behind, while Lee et al. Just needed a cup of coffee to let his brain function, which is less than 20 watts. So it is really true that we have to implement the right hardware that can leverage the functionality alongside the huge development in this artificial intelligence that is efficient not just in size or processing functionality, but in energy at the same time. Yeah, so this slide again emphasizes the memory wall, where you see the processor power has been increasing 52% annually. However, your memory has been only increasing by 7%. So there's a huge performance gap, which actually makes this bottleneck in the computing efficiency. So the solution of them is to co-locate your memory and processor units at the same location using the accumulative memories, and this is where the whole idea of in-memory computing is coming. So this can be done by many different kinds of approaches, and is similar to any brain analog synaptics, where these fundamental in-memory computing units can be done by, here we have examples of spin torque oscillators, or phase-change materials, which I'm going to talk about for the rest of this presentation, where the idea is exactly the same, that their in-memory computing unit process and stores the information at the same time so that we can bypass this von Neumann bottleneck issue. However, most of these in-memory computing has been started in electronic domain, but we're at the photonics group, so we of course think which platform would be better between electronics and photonics. While photonics, of course, is better in some aspect in terms of large bandwidths because it has a different wavelengths, polarizations, and in some cases angular momentum, which all of them are multiplexing parameters that you can process your information in parallel over this spectral domain. So it definitely offers a faster communication speed. However, in some cases, photonic is not as good because, as we know, the photonic components are usually bulky. In free space optics, all of these lens components in our microscope or these lenses that these cameramen need to carry are often diffraction limited. And then, so it's much bigger than any other electronic components that we usually deal with in our transistor and the PCB board, so on. So we can make them into small, like integrated photonics. So we can make them into nice photonic arrays. However, still, this requires a lot of electrical modulation, analog digital conversion, a lot of photodetectors that we use that occupies a whole optical table to run these small metrics. Of course, there are a lot of different ways to do the compact photonic packaging. However, this is still true that electronic counterpart is still needed to run some photonic network. So the idea is we do both. We do photonics for the larger data communication, but we also use electronics to program something in a very small device footprint. So to leverage both functionalities in both domains, we need a good material, some functional material in both domains, so we use phase change material. So phase change material is a reconfigurable material that changes its electrical and optical properties depending on its crystalline phases between amorphous and crystalline states. This material has been here for long enough. It already has a lot of low-value applications too. For example, it's been used in optical DVD, CD rewritable disk because the most common phase change material here, GST, has a large optical contrast between amorphous and crystalline phases in both real and imaginary part of its optical index. So we can use this to store its data in an optical domain. But also we use this for electrical data storage. There is a commercialized product from Intel where this phase change material is connected between two electrodes, and we let the current through this PCM, and PCM forms a conductive channel between low conductive amorphous and high conductive crystalline states. So by letting the current through this active material, we can use this for electrical data storage. So yeah, our group works on this phase change material in different platforms. So with that, I would like to outline some of our recent work. So I will start with all optical phase change platform first. So we developed the first phase change photonic memories quite a while ago by our former student Carlos by depositing phase change GST material on the top of the electric waveguide. And when the light goes through it, this light gets evanescently coupled by this lossy GST. And as I said, this optical constant changes depending on the crystalline phases of this material, so we can encode the optical information by attenuating our transmission by this lossy state of this material. So here, in amorphous state, our optical transmission is high, and in crystalline state, it gets mostly attenuated, so we can control the amplitude of the optical transmission. And most of this phase change material can be switched back and forth by using any energetic pulses that can induce the melt quenching mechanism. And in this case, we can send another optical pulse into the same dielectric waveguide that goes through this GST layer, and then this optical pulse can switch this back and forth, and by controlling that pulse parameters delicately, we can also form the multi-levels between 0 and 1. So after this, we decided to look further into it, how many different levels can we obtain using this single phase change photonic memory. And this was done by our former student and former postdoc Xuan and Nathan, where we controlled the pulse duration and pulse power effectively to control the fraction of how much phase change material is switched within a single PCM cell, so that we could eventually achieve 5-bit 32 different levels of photonic data storage in a very robust manner. So after figuring out this, we started to do some computing. So we showed the in-memory computing, simple direct multiplication first. So here, in this case, we use a fraction of how much phase-changing material is switched as a multiplicand of the scalar multiplication process. So you see here the input B, optical intensity of input B is coming in, and it gets multiplied by A, which is a weighting coefficient which was pre-programmed by optical pulses to switch certain fraction of PCM within the single PCM cell. And this gives a total output of C. So we can get optical scalar multiplications. And we can extend this further. For example, here we can put two different phase-changing materials in G11 and G12. And then input of light is coming in from each direction. And then it gets multiplied by each weighting coefficient, G11 and G12. And it can be simply added up using the combiner. So we can rate the added output, which is effectively matrix vector multiplication. So we can do multiplication, accumulation at the same time. And then we designed further. After that, we made the proper matrix, rows and columns, where the light is coming into each row of the dielectric waveguides, and it's optically guided into different directional couplers. And then phase-changing material is sitting on each node of this matrix. And then light gets attenuated by pre-programmed weighting coefficients, and then we eventually do the convolution edge detection here. But one important thing to note here is that we use wavelength division multiplexing, so we send the multiple different wavelengths into multiple different waveguides, so we can increase our computing efficiency by using this wavelengths domain. So we call this as a photonic tensor core, which can actually increase our computing density over potentially 162 TOPS per millimeter square for a silicon platform. So from here, we kind of know that for the development of either electrical or photonic accelerators, if you want to develop this functionality further, we usually need to explore the additional degrees of freedom. So here in photonics, we started from 0D, goes to 1D, 2D, and then we made a matrix. And then we now use the optical wavelengths as additional degrees of freedom. And then we only recently started to think further if there's another degrees of freedom we can harness at the same time. And we decided to use RF modulation. This was done by Boe, our current postdoc. So we use the same matrix, which can be multiplexed over space and optical wavelengths, but we also use a radio frequency. So because the radio frequency and optical frequency are quite far away from each other, so we can use them in a decoupled manner. So what we do is that we, instead of conventional digital data representation, we use a continuous time data representation. So we encode the amplitude information into different RF frequencies, and then we send them in multiple optical wavelengths into the matrix. So here is a brief picture of what we use. So we have a 3x3 matrix, and we send different RF signals with optical wavelengths, so WDM. And then we could do a synchronous convolution, which is ideal for higher dimensional synchronous convolution operation. Here we showed an example of a 100 clinical electrocardiogram operation. And this paper was only recently accepted. So we deal with these different kinds of photonic accelerators, photonic compounds, where most of them are very, very sensitive to fabrication. So we often use micro ring resonator, directional couplers. Even here we use MZIs, which are have a less fabrication tolerance. So recently what we have been also trying to do was, it was done by Nick, our current postdoc. We tried to, as a post-processing approach, we tried to optostructurally trim our photonic circuit in a very accurate manner. So here we use a polymer. So we deposit the polymer and we expose either UV or electron beam onto it. And depending on exposure of this beam, we can control the volume change of this polymer in a very high precision. So in this case, we can control you can see the height of our polymer according to the dosage exposure to our polymer. And then you can see different colors stacks can be formed because there's a Fabry parrot cavity having different polymer thickness. And then using this technique, what we thought of doing next is we put them onto the waveguide. So in this case, we can effectively control the effective refractive index of our mode propagation. So if you see, look at here, we put them onto the micro-ring resonator, and depending on the exposure of UV light in this case, we could actually shift our resonant wavelengths in a very accurate manner. So this can be useful for later on if you want to trim your photonic circuit in a large scale. So for example, we here developed 3 different micro-ring resonators. So 3 identical micro-ring resonators, but you see they are in a different random resonant peak positions, but we do 2 steps of optical trimming, then you can see they are all nicely positioned at each FSR of the micro-ring spectrum. So we can use this after fabrication to post-process and fine-tune our optical responses of photonic circuits. But since this shows a very good resolution in both X, Y, and Z dimension, we thought it could be also useful to useful for making 3D nanostructure. So maybe some of you can recognize this image. It's, I think, one of the Greek islands called Hydra. We try to make a 3D topography shaping using it. So we get the image of this, and then we discretize this topography into different energy levels, and we expose them, and we could make a good 3D nanostructure of this. So we think this can be useful for some other 3D complex nanostructure fabrication. Yeah, so far we've been looking at some sort of optical platforms of using phase change material for neuromorphic computing. But of course, as I said in the beginning, we wanted to interface this into electrical domain. Yeah, however, there's one fundamental problem in here, which is a scale issue. So most of our phase change photonics utilizes micron scales of phase change material on the top of the electric waveguide, so that light can effectively interact with our phase change cell. However, in electrical case, you only need less than 100 nanometer of phase change material, so that conductive channel can be just formed by a filamentary effect between 2 electrodes. So if we imagine we have an all-electrical system that's less than 100 nanometer, if you immerse that directly onto photonic waveguides, the optical contrast will be very negligible. So a few years ago, Nick and Nathan found a smart way of bypassing this by using plasmonic nanogap. In this case, we have a gold electrode, and light propagates through these gold electrodes, and then we have a phase change material between these electrodes. And in this case, due to the plasmonic enhancement, all of the optical field is strongly confined within this nanogap. So even the little change within the PCM, we can see the optical contrast readout. But interesting thing here is that this gold electrode is not just to confine the electric field, but it can work as an electrode that it can electrically program. So you can let the current going through between 2 electrodes, so we can also switch them using electrical current. So this shows the plasmonic nanogap that shows the first result of dual electrical and optical functionalities, so that light is going through this tapered waveguide, and then electric current is also going through between these 2 electrodes, and the phase change material is sitting in between. So we can electrically program, optically program, and also electrically monitor, and also optically monitor the readout. So this was the result. As you can see, we send the different optical pulses, and then we see there is a readout changing electrically. At the same time, we also send the electrical pulses, and then we see how it changes in optical readout. So it can be completely vice versa, and then we can have multi-level operations here too. And recently, Nick also found a way to improve this coupling efficiency more. So of course, if you want to make this system in a larger scale, we always think about the loss, but we use a gold here, so we can think that it's a very lossy system. However, the most of the loss is actually coming from the imperfect coupling to plasmonics here. So most of the light is reflected at the gold interfaces. So what Johan and Nick recently have done is they made the grating structure so that most of the light can be coupled within this plasmonic nanogap more effectively. So we can nearly switch within a few picojoules in this case. And even further, what we tried to do was that we were trying to use this metal electrode as an indirect heater. In this case, we can switch the overall area of PCM because we are now heating these whole metal electrodes effectively. So here you have a gold electrodes, and we are letting the current going through between these two gold electrodes so that it's used as a microheater that switches whole this phase-changing material, so it actually increases our optical contrast. So if you look at this table, this achieved a very, very low programming energy for both amorphization and crystallization technique. And then this was accepted recently in Advanced Sciences with, as you can see in the cover page. So inspired by this, also recently we used a microheater. In this case, we used not a metal, but doped silicon heater. So we embedded the doped silicon heater underneath the electric waveguide, and then we put the phase-changing material on the top of it. Again, we get the similar advantages, which is a very high contrast switching. Rather than we send optical pulses, electrical pulses, we are heating up the whole phase-changing material so that we can get the higher contrast here, so we could effectively build high-efficient dot product engine for some filtering operation. For the remaining of time, I would like to talk about the last bit of this presentation, where if we can achieve more benefits from photonic side, that we harness like different degrees of freedom in photonic domains. So I will say I will exploit different photonic bandwidths in updating neurons. So if I come back to this slide, even though we have this photonic matrix, it's usually if you want to update each phase change material differently, you have to move your optical illumination site to each individual phase change active element, so that you have a lot of time and effort are needed to program different active elements. So we are thinking of using different ways of doing it. So I'll just shortly, you know that we've been using a lot of techniques as a WDM for wavelength multiplexing and so on, but we haven't seen much of a polarization technique, so we never really use polarization to actively tune the material, especially in computing applications. And the main reason is that because there was no polarization selective device so far. So recently, I wanted to show that, I'll just skip the last slide, and I'll just show our recent work that we use phase change material in the nanowire, and then we illuminate the light from the top. And then it's not just a free space light, but we control the polarization of this free space light. So it's polarization modulated free space light. And in this case, because this silicon GST hybrid nanowire resonates only at certain polarization condition, we can actually use polarization to switch our active material differently. So for example, when the polarization angle is aligned well with our nanowire, it switches. If it's perpendicular, it does not switch. So we showed the result here. So we let the current go through this nanowire, and we're illuminating light from the top. And we see when it's only as polarized, the nanowire is getting switched in crystallization or amorphization process. And we can also rotate the polarization angle to achieve the multiple photonic memories here. Good thing about this is that we can put multiple nanowires together, and then in this case, we can use polarization as a selector of element. So here we have 3 different nanowires, nanowire A and nanowire B. In this case, we can choose polarization, to choose which nanowire to be switched. So here is the result. We have a nanowire A, B, and C, where the current is going through each nanowire, and we are illuminating light in the middle. And when negative 45 degrees of polarization is coming in, it switches nanowire A, while nanowire B isn't affected. And in the other case, it switches nanowire B, while nanowire A isn't affected. So you can do this multiple levels, and eventually we show this, we can use this for matrix vector multiplication as a proof of concept demonstration, so that nanowire A goes through 1 scalar multiplication, nanowire B goes through 2nd scalar multiplication, and it gets added up at 3rd nanowire by just measuring the total current output, so that we could actually achieve a simple demonstration of matrix vector multiplication, but importantly, we use the polarization as a tunable vector. And lastly, we wanted to, of course, do that into integrated photonic platform. So this was recently done between me and Nick, where we try to use a standing waves within the waveguide. So in the waveguide, we send the light from the two opposite directions, and then we make the standing waves within the waveguide. And then by changing the wavelengths of these standing waves, we can actually tune the spatial position of electric field of this standing wave from one to the other. So if we effectively put our nano antenna at one position, we can make one to be completely absorptive, which can be reconfigurable in phase change material, but the other one can be completely transparent. So we can make wavelength selective system similar to how we made polarization selective system in free space. So here is an experimental demonstration and simulation too, where we have so we use a ring resonator, and the light comes into the both sides of the input waveguide, and the standing wave is formed within the ring resonator, and we have a phase change nano antenna at the middle of this waveguide. And then in the lambda 2, most of the light is coupled with this nano antenna, but lambda 1, it's actually out of phase, so it's not interacting with it. So we put them here, and then we try to switch from crystalline amorphous to crystalline, and you see there is a transmission reduction at lambda 2, but lambda 1 is nearly stationary. So we see we can make lambda 2 reconfigurable, lambda 1 unaffected. And then, yeah, we optically program it too. So here we send the optical pulses in lambda 2, so you can reconfigure the optical states in lambda 2 while lambda 1 is unaffected, and same for the multi-level operations. And then at last part, we also try to put two nano antennas, so double nano antenna, while left nano antenna is subject to lambda 1, right one is interacted by lambda 2. So we can make multispectral modulation simultaneously, while two nano antennas are only 460 nanometer away from each other. So we can use lambda 1 pulses to switch one wavelength channel and lambda 2 to second wavelength channel. Yeah, I'll probably skip this, but we also wanted to mention that we use phase of light to optically control, to program different phase change material selectively. Yeah, with that, I would like to conclude that we are working on different phase change optoelectronic and nanophotonic platform for future computing applications that can be used both electrical or photonic domains, and at the same time, we wanted to exploit different degrees of freedom in photonics to increase the functionalities of our devices. Yeah, with that, I would like to thank our group members, collaborators, and funding sources, and I'm happy to take any question. Thank you.
Thank you, Jun-sang. Any question? Yeah, please.
Yeah, thank you very much for the nice talk. I have a question regarding the fabrication of the nanowire devices that you're showing over there. So, you just grow them epitaxially, and you put the contacts on top after that, or you kind of spread them on a sample?
It's actually, yeah, even though we call it nanowire, it's actually all lithographically made. So we just lithographically, we did a lithography, and we just spot her phase change material and silicon sequentially, and then, yeah, that's what we did.
And what are the maybe I missed that. What is the size of the nanowire?
So yeah, it's okay. I will show you. It's around 100 nanometer, 120 nanometer in width, and the length can be a 5 to 10 or 20 micrometer.
And if I make, are you also looking into working with nanowires which are grown by in a top or bottom-up approach, or?
Yeah, exactly. So actually, for that. But for in this application, the reason why we need nanowire is just to have a dielectric resonance within the nanowire. So as long as it has enough enough dielectric constant with low loss, it can effectively confine the light within it. So it's fine. But if we needed a higher quality factor of dielectric resonances, I think we need to definitely use a different approach. But in this case, the selectivity was good enough with using just a top-down approach here.
Hi. Yeah, sorry, I'll give it to you later. So a key purpose of your work is to do in-memory computing, right? There are these other approaches that you did briefly mention and somewhat compare, like phase change memory, but without using light, or resistive RAM. Some people, actually, there are startups that are getting tens of millions in funding where they use just SRAM, and they call that in-memory computing. Do you think that there's one of those directions that is the one to follow, or maybe either a specific type of in-memory computing for which your approach is better than others, or is there a clear answer to that, or not yet?
Yeah, I mean, that's exactly one of the purposes of this presentation, where I was trying to kind of show different ways, and we are not trying to say the photonic approach is always the best in this case. That's why we are always trying to explore different approaches at the same time. I think there are always pros and cons in different cases, but what we are trying to do is that it's not that we're trying to make everything imperfect, but we are trying to find the approach. For example, I think the Nick's plasmonic nanogap was very good to have a mixed mode and also energy efficiency. But if you want to scale up, still we have to find another solutions. Polarization nanowire, it's good that we've explored polarization for the first time as a tunable vector, but it's of course not as scalable if you think about energy consumption and everything. So I think at the end of it, we have to converge different aspects of it, but I think, yeah, that's a good point. But yeah, for now, I think we're trying to explore different domains and different functionalities and try to converge them at the end of it.
So is there a specific application in which these approaches that you showed are the best, in your opinion, of course?
I mean, I think, for example, depending on your application again, for example, our group is working on many different kinds of neuromorphic computing. For convolution neural network, I think what we are doing for matrix vector multiplication using the matrix, of course, that's most efficient now. But in our lab, even though I didn't show, we are working on associative learning. We are working on different kinds of spiking neural networks too. So it definitely depends on application that you're pursuing, I think.
Many thanks for this really interesting talk. Yeah. I have a question about the plasmonic nanogap with the PCM.
Yeah.
What have been the dimensions of this plasmonic slot, more or less, isn't it?
Dimension you said, right?
Yes, this is a plasmonic slot, more or less, that you are using, isn't it?
Yeah, it's around 50 nanometer.
The width?
Width, yeah.
And the length of the interaction?
So you can see from here, so actually it's within, I think, 100 nanometer region, where you can see that most of the plasmonic coupling is happening within this region, so with nanogap. You can see that it's, so within 100 nanometer, it happens, all this conversion and confinement.
Okay, so this is not really a propagating mode.
Mm-hmm.
So you excite some plasmons, mm-hmm. you get the effect, but more or less the loss that you get does not relate to plasmonic propagation losses, but mostly due to coupling from one waveguide to the other.
Yeah. I think it's mostly coupling. And it's more about confinement using plasmonic. It's not, I don't think it's actually, you're converting photon, plasmon back to photon, but it's more about you're confining your electric field within a narrowly spaced nanogap. I think that's the main purpose.
Okay, thank you.
Yeah. Okay. Another question from my side. Sure. How fast actually are the phase change materials, the reconfiguration time? Because sometimes we want to reconfigure the weights.
It's a very good question too. In our case, okay, depending on phase changing material, but most of the things that we work on, GST, for example, it's a few nanoseconds to amorphize, but 100 nanoseconds to crystallize. But there are a lot of other work nowadays on femtosecond region. They are trying to not use a melt quenching approaches, but try to use like bond dissociation techniques or something. Still, that's on a debate now. But in that case, we can go down to femtosecond region. So maybe gigahertz range, it's going to be possible.
Femtosecond? Huh?
Yeah. I mean, but yeah, not in this case, but that's what phase change community are also pursuing.
Yeah, very interesting. Yeah. Thank you. So let's thank the speaker again. And the next talk will be given by Professor Haris Mesaritakis from Aegean University with title Photonic Integrated Accelerators Based on Spectrotemporal Processing for Telecom and Machine Vision Applications.
Okay, thank you all for coming here. My talk, I'm going to present our common work from our joint lab between the University of Aegean and University of West Attica. And it's about an unconventional way to use photonics in order to do processing. So when I was trying to prepare the presentation, I didn't know how to start and what things to include or not, so I just asked an expert. So what should I include to this presentation? So the answer actually was quite accurate and said that I should discuss about accelerated processing units and hardware systems and ASICs for this job. I should talk about edge computing and the new landscape that emerges through these years. And of course, I should talk about quantum computing and neuromorphic computing. Fortunate for me, the two of the three projects that fund this workshop are evolving about quantum computing and neuromorphic computing, the Neoteric project and Prometheus project. So I said, okay, I will have some material to present about this. Then I asked the tricky question, should I include photonic neuromorphic computing or just neuromorphic computing? And the answer was not so encouraging. ChatGPT said that, okay, it's a really interesting area, but it's not really mature yet, and there are a lot of things that should be done in order to attract your audience. So in this context, I disagree a little bit. So what I'm going to do is just give a brief outline of the current computing challenges. I think that Professor Wu provided a really clear overview, so thanks for this. And I'm trying to put the photonics in the map and check a little bit about scalability. I think that Wim's presentation and Jose's presentation did this thing also really, really well. And the main part of my presentation will focus about technique, the recurrent optical spectrum slicing technique that we have devised and used. And I'm going to present some key application areas that can proliferate it from this neuromorphic paradigm. It will be about optical communication field and about machine vision and convolutional neural networks for machine vision applications. So I won't say a lot of things about this because you have seen them before. It's that the common trend during the last years is that the size of machine learning models become huge. There's an exponential increase. All these nice things, especially for our students that can copy things really fast and really efficiently, come at a cost that the size of these models become larger and larger. This expansion of the size comes, of course, with a significant expansion of the training time and how much effort and power we have to put into the systems in order to train them. On the other hand, if we examine a little bit the Moore's law and how the hardware, the typical digital processing units evolve, we can see that the rate that our requirement for machine learning application it's really, really high compared to our hardware systems. And the same can apply for the memory, meaning that the memory of the systems almost doubles every 2 years, but the parameter size of these models has an exploding growth. So we cannot even store these parameters. So there is a problem with storing these parameters. So what is the basic idea? The basic idea is that all these wonderful things underneath the hood is just massive linear algebra. So what we have to do is we have some inputs, and these inputs can be represented as a vector, and we have to provide them to some neurons, some nodes. So we have to generate a connectivity pattern, a connectivity matrix. So in reality, what we have to do is to do this multiplication. So all the neural networks that we currently use, most of them currently can be broken down to matrix value multiplications or MVMs. So in order to be efficient, these MVMs should be high speed. Should we consume low power in order to do them? And the hardware that we're going to use should in principle, have a limited footprint. So, photonics. All the presentations from the morning presented really nicely and expanded this field. What we can do with photonics. Photonics, at the start, they copy this MVM approach really, really efficiently, and they try to do it really, really fast and with a really low power consumption. So many approaches. The coherent way with the Mach-Zehnder interferometers and the meshes with the unitary matrix and the SVD approach that we discussed. Maybe scale to 3D and try to generate this 3D matrix and do the multiplications, or use phase-changing materials and different wavelengths and do this multiplication efficient. In its case, despite the merits, despite the great potential of its technique, there are hidden issues. And the biggest issue of all is scalability, meaning that for actual applications, the size of the matrix that you have to multiply is around 1,000 by 1,000. Professor Wu provided that they are building such a system. But in any case, building it is quite expensive, I presume, and it's quite hard. Or scaling up further is also something that is, let's say, not so easy from a technological point of view. So maybe we have to carve an alternative route. Maybe we have to see things a little bit differently. This different point of view has been provided many, many years ago, almost in 2003, and it's called reservoir computing. Reservoir computing, many of you are quite familiar with it. It's that you build, again, a neural network. You have your matrix multiplications, but with a slight difference. These weights that you have to apply do not need to be arbitrarily controlled. We don't have to have precise control over all these weights. They can be random. So the basic idea is that you have an input, you project this input to your connectivity matrix, the reservoir computing random core. There are complex interactions, so you generate a complex output at the output context, many, many outputs. And then you have to train only a small portion of your neural network, adapt the weights in order to get your answer. So if we see the basic computation for a reservoir computing system, it's quite similar. So the MVMs are preserved. But this matrix, WRC here, it's random. So it's easier to implement, easier to do. The photonic community rushed to the rescue because randomness, meaning that is quite forgiving from a hardware perspective. So many, many approaches have emerged during the last years about reservoir computing. It's using from IMEC and the reservoir computing with delay lines and splitters and combiners in integrated form. We have proposed with microring resonators and triggering the optical Kerr effect in order to trigger nonlinearity. There is the time-multiplexed reservoir computing, really nice work that you have virtual random nodes. And lately, Professor Psaltis also proposed that we could use projection to the free space and exploit the random mixing that occurs through a multimode waveguide in order to do these random linear combinations at the reservoir core. So there are a lot of efforts. So what we did, what is our contribution? Our contribution started from an early work of ours where we have microring resonators interconnected with waveguides in such a rectangular approach. We have some loopback connections connecting different nodes, and we use it like a reservoir. And in order to trigger the necessary nonlinearity of the system, we increase the optical power and we trigger some optical Kerr effect in order to trigger the nonlinearity. This design was not easy to fabricate. So we have made simulations, but in order to fabricate, it was not really easy. So a couple of years later, we devised a different approach. In this approach, we use a common loop. So we have a single loop now, and all the microring resonators are placed inside this loop. In this case, the fabrication is much more easy. We have a single input, but we can have multiple outputs because we can have add-drop microring resonators, so we can exploit all these different drop ports in order to acquire the signal. And there was another trick. The final trick is that this is the typical transfer function of a microring resonator acting like a notch filter. But if we phase modulated a signal, so there is a phase difference between the light injecting into the microring resonator and the light circulating inside the cavity, then this corresponds to a frequency detuning. So actually, if I phase modulate in my input, these phase modulations will correspond to amplitude modulations. So I will convert phase to amplitude in a nonlinear manner that we will follow the transfer function of the system. So this idea, we put it in practice and we checked it. And we see that if we change the phase response, the phase of the input, we could get this really nice nonlinear response at the power at the output of the system. The interesting thing here is that this type of nonlinearity is not power dependent. It has nothing to do with the signal's power, so we don't need to pump a lot of optical power into our device in order to trigger nonlinear effects. In order to confirm it, we did some toy tasks, really simple classification task, where we replaced our micro-ring resonator with simple waveguides. So we removed this nonlinearity, and we saw that when we remove the nonlinearity, we have a significant reduction in the classification accuracy of this really simple task. So the idea is, okay, we try to escalate the number of nodes. We say that, okay, we need more nodes in order to compute more complex tasks. But all these micro-ring resonators were at the same frequency. And by being in the same frequency, it means that the signal, by circulating inside this loop, was attenuating. So the losses were really high, and the signal-to-noise ratio at the output was really, really bad. So when we increased the nodes, we didn't get any performance improvement. So we devised a different strategy. We say that we will generate a loop that will contain only a single filter. And in this case, we have the filter, and we have a coupler, A and B. There are two couplers in order to inject and take out the signal. And we have a loop where we could adjust the phase and actually the attenuation. So it's like taking this approach and using a single microring in a loop and say that this is the node. And the second thing that we did is that for each filter, we placed it at a different portion of our spectrum, of our incoming spectrum. So we sliced it in a way so as that each node processed a specific part of the signal. This provided really nice results for some applications, for many applications. That's why we have patented alongside colleagues from IMEC and University of Ghent. And in order to understand a little bit, we can see the time response of the filter, assuming that it's a really simple bandpass filter. And we can see that the time response, of course, is complex, and it includes two main factors, the central frequency and the bandwidth. This means that if I shift the central frequency of my signal compared to of my filter compared to my signal, then it's like multiplying in time with complex weights that can change if I change this frequency. So it's a type of convolution of multiplication in the time domain with complex weights, not real value weights, that change when I shift my filter. The same idea has been provided by a similar idea by Francesco Daros's group in DTU, where he has filtered the signal and then sent into reservoir computing realized in software. So two similar ideas working in parallel. And we could see that the same effect can be achieved if we play around with the bandwidth. So if we change the bandwidth of the filter, we get these complex weights that we could tune them and change them. So in a way, this approach is quite similar to a reservoir computing because, okay, again, we multiply our signal with weights. In this case, the weights are complex, and they are not completely random, but let's say we have a coarse control over them. We can play around with some parameters, the bandwidth of the filter, the central frequency of the filter, and some parameters of the loop, the phase of the loop, and so on, but we cannot have an actual control of them. So in this perspective, it looks a lot like a reservoir computing. So we multiply, but we multiply with random weights, not fixed weights as in the approaches that we have seen mostly today. So the basic question, does it work? It sounds cool, but does it work? Does it provide any benefit? That's why we have, first of all, to devise the application area where we should apply such a scheme. So the typical playground for photonics is optical communication. Say, okay, let's see how these things can work in the optical communication domain. So especially Adonis, which is the telecom expert in the group, in the lab, he said that there is a strong pursuit for the 100 gigabit per second goal for different systems. So the question is how? Using coherent, using intensity modulation, using direct detection. The industry is struggling with these concepts to find the better solution. So there are a lot of solutions in order to increase the bandwidth. You can increase the analog bandwidth. You can use more complex modulation formats. You can go for more wavelengths and so on. So the basic questions that arise for this problem, such a high bit rate communication, is the high frequency components that are needed, the linearity of transceivers and the optoelectronic components, losses and non-linearities during transmission, and for the short reach especially we have dispersion and its combination with direct detection and the power fading effect. So we investigated a little bit the literature and we found that especially for the short reach, in order to go to the 100 gigabaud per second regime, one of the, let's say, more efficient solutions is to go for 100 gigabaud PAM4 signal. In such a modulation format, for such a scenario, maybe we are limited by two parameters, the linear impairments and the non-linear impairments. The linear impairments are the bandwidth limitation of devices and, of course, chromatic dispersion, where mainly the non-linear impairments are chromatic dispersion alongside direct detection, where we have destructive interference and we have these power fading effects that distort significantly the signal. So how does how typical this problem is addressed? You either use digital electronics, so like a feed-forward equalizer, but this gives you a limited reach, so you cannot go many kilometers, or you can use a more elaborate digital signal processing system, like the MLSD, and then you can go to 10 kilometers or more, but at the expense that this is quite power hungry and quite complicated in order to work with it. So the basic idea is what? Okay, can we answer the question that has arisen from the morning, photonics or electronics? So we try to answer again in a middle ground approach. See, not only photonics, not only electronics. So the key idea here is that if we can replace costly digital signal processing with a photonic accelerator, with a photonic preprocessor, that cannot work by itself, but uses a really lightweight electronic backend. So we thought that the optimum solution is to merge these two worlds and not rely only on analog computing, but merge analog computing and digital computing in the same platform. So what we did is that we did the simulations of the transmission for many kilometers with chromatic dispersions and so on. We did all these things. And after the transmission system, we detected the signal, the different symbols, we phase modulated the new carrier, and we injected to such a, let's say, photonic preprocessor. Not a really clever idea, because all these rings were located in the same spectral region. So what we got was not so fascinating results, but quite nice. So we saw that for a 24 gigabaud per second PAM4 signal, when we use 30 nodes, meaning 30 photodiodes, 30 ADCs, and so on, we could go to an HDFEC compatible performance for 45 kilometers. So there was a reach extension, but at a cost that we had huge amount of electronic components in order to detect this thing. And we say, okay, it's nice, but it's not really practical. So let's see how our slicing scheme works. In this case, we have only two nodes, two filters, not more, and these two filters are positioned at different parts of our signal. So we modulated a 112 gigabaud PAM4 signal. After the photonic preprocessing, we use a really lightweight FFE algorithm, the feed-forward equalizer, which is one of the most lightweight approaches in order to solve this task. And we compared what we could achieve with two simple filters. So with only two simple filters, we could achieve HDFEC compatible performance for 100 gigabaud signal for a distance of 70 kilometers, which is really, really high. It's quite beyond the state of the art of what exists. But all these are numerical simulations. So when we got the results, we were quite happy and said, maybe it's working, but we have to check. So what we did is just we tried to replicate this basic idea in the lab, doing an experiment, an actual experiment. So what we did is we use a laser source, we use an AWG with 64 gigasample per second rate, and we modulate it, and we assume a signal of 32 gigabaud PAM4. We couldn't go faster. We assume a 50 kilometers of transmission through, we did not assume, we did a 50 kilometer transmission, we amplified the signal, and because we didn't have such a photonic integrated nice circuit with a recurrent loop and the microring resonator, what we did is we just replaced it with a bandpass filter, a typical off-the-shelf bandpass filter with, if I'm not mistaken, with 26 gigahertz 3 dB bandwidth. So we sliced the signal. We positioned the filter, not the filter, we tuned the laser compared to the filter in order to provide a similar to the slicing effect. So we changed our input to position 1, 2, 3, 4, and 5. We recorded the output, and then we combined them offline using an FFE algorithm in order to do the correction. So what we got is that if we didn't do any filtering, the bit error rate performance is 90.8, 10 to the minus 2. So it's quite high for the 32 gigabaud signal. But if we use 5 filters, 5 different positions, we could go to 3.6, 10 to the minus 3. But imagine, we use the most lightweight algorithm available, the FFE, and what we used as a photonic preprocessor was just slice it at different locations using a simple filter. The performance is really interesting. It's not comparable to the numerical results, and that can be easily explained. The basic idea is that we have shown that if you don't have the recurrent connection, you don't get such a big performance boost. So it was anticipated not to reach the levels of the numerical simulations, but we proved the concept. We proved that this concept indeed works. By slicing the signal, we can reduce the bit error rate and do the equalization. The second application that we imagined for our system is actually if we can go to coherent modulation. So coherent is also really big. And in this context, in principle, we thought that we could achieve this because our system with the filters has this phase-to-amplitude conversion efficiency. So we could convert through the detuning phase variations to amplitude. So all the different symbols will be imprinted to the amplitude. So we could do this. So we tried it using, of course, numerical simulations. And in this case, we use a residual Carrier QAM system. So we have a constellation which is slightly shifted. So in order to, when we do the processing, to get different amplitudes for all the symbols. And in this case, we have used 3 filters, 3 photodiodes, 3 ADCs, and we have sent the results to either a really lightweight FFE or to a really lightweight RNN, recurrent neural network, in order to do the actual equalization. Numerical simulation proved that, yes, this can work as well. So slicing is a universal tool that can help direct detected signals and coherent signals as well. So really interesting results. Currently, we are doing some experiments on this, so we hope to get experimental results on this field as well. The second part, where many of you are also working on it, is do convolutional acceleration or convolutional processes. So in this regard, we also apply this concept, but we try to do this in an unconventional way. We didn't want to replicate the digital convolution process. So what we did is, first of all, we have somehow to transfer our input, our images, to the optical domain. So what we did, we have an image, there is a patch, and we can serialize this patch either horizontally or vertically, or in different orientations, make them serialize and send them to an amplitude modulation in order to send them to the nodes. And the nodes in this case are just our filters, where they apply different complex weights depending on their actual position. So you can see that if we inject the digit 3 at the output for 2 different spectral regimes, we can acquire different features. And at the output, we have used some photodiodes and, of course, some ADCs in order to digitize, again, the results. And the photodiodes in this case were set at a lower bandwidth. So in order to get the pixels, we multiplied and processed them through the filters, and afterwards, through the lower bandwidth of the photodiode, it's like averaging them in time. So we did an average pooling similar effect, similar to typical convolutional neural networks. So, and with ADC, we could change a little bit how we sampled, if we took many samples or if you undersampled and so on. At the back end, we preserve the digital computation. So we have a simple, fully connected neural network in order to do the final training and the final classification. In order to do this, we have used numerical simulations. We have used, in collaboration with Ipronics, the smart light emulation in order to get a more physical related result. We have used off-the-shelf filters, similar to the telecom case. And in a few weeks, we are waiting for the chips, the actual photonic integrated chips, in order to test the same ideas on the devices themselves. And for the data set, we have used the NIST, and we have used some biomedical related data that we have acquired in the lab, so we could detect the moving particles really fast through a neuromorphic camera, and we could classify them using this approach. I try to speed up a little bit, so just to provide the basic idea. So for the NIST dataset, what we saw is that if you just take your image, serialize it, and send it to a fully connected layer, the performance that you get is around 92%, the accuracy that you can achieve. Just send the image to a fully connected layer. If we pre-process it in the optical domain using 10 passive filters that do not use any power at all, then send it to a fully connected, where at the same time we average our pixels, so we generate fewer samples for the fully connected, we could escalate performance to 97.6. So we get a performance increase by 5.5% in accuracy, while at the same time we reduce the number of samples that we provide to the fully connected layer, meaning that we accelerate also the digital processing process. And in order to compare it a little bit, what we did is say that in our case, the optical slicing, we do the convolution in the analog domain. So we get a 97.6% with no power consumption. And for the digital part, the number of flops that we have to do is 14,000. If we go to the LeNet5, which is a fully digital convolutional neural network, and we have all the different convolutional neurons in place, it goes to 98.9% of accuracy, but the number of parameters that it uses is 700,000. So we get a minor reduction compared to really sophisticated CNN systems, but we get a massive reduction in the number of parameters we have to train. We have published these results, and to speed it up, we tried again with more physically accurate systems. So we did the same thing, but now using Ipronics platform. So we do, again, the NIST classification dataset. We try to solve things, but we use the emulation, which is physically accurate. It includes losses, thermal noise, shot noise for the photo detection, everything. So in this case, we saw that we could, we generated micro-ring resonators using programmable units from the system, and the accuracy that we could achieve was around 96.7. So we only lost 1% of accuracy. We preserved all the benefits in terms of computation due to the losses of the system and the constraints of the actual system. And finally, we did the same thing using an actual experiment. So we use an 8 gigasample AWG. We did the same thing, as I mentioned before. And instead of a recurrent optical spectrum slicing, photonic integrated circuit, and so on, we have used a simple bandpass filter as in the telecom case. So what we saw again is that performance could scale up to 97% if we use 2 filter positions and different orientations at the input, confirming that this indeed is working and slicing can provide acceleration for our signal. So probably yes. So the final part is that we have also tested it using microfluidic systems and actually monitoring of microparticles moving around with a new data set more realistic. And we could again achieve a huge performance boost as well. So to conclude, First of all, welcome to Greece, everyone. And I hope that this is, let's say, not the typical way to go. We don't try to replicate the digital world. We try to merge the digital world with the analog world, combine them. And we don't try to do the MVMEs like a GPU, but we try to find hardware-friendly approaches that can help the digital systems without all the constraints and the complications of the scalability issues. So this is the group. All the work that I have provided is provided by our students, our common students, and our common lab. These are the two projects that we are working on, Neoteric and Prometheus. Prometheus is about, Neoteric is about reconfigurable photonics for neuromorphic applications and such schemes. And Prometheus is quite similar, but it also includes spiking and spiking neuromorphic computing with a reconfigurable mesh. So if you want more information, you can go to our website and see the different activities. Thank you for your attention.
Thank you, thank you. Any question from the audience? Again, Nikos.
Thanks a lot, thanks a lot. Yes, thanks a lot for this and nice talk. One question about the filtering, the filter scanning approach. Have you studied what's the impact of the filter bandwidth or the filter shape on this approach?
Yes. Actually, especially for the imaging application, the shape of the filter, the slope of the filter in particular, it's reverse proportional to the time response of the filter. So if you have a really sharp filter, the time response is quite large, so pixel-wise, you correlate many different pixels in time. So when you have a kernel, you can have a larger kernel, and you can correlate all these pixels together. If you have a more, let's say, less steep filter, then your time response will be shorter, and actually your kernel will be shorter, and you will be able to correlate fewer pixels in time. So we have optimized the bandwidth of the filter and the slope of the filter to the specific rate that we inject in the symbols and the problem.
I have a similar question. Sorry, is there any other? About the tunability of the weights, can be tuned arbitrarily from -1 to 1?
No. Actually, that's why we think that this concept in a way resembles a little bit the reservoir computing paradigm. Because it's not completely random. We can fine-tune them, but we can not fine-tune them, we can coarse-tune them using these hyperparameters of the filter, but we cannot have exact control over each parameter that we apply to our signal. The interesting part is that even though we apply some coarse-tuned parameters, it seems to work in practice. For imaging and for telecom, it works. So maybe it's not a necessity to go to full MVME replication in order to solve a task. That's the basic idea.
So let's thank the speaker again. And the last talk of today's workshop will be given by Ryan Hammerly from MIT and NTT with title Non-Local and Single-Chip Machine Learning Enabled by Light.
All right. Well, I guess that I'm the last talk before dinner, or if you like me, you're still in an American time zone, the last talk before lunch. I'd like to thank Nikos and the organizers for giving me the opportunity to give this talk at this session today, and for those of you who stayed to the end of the session. So this talk is going to be about two projects that we're working on at MIT, and they're both based on solving an important problem in computing at the intersection of two trends. Now, one that's got a lot of mention is that of deep learning, so the application of deep neural networks to problems with large amounts of data. And of course, we don't need the introduction to this, but a deep neural network is a sequence of layers consisting of linear matrix vector multiplication and nonlinear activation functions. And depending on who you talk to, activation functions can either be functions or maybe they're also spiking and have some dynamics. And as neural networks have gotten bigger, they become more powerful. That's seen in certain benchmarks. But this has come at the cost of an exponential increase in the required compute to run them. And so this brings us to what I think two speakers before me have already introduced. So this is a commonly spoken of topic now, which is the AI hockey stick curve. It's the idea that up until about 2012 or so, when AlexNet really set off the field of deep learning, machine learning models were doubling in size every couple of years commensurate with Moore's law. But then that switched to roughly a 3-month doubling as people started deploying these models on larger and larger GPU clusters. Now, I think what's worth mentioning is that most hockey sticks have an end, and what we're starting to see is that for the very large models, that doubling time is getting longer, and it's starting to approach that of Moore's law again. And so this suggests that probably future advances in AI are not going to be possible by simply brute force scaling up your hardware. You're going to have to improve the underlying performance of that hardware, whether it's photonic, electronic, or anything else. Okay, well, a second important trend is edge computing. And so this is based on the fact that as we move into this modern IoT era, where we're swimming in sensors and drowning in data, we have large amounts of data being generated at devices that don't have access to large amounts of compute. And this data is highly constrained because the devices have limited bandwidth between them and a cloud that does have access to compute. You can't really do cloud computing on them because of the latency, even if you could solve that bandwidth problem. And you can't do the compute on the devices themselves because of the size, weight, and power constraints. So if you combine these two trends together, then we're largely up against a wall because of this exponentially increasing compute demand to run state-of-the-art tasks. But at the other hand, you have this push towards edge computing that's also constraining the compute power you have available. And the question is whether photonics can provide a solution to this problem. A solution that will probably complement some of the existing electronic solutions out there. So right now, there are a bunch of companies that have developed AI accelerators, all based on standard CMOS hardware technologies. And it's well known from these developments that all of these accelerators are bottlenecked by their power consumption, mostly power consumption of matrix operations, and that in turn is mainly limited by the data movement costs. Can photonics provide a solution to this problem? Well, yes and no, depending on how you do it. So if you just try to reinvent the wheel and build a general purpose photonic computer, you see that that's hard because many things that are easy in electronics are hard to do in photonics. But fortunately, photonics is very good at two things that electronics is either marginally good at or not very good at, which would be data movement and linear algebra. So since most of deep learning, at least deep learning inference and also training, involves matrix multiplication, if there's some way to accelerate that matrix multiplication, then potentially you can speed up all of these accelerators. So along this direction, our group has a number of research efforts. Well, when I joined the group, I started out working on optical neural networks based on coherent detection, and that's still an active program in our group. We had a recent demonstration of this coherent detection scheme based on VXL arrays. That's about to come out in a couple of weeks. More traditional schemes based on free space optics and programmable fan-out. But the things that I'm going to be talking about today are photonic error correction and the implementation of error correction in a beam splitter mesh-based circuit, and then also wavelength multiplexed optical edge computing, or this scheme that we call netcast. And I'm going to start with this one, and if there's some time, I'll also get to the PNP meshes. So what is this netcast idea that we come up with? It's a solution to this edge computing problem that I mentioned beforehand, where we have this ever-reducing available resources at the same time, where at the same time the deep learning workloads are growing. And the question is, can photonics solve this gap? Well, we can look at different potential approaches to this. They involve custom CMOS, as mentioned before, memristor networks, weight stationary optical neural networks, and then some output stationary optical neural networks. And if you look at all of these, for example, electronic solutions, they have great performance, but then they also draw a lot of power, so that doesn't really work in many edge applications. And another really important thing is to note that this normalized performance per unit power, or roughly speaking, the energy per Mac, that's a figure of merit that has not improved commensurate with Moore's law. So even though Moore's law is not dead, and the number of transistors is still doubling every generation, Google had this great paper in 2021 where they compared the energy to do a Mac at 45 nanometer versus 7 nanometer, and that should be a 7x improvement, and in reality it was a 2 to 3x improvement. So there's a slowdown in the practical effects of Moore's law, which means that it's unlikely that accelerators will get significantly better in the future. There are many approaches trying to use photonics to accelerate these neural networks. And most of them, I would say, are based on a weight stationary architecture. So this is an idea where light is propagating through a medium, and that medium statically encodes the deep neural network weights. Sorry about that. And this works in principle because the optical propagation through that medium is essentially free and passive, so that consumes no energy. So once you set the weights in your weight stationary architecture, well, up to some caveats about that being done thermally, then the cost is entirely dominated by the input and the output. And if you make your mesh big enough, then you can have significant scaling advantages over doing it in electronics. But the limitation is that you need one photonic component, whether it's an MZI or a microring or so forth, per weight of your neural network. And since these components are really not nanoscale, they're micron scale, there are a limited number that you can put in even a very large chip like the ones that Wim Bogaerts talked about at the beginning of the day. And so it's a big challenge to making this a practical device. So there are also output stationary optical neural networks. In an output stationary scheme, it's not the weights that stay put, but it's going to be the activations on the output of each layer of your neural network. And then both the input activations and the weights are streamed into what effectively is a multiplier and accumulator. In this case, one implementation would be a homodyne detector, so that the time integrated charge on that device gives you the dot product between this activation vector and this weight vector. And if you cascade such dot products, you can get a matrix vector product, and that allows you to do the matrix vector part of your neural network. So that approach is theoretically more scalable because you only need one photonic component per neuron rather than one photonic component per weight. And in most neural networks, there are many more weights than neurons. But the limitation is, if we wanted, and another great thing is that you're streaming in the weights from somewhere, we'll call it a weight server, to your processor. So if you have an optical link between a server and a client, potentially you could just stream the weights to the client and you never have to retrieve the weights from memory. But the original approach that we came up with, it just required a large number of optical waveguides or fibers, and that would just not be practical. So if you can you can compare all these different approaches in terms of things that would matter for edge computing, and you see that no solution exists that simultaneously solves all the problems. And the proposal that we've come up with, which we call Netcast, and we call it Netcast because it involves using optics to broadcast the neural network to many users. It's a potential way to solve this. It's what I would call delocalized edge computing powered by WDM. And a really nice thing is that this is compatible with existing fiber networks and existing fiber optical components. So the work was led, well, I came up with the idea, but all of the good work was done by Alex Sludz, our excellent graduate student, who is currently working at Lightmatter. And this work was just published in a paper last year, and we have another paper on the theory that's currently under review. So Netcast is a form of delocalized computing. And what do we mean by delocalized computing? Well, let's look at the more conventional ways of doing computing. Most people are familiar with desktop computing, where you have an input, that input gets converted to bits, and then those bits are sent through an algorithm on the processor itself, which gives you your output. This works great if your algorithm doesn't consume too much power. But if that is, let's say, a very large neural network, then the power and memory constraints would require you to offload that to a larger processor. And that gives us the other paradigm of computing we're all familiar with. So, okay, Siri, what is cloud computing? Yes, cloud computing is where you do the same thing, except now you have a network that separates the data and the compute. So the data is sent from the user to the cloud does the processing, and then the result is sent back to the user. So this gives you a much lower power consumption at the edge, but on the other hand, you have problems with latency and privacy of your data, as well as the need for this two-way network. There's a third paradigm of computing that is much more specific and only works some of the time with particular physics, and this is called magic state computing. The idea is, what if there's a way to convert the algorithm into a physical object that we call a magic state and send that from the server to the client, so that most of the effort here is done in generating this magic state. If that's possible, and let's say at the client side, there is something that's called a coprocessor, which takes the data and then processes it with this physical magic state to get you your output, to get the output of your algorithm. So if you can do this, you still need a network, but it only needs to be one way. This magic state can potentially be broadcast to many users, and you don't have any privacy constraints. And if things are timed right, you also don't have latency problems. So this idea of magic state computing, it's actually something that arose from quantum information processing in the context of gate teleportation, which is the idea that sometimes you want to perform hard quantum gates, often T gates or other non-Clifford gates, on unknown data. One way you can do this is by generating what's called a magic state corresponding to that gate, and then using that magic state in an easy algorithm that consists of some easy Clifford gates and then some measurements and feed forward in order to effectively perform the hard gate on your unknown data. So this is not a free lunch. You still need to generate this magic state, and that takes as much effort as performing the original gate, but it reorders your computation. So now you can generate all your magic states beforehand and then use them on data as the data comes in without really any constraints about how long it takes to generate those states or so forth. So netcast is a classical analog to this. It's a form of classical magic state deep learning powered by photonics. And the way it works is as follows. The computation is broken down into a server and a client connected by an optical link. The server here is a WDM array of modulators that's encoding the weights of the neural network into an optical pulse train. So the weights of a neural network are a sequence of matrices. And each matrix, in this case, is going to be encoded in a time frequency basis, where the frequency channels, which correspond to modulators here, will correspond to rows of your matrix. And then the time bins will correspond to the columns of the matrix. This state is sent into your client, and then the client processes that state by sending it through a broadband modulator, like a Mach-Zehnder modulator, that scales every one of these columns by a particular element in the activation vector, so one of your x's. And then after that's done, you demultiplex all of these wavelength channels and send each one to its respective photodetector, and then accumulate in time, so that the final accumulated charge is the sum of all of these piecewise products, and that's effectively going to be equal to the matrix vector product between this W and this X. So we get Y equals W times X. So this takes advantage of a number of important features of optics to give you the required performance you need for these edge applications. So one is the requirement that we're stipulating here is all of the weights are streamed in from the server to the client. That's a lot of bandwidth, but fortunately you have access to a lot of bandwidth in optical systems. For example, in typical fiber, if you only look at the C-band, there's at least 4 terahertz of bandwidth there, and actually people are pushing beyond the C-band to the S-band and the U-band now, so that will expand in the future. So at least in principle, there's the possibility for on the order of 4 terawatts per second capacity, which is actually more data capacity than the high bandwidth memory link on the state-of-the-art GPUs now. So we know that at least the capacity exists. Second is that this makes use of 2 forms of what I'd call optical parallelism, and that's where we're performing multiple operations in parallel in using a single optical component in a single time step. So an example of this would be when you drive this modulator, driving that modulator only needs to be done once and is a single modulator, but you're scaling all of the wavelength channels in parallel. And this should be distinguished from traditional parallelism in parallel computing, where you have many cores, and each core is processing data serially. In this case, you have one core, and it's processing multiple data on that one core in parallel. You also get an energy savings in terms of the detectors, because you're reading out these detectors once after n time steps or accumulation. And so both of those costs, the modulation and the detection and readout, get amortized. Another important advantage here is that we're pushing most of the memory load, at least for inference, over to the server. Because typically you have more weights than you have activations, and so that means that the client device that has a lower memory requirement, which matters a lot for big neural networks. In addition to the fact that most of the energy consumption in the scheme is in driving these modulators at the server side and reading the memory according to them. And that's all done at the server, but that doesn't limit the energy requirements at the client side. And then finally, unlike some previous approaches that we'd come up with, here the server and the client are only connected by a single mode optical link, which makes it a much more robust architecture, and actually in the way we've done it so far, it's all amplitude modulation, so it's phase insensitive. So this is not just the same as reinventing a transceiver. You can imagine a protocol that looks very similar to this, but where we have just replaced this weight server and this client with a transceiver. In that case, you can stream weights from the server to the client, and then you can decode those weights in a digital form at the client and do neural network inference. And it will all work, and it will save you the memory at the client, but it will not be energy efficient, because when you decode these outputs coming from the receiver, that takes an energy consumption on the order of several picojoules per bit, which will correspond to tens of picojoules per weight, which corresponds to energy consumptions per Mac, which are no better than just doing everything in electronics. The difference between our scheme is that our scheme is an analog, and it performs the integration before the detection. All right, so that was the theory, and we demonstrated this in practice. So the way we demonstrated this is we used this 48-channel Mach center modulator chip, and this is something that we had fabricated in the group several years ago for some QKD experiments. It's designed in silicon photonics. Each of these channels is designed to go at some typical telecom speed. And that thing we drove with up to 16 lasers, just limited by the number of lasers we had around. So that gives us our weight matrix, which is our magic state. To show that it's possible to do delocalized computing, we send that matrix from a server to a client that are connected by a fairly long deployed optical fiber. In this case, it was an optical fiber connecting MIT campus to MIT Lincoln Lab on the suburbs of Boston, which is about 43 kilometers, with a loop back to go back to the campus. So that's about 86 kilometers of deployed fiber. And then back at the campus side, we put the netcast client, where at the client side, you're combining all of this data coming in from the server, which are the weights, with the data that's stored at the client, which are the activations, and then you're demultiplexing again and integrating. So if you look at these traces here, this is a weight modulated by the activation, or sorry, this is an activation multiplied by the weight, and then this is just the partial sum when you integrate, and you care about this value at the end, which is the final charge. This here is showing a calibration curve, showing that we can, if you send in random data, the outputs are very close to the inputs. These residuals have around a 0.5% RMS error, and that corresponds to effective bits of precision of about 5 to 6, which, as you can see for this particular example, it gives very clear, correct classification. In terms of the full ensemble of MNIST test data, we get on the order of 98% accuracy, which is really independent of whether the server and client are right next to each other, just connected by a fiber link, versus the deployed fiber that is 86 kilometers or whatever. So it really is independent of the length of the fiber, as long as you get light out the end. All right, so we also characterized the optical energy consumption of this device. You can vary the optical attenuation and look at the minimum optical power required to run this. Because if the power is too low, then you run into signal to noise ratio problems. And what you see is that for conventional time integrating detectors, that's on the order of several hundreds of photons per Mach. But if you look at single photon or quantum limited detectors, you can bring that down to a couple of photons per Mach. Now the way we did the quantum limited detectors is not really practical from a telecom perspective. This was cryogenic single photon SNSPDs. But it's also possible to do quantum limited detection through homodyne detection. And so we've also, in theory, analyzed the minimum optical energy required to do coherent netcast with Hobodyne detection, and it actually does even better than this. This experiment is something we have yet to do. All right, so in conclusion to this part of the talk, so I've introduced Netcast, a protocol for optically accelerated edge computing based on these principles of output stationarity, WDM, broadband modulation, and integration detection. We demonstrated this over an 86-kilometer deployed fiber link, and we also provided some analysis of crosstalk and noise limits to both the speed and the power, which can be seen in both of these papers. So in addition to these output stationary schemes, our group is still interested in weight stationary optical neural networks, which I think can play a complementary role in accelerating other tasks. So one example would be these PNPs, or these beam splitter mesh-based optical neural networks. And this is something that that our group is actually most well known for, which was this groundbreaking 2017 Shen-Harris result, which was machine learning with coherent optics. Recently, Shomil Bandyopadhyay, who is actually graduating this year, he generalized the 2017 result from simple matrix multiplication to a fully on-chip 3-layer deep neural network. So this is, as far as I can tell, the first demonstration in the literature of a single-chip coherent photonic deep neural network. And it involves three programmable 6x6 MZI meshes. And then between those meshes, you have to have some kind of nonlinearity. In this case, the nonlinearity is implemented through what he calls a NOFU, or a nonlinear optical function unit, which consists of driving a modulator with a detector that comes from the same signal. And you can show that this NOFU activation function, it can take a number of forms depending on the detuning of this ring and the fraction of the light that you tap out. So this is a very impressive experiment. Usually the first criticism people will make when they see this is that it doesn't look scalable. So as you scale this up, you're going to run into two problems. One is chip area. In practice, though, that is probably something that can be engineered away with enough effort. It would be a lot of effort, but people have demonstrated 64 by 64 meshes in the literature. And a lot of this is limited by what's currently available in existing silicon photonics foundries. So if we get improvements to things like phase shifters, improvements to co-integration with DACs and memory, then this could improve potentially still further. But there's a more fundamental problem, which is that this is an analog approach. And analog computing is something that has historically been disfavored because people will say it, and it is correct, that it doesn't scale due to errors. So it's sort of like saying that we're used to thinking about photonics as an interconnect, where you're just sending data from A to B and you have access to error correction and so forth because all the data is digital. But now we want to do computing with photonics in the analog domain, which, if it works, can have an even bigger impact. But now we're much more sensitive to errors in the device. As far as errors in MZI meshes are concerned, there's actually been a lot of interest in this, especially because the dominant errors in these meshes are errors due to imperfect fabrication, which only occur once at fabrication time. And if you can characterize those errors, potentially you can correct for them perfectly. So there's been a lot of work based on techniques such as numerical optimization, local error correction, in situ training, and progressive self-configuration, trying to address this error problem. And every solution has its ups and downs. Recently, we came up with what I think is a close to optimal self-configuration technique. So it's 5 minutes until the end, or the 5 minutes till the end of the talk? All right, okay. Yeah, so I'll just finish this up in 2 minutes, and then we can have questions. So we came up with some self-configuration schemes that merge both the elegant theory of how these MZI meshes work with physical techniques to correct for the errors. So the theory is that the matrices that you're trying to realize in these meshes are always products of 2x2 blocks, and that in order to, you can show that programming these matrices is equivalent to diagonalizing, or programming these meshes is equivalent to diagonalizing matrices through a set of Gibbons rotations. Now what you can actually show is that there's a physical equivalent to that, which is that Gibbons rotations correspond to sending in particular inputs to your mesh and then adjusting the phase shifts in order to zero the power at particular outputs. And if you do this correctly, then you find that all of the elements in your mesh get configured to their correct state. And what's also remarkable is that this works not only for perfect meshes that have no hardware errors, but also for meshes that have imperfect hardware. And also that you can generalize it from these triangular meshes to the more useful rectangular Clements design through what we would call row and column Gibbons rotation permutations. So after coming up with these protocols, we decided to implement them at least in software and see how well they work numerically. I guess to cut to the chase, you find that compared to not doing any error correction and programming the meshes naively and doing error correction as a function of your MCI error, you see that you have about 10x or more suppression of total errors in terms of your matrices. And that's really good if your component errors are low enough. Many components have slightly higher component errors, but have better properties such as being more broadband. But you can see that still for many mesh sizes that gets you to below the several percent that you want in order to get good accuracy on neural networks. Now, some cases that's not true. I think that I'll skip through this because it's a little short on time, but you can actually show that there are modifications to these MZI meshes that effectively reduce the number of times that this error correction fails, that improve the performance of the error correction even more. Let me skip over that. Just conclude. I guess that we have a number of other projects here that I mentioned. One is related to implementations of this coherent detection scheme based on a VXL array. So this was work that was done by Zaijun Chen, and it's going to appear in Nature Photonics in a couple of weeks. Zaijun is currently a faculty at USC. We have some work that recently just came out in Science Advances on free space optical neural networks, where you're making use of programmable fan-out, sorry about that. You're making use of programmable fan-out in the frequency domain to let you do neural networks of really any size that fits within the SLM. And then, I guess since quantum was mentioned earlier in this symposium, I just wanted to mention we have some collaborations with some people at Stanford looking at how you would do quantum gates with nonlinear optics with materials that might be available, with material platforms like lithium niobate and the values you would expect that might be available in the next couple of years. So with that, I'll just conclude. I'd like to acknowledge the people who did this great work. If you're interested in getting involved, we're certainly open to collaboration. And if you are looking for a job or have students looking for jobs, certainly have them contact me. Thank you.
Thank you, Ryan, for the excellent presentation. Is there any question from the audience? I do have a question regarding the end-to-end photonic neural network. You used unitary weighting for, because I see, can you go to the slide, please?
Regarding which one again?
I don't remember the number of the slide. Ah, this one.
This one?
Yeah, this one. This is for unitary weighting, right?
Yeah, the weighting is unitary, but of course the nonlinearity is non-unitary.
No, not about the nonlinearity. So how you train the network? Just with unitary weights, and the accuracy was sufficient?
Oh yeah, that's a good point. So there are many different training algorithms you can use for these. I think one that got a lot of attention is the scheme by Shanhui Fan's group that just came out in Science in a paper by Sunil Pai a couple of months ago. That requires that you have photodetectors everywhere after every MZI in your chip. So it wasn't something that was available for this chip, but it does let you do backpropagation. Another possibility is what's called physics-aware training, which is something that Logan Wright and Tatsuhiro Onodera and Peter McMahon's group did. Is that in Nature last year or either the year before? And that's where you do forward propagation in the hardware, and then you have some reasonably accurate model of your device that lets you extract an estimate to the gradients in software. And that actually works much better than doing forward propagation in software as well, because the forward propagation in hardware, it lets you correct for the errors in the hardware.
Yes, yes.
And so forth. But in this case, especially the nonlinearity in this system appeared to be too complex to do that straightforwardly. And so we used a variant of what we call random direction search, where you pick random perturbations to all of your phase shifts. You do a step in that direction. You estimate the gradient from that step, and then you descend as you would in regular gradient descent. It turns out that this does better than coordinate descent, where you perturb a random element. Why it does is not entirely clear. It might have to do with the dimensionality of your manifold being, the manifold of useful states being different from the full dimensionality of all of the phase shifters. But that was how this was trained.
Yes, thanks a lot, Ryan. So on the same matter here, so typically a neural layer implements a random non-unitary, so any matrix in its linear part.
Yep.
So here, since you are using a unitary matrix instead of any possible, this means that you had an extra restriction to your weights. So does this type of deep neural network perform over a certain restricted pool of applications, or does it have any extra limitations due to the fact that you use the restriction of unitarity in its linear part?
Yeah, so I don't know if there's a clear sense in the neural network literature whether unitary neural networks are more constrained or less constrained than non-unitary networks. Certainly the fact that you have non-unitary elements between the neural network layers, I think that's critical, because any kind of learning involves compression of information where you want to get rid of all of the noise and extract out the signal, and that's not possible if you only have unitary elements. But that's just equivalent to us also not being linear. You could do the SVD scheme where you stack two clemences and you have an SVD. There are other ways to do non-unitaries as well. They require twice as many phase shifters, so putting that on this chip would probably be out of the question if you wanted to have 3 layers, given the way this chip was packaged. But it's also worth mentioning that traditional neural networks, they're not complex valued either. They're real valued. And an n by n unitary matrix has the same number of degrees of freedom as an n by n real valued matrix. So it's not like we have fewer degrees of freedom in here than, say, a 6 by 6 by 6 that you would just train in TensorFlow.
So, one last, Adoni or what? Okay.
Actually, I forgot my question. Right. So there's a trend in putting the computation in memory to deal with the bottleneck, or von Neumann bottleneck, and so on. But you spoke a bit, and it seemed very interesting, this approach of streaming the weights. So essentially, purposely putting the weights out of the memory, while you could potentially have the alternative implementation. So could you comment a little bit about these kind of orthogonal directions?
Yeah, so Professor Vivian Z at MIT likes to distinguish between different kinds of stationarity. So there would be input stationary, weight stationary, and output stationary, and usually it's weight stationary is what most people use. And yeah, that's motivated by the idea that most of your memory is the weights, and you want to keep those stationary well to minimize the total amount of data movement. But yeah, weight stationary it has a lot of advantages for electronic in-memory computing, because those weights can be made really tiny if they're memristors or even SRAM cells. But in photonics, those weights can be pretty big. And so the density becomes a disadvantage. And also the disadvantage of weight stationary, which is that you have to, the disadvantage of output stationary, that you have to send a large number of weights into the system. That no longer applies in photonics because now the data movement is free. So we've reversed the equation, and maybe output stationary is a lot more advantageous than weight stationary. That being said, the output stationary scheme I talked about here, Netcast, it doesn't reduce, if you only have one client, it doesn't reduce the overall energy consumption because you still need to read those weights from memory every time you do the computation, and the memory reads tend to be very expensive. So if you care about reducing the client-side energy consumption, it's great. And if you have 1 million clients and you have some broadcast, then it could also be great. But I think weight stationary avoids this because, well, you're never actually reading the weights from memory. The compute's done in the memory.
Thanks.
So let's thank the speaker again. Don't you want to add something?
And for tonight, yes. Okay, for our speakers, at 9 o'clock, you know the place, okay, for the dinner. And for those who are interested, 20 minutes before in the Monastiraki Square for the brief tour. And of course, tomorrow at 9:30, please come 10 minutes before, so as to start on time. We will have the second day of this workshop. Thank you all for being here, and I think it was a very successful day today.